Hi, can we start? Is it, yeah, I think we are live, right? So welcome everybody to the second day of our summer school. I don't want to take too much time out of our schedule, so let's start immediately and welcome our first session today. That's going to be about dataset and software. There are going to be many cool speakers, and the first one is going to be Joe and Carl, and they're going to talk us a recent dataset called Fusion 360. I think it's going to be a video, so if you can start playing it at the end of the lecture, there we're going to be some live Q&A, and you can ask your question either on the Zoom chat or on the Discord channel.
Hello and welcome to this talk on the Fusion 360 Gallery dataset, learning segmentation, reconstruction and assembly modeling. I'm Joe Lambourne from Autodesk Research, and this presentation was also made by Carl Willis. I'd like to start by telling you about our motivation for building the dataset and for conducting research in this area. As I'm sure everyone here will be aware, neural networks working with 2D images and 1D sequences have shown amazing progress over the last decade, becoming the standard method for implementing functionality like image classification and segmentation, dictation software, and machine translation. However, the data which Autodesk users work with is very different from images, text, and audio. We write software which helps architects design buildings, mechanical engineers create machines and consumer products, and animators make 3D movies and game assets. In this talk, we focus on mechanical engineering and design for manufactured parts. These consist of large assemblies, each containing a large collection of individual solid models. The kind of functionality we hope to enable is the recognition of characteristic structures within models, like these clips, ribs, and bosses. Also providing tools which assist users with tedious selections. Tools to help engineers identify and remove superfluous details from models, allowing faster simulation of mechanical properties of parts. Also, we hope to completely automate repetitive tasks, like the placement of bolts, nuts, and other fixtures, which are commonly used to hold mechanical parts together. Finally, we aim to provide new ways in which geometry can be created, for example, based on point cloud or image data. To allow us to investigate which machine learning architectures might be suitable for solving these problems, we built the Fusion 360 Gallery dataset. We derived the data from a collection of CAD files created by users of the Fusion 360 CAD software and posted to the Autodesk Online Gallery. To understand the content of the dataset, it's useful to understand a little bit about the design process in mechanical CAD. The designer starts by creating 2D sketches, which can then be extruded to form 3D solids. Additional operations like edge blends can then be applied. Further extrusions can be used to add to or cut material from the model. All these user actions are recorded in the design timeline, a parametric modeling history which can be used to facilitate editing of the geometry. Each solid model created in this way is stored in the boundary representation or BREP format. A BREP is similar to a triangle mesh, except that many of the restrictions are lifted. While meshes are typically limited to having planar triangular faces, the faces of BREP models can take any shape, including cylinders, cones, or freeform spline surfaces. The edges bounding each face can also comprise of any curve type, including lines, arcs, and splines. Finally, these individual BREP models are aligned and connected together to form larger assembly structures representing objects with multiple parts. The dataset is divided into 3 subsets, each focusing on a different aspect of the data. The reconstruction subset exposes the timeline information, allowing geometry synthesis models to be trained to build solids using sequences of sketch and extrude operations, just as a designer would. The segmentation subset focuses on the problem of how to understand BREP geometry and topology and recognize substructures. The assembly subset focuses on the task of how to align individual solids to build entire machines. Let's now take a look at the reconstruction dataset that contains over 8,500 3D designs with the underlying sequence of modeling operations used to create them. To balance design expressivity with a tractable problem for learning-based methods, we limit the modeling operations used in the dataset to sketch and extrude, two of the most common operations used in parametric CAD. Sketches are composed of 2D primitives such as lines, arcs, and circles that can be lifted into 3D using the extrude operation and combined with other shapes using built-in Boolean operations. To expand the size of the dataset, we suppress unsupported modeling operations such as fillets. The wooden chair design is shown here before and after the fillets are suppressed. Here we show example designs from the dataset colored according to the number of extrude operations, covering simple designs with a single extrude on the left to more complicated designs on the right. We consider each design as a parametric CAD program, where user input when drawing lines or extruding sketches has an underlying program representation with parameters that can be dynamically adjusted. Using CAD software, the program can be executed to produce the final geometry. We provide an environment called Fusion 360 GIM to execute CAD programs provided in the dataset and to enable real-time interactions with Fusion 360 via a high-level Python API. Moving on to the segmentation subset. This data provides a segmentation task for the faces of the BREP model based on the operations which created them. The Fusion timeline keeps track of which faces in the final model were created by which timeline operation, allowing us to produce labels which document how a part was created. For this data subset, we include models created using additive extrusions, subtractive extrusions which cut material out of the solid, edge blends which are commonly referred to as fillets, chamfer features, and finally revolve features. As for the reconstruction dataset, other modeling operations are suppressed. Faces created by extrude and revolve operations are further subdivided according to whether the face was on the side or the end of an extrusion. This gives a total of 8 classes for faces. The entire dataset contains 42,900 BREP bodies. This mosaic shows some examples. Finally, the assembly dataset contains over 8,000 assemblies, with more than 150,000 individual parts. Each assembly has a user-defined structure where individual parts are grouped together into sub-assemblies. Parts are also connected by joints that are created by designers to define the degrees of freedom between pairs of parts. We also provide labels for surfaces that are in contact with one another and surfaces that represent holes. These hierarchical and connectivity relationships enable several graph representations for each assembly, such as a parts graph that forms the topology between parts, and a hierarchical assembly graph based on the designer's grouping of the parts. Now I want to talk about some of the work that we've done in Autodesk Research, looking at this pattern recognition problem. We had 2 publications in this area in CVPR 2021. I will describe the UVNet architecture now in a little bit more detail. UVNet extracts a face adjacency graph from the BREP's topological data structure. In this graph, the nodes are faces, and the edges represent adjacent faces sharing a common geometric edge. BREP geometry consists of many different curve and surface types. These include analytic curves and surfaces like lines, arcs, planes, and cylinders. Also freeform curves and surfaces represented as splines. While the equations defining these geometric entities are very different, they're all parametric, i.e. every curve maps an interval of the real line, called the U-domain, into 3D space, and every surface maps a rectangular 2D UV domain into 3D space. UVNet uses a unified point grid representation for these parametric curves and surfaces. Parametric curves are polygonized with a fixed number of equally spaced points. The UV domain of the parametric surfaces is then sampled to build up a regular grid of 3D points, normal vectors, and Boolean flags indicating if each point is inside the visible region of the face. At inference time, the UVNet architecture processes the input data as follows. A convolutional neural network processes the point grids from each surface, compressing the 3D coordinates, normal vectors, and trimming mask into a single embedding vector. A similar 1D convolutional neural network processes the point coordinates, tangent vectors, and normals of the adjacent faces. These embeddings from the BREP faces and edges are then used as node and edge features in a face adjacency graph, and a message passing network is used to propagate information across the topology. This diagram shows a summary of the architecture. The node embeddings at the output of the graph neural network can be used to identify the class of faces in the Fusion Gallery segmentation problem, or they can be pooled to form a global shape embedding for object classification or search tasks. Our results show that UVNet obtains state-of-the-art performance on the Fusion Gallery segmentation problem, with an intersection over union score of 79.37%. Both BREP-based methods outperform networks for processing meshes and point clouds, demonstrating the advantage of working directly on the BREP representation. Now I want to talk a little bit about one of the techniques we've tried for addressing the reconstruction problem. In this work, we go beyond what is made to focus on how shapes are made. Specifically, we use learning-based methods trained on human design sequences, such as the sketch and extrude modeling operations shown here. Learning how a shape is constructed matters because it allows us to dramatically improve editability of that shape. In parametric CAD, the prior steps in a design can be edited to quickly and meaningfully change the design. Here we edit the game controller design at different steps in the timeline to produce design variations. So what applications might the knowledge of human design sequences help with? These applications fall into two categories: forward problems and inverse problems. With forward problems, a partial design sequence is available, and the goal is to predict the next steps to autocomplete the design, much like we do with word or sentence autocompletion in our phones today. We might also go further to synthesize entire designs, generating realistic CAD models from learned distributions. With inverse problems, some representation of the final design is available, and the goal is to recover the steps taken to create that design. A classic example is reverse engineering, where from a 3D scan, we hope to recover a parametric CAD file. In Cad Reconstruction, given an input geometry, the goal is to recover a CAD program that can be executed to reproduce the input geometry exactly. In our work, we assume input geometry in a BREP format and output as a Fusion 360 CAD program. This represents a common scenario where the modeling history is lost when designs are exported into a neutral CAD file format. In recent years, several approaches have been attempted for CAD reconstruction. Common in prior work is the use of constructive solid geometry with parametric primitives such as spheres, cylinders, and cuboids. Rather than CSG primitives, we use a learning-based approach trained on real-world sketch and extrude modeling operations for the first time. Let's now look at how we set up the task. We design an agent that interacts with our Fusion 360 GIM environment. At each step, the state containing the current and target geometry is communicated to the agent. The agent outputs an action in the form of a modeling operation to progress the current geometry towards the target. This loop continues until we've fully recovered the target geometry or exhausted the search budget. To represent the state, we use a face adjacency graph derived from the BREP model. Each node in the graph represents a BREP face, and links in the graph represent BREP edges in the design. We use graph node features similar to those used with UVNet, consisting of uniformly sampled points, normals, and a trimming mask, indicating if a sample is inside or outside of the trimmed surface. We also include the face surface type. We represent modeling operations with a face extrusion action representation. Here we leverage a knowledge of the target geometry to extrude from a start face, defining the extrusion profile, to an end face, defining the extrusion distance. Finally, a Boolean operation is used to indicate if the extrusion should generate a new body or join, subtract, or intersect with the existing bodies. Here we can see the whistle design is recovered using two face extrusion actions. We estimate that approximately 80% of designs can be represented with the face extrusion representation. Some designs do not have sufficient information in the target geometry. For example, the sketch used to subtract from the top of this design is not present in the target. We provide support in the Fusion 360 GIM for an alternative low-level sketch extrude representation, where individual sketch curves are drawn and then extruded. In the remainder of this section of the talk, we show results using face extrusion. Our learning-based agent consists of two separate message passing networks that create embeddings for the current and target geometry. These embeddings are combined, and a multi-layer perceptron is used to output an action containing the start face, end face, and the Boolean operation. To amplify performance, we use the probabilities from the network output to guide a search for the target geometry. This allows us to traverse numerous paths and find the target within a given search budget. In the paper, we present results for multiple agent types and search strategies. We include a random agent as a naive baseline that randomly picks actions, an MLP agent that doesn't utilize message passing, and several message passing network agents. In the remainder of this section of the talk, we present results using random rollout search. We measure performance based on exact reconstruction when the intersection over union value between the target geometry and reconstruction is 1. In this example, the two top results are considered correct, as either order correctly reconstructs the design, but the bottom result is incorrect, as the second extrusion is too large. In the best case scenario, it's possible to reconstruct the ground truth test set in 20 steps, the length of the longest sequence. Here the x-axis represents the number of face extrusion actions executed in the environment. The y-axis shows the cumulative exact reconstructions, where a value of 100% indicates the entire test set has been correctly reconstructed. Additionally, we show the estimated face extrusion representation limit. Note that single extrude designs will be reconstructed before the longest sequence in the dataset. We find that the random agent does well on simple designs with short sequences. Our face extrusion action representation makes it easy to recover these designs, as there exists only a single solution to extrude between two planar faces. The neural guidance provided by the MLP agent improves search performance, even without message passing. The addition of message passing further improves performance, correctly reconstructing 68% of the test set. Let's now look at some reconstruction sequences using different agents. Even with short sequences, the random and MLP agents can struggle to fully reconstruct some short sequences. The message passing agents perform well on short sequences, but performance drops as sequence length grows. Let's now take a look at working with the assembly data. Joinable is our method for learning bottom-up assembly of parametric CAD joints. This is joint work between Autodesk and MIT CSAIL and was recently presented at CVPR. So what's the problem that we're trying to address? Real-world objects can be made of hundreds or even thousands of individual parts. Assembling all those parts together in CAD is a critical but often tedious process. In fact, assembly accounts for 1/3 of all time spent in CAD. So what does the process look like? Here you can see, even in this simple example of a pump assembly, the designer has to manually select and assemble multiple parts again and again. This is not only time-consuming, but can also be error-prone. You might imagine that we can help designers out if we could automatically predict how to attach the next part based on the current state of the assembly. Our research question can be shown visually. Given a pair of 3D shapes, can we automatically assemble them without any prior knowledge of the global design, its object category, or additional human input? So in this case, these two parts come together to form a pair of scissors. But how have other researchers tackled this problem to date? Almost all prior learning-based approaches take a top-down approach, using human annotations in the form of object categories and semantic segmentation labels. They learn a global pose for each part. In our work, we want to overcome the reliance on human annotation labels and learn from the information available in standard CAD files. We take a bottom-up approach that learns from the local joint connections between pairs of parts. We do this without object category labels or any human guidance. This joint information is stored in the CAD files and set up by designers who select faces and edges to mate pairs of parts together. So let's consider a simple example where we want to position a peg in a hole. Each part is modeled in the boundary representation format and contains edges and faces. The edges and faces highlighted in blue are the ones that the user clicked when setting up the joint. These are used as supervision. We represent each part as a graph, where the BREP faces and edges are nodes, and the graph edges are defined by adjacency. The aim here is to predict the nodes the user selected. We can visualize the prediction space as a 2D matrix, representing all possible connections between these two graphs. Given a prediction, we can then recover and align the joint axis to place the peg in the hole. Let's take a look now at the joinable architecture. Our encoder generates embeddings for each node in each graph using multi-layer perceptrons followed by a message passing network. Next, we perform dense edge convolution between the two graphs and predict the joint axis. Finally, we perform a neurally guided search to find suitable joint parameters for the final assembly. So how does joinable perform? We find that for top 1 accuracy on the joint prediction task, joinable can almost match human performance. We find that methods using the boundary representation do well, including both heuristic and learning-based methods. Point cloud-based methods, on the other hand, struggle on this task. For the joint pose prediction task, the aim is to assemble two parts to match ground truth. We again outperform the point cloud baseline. The output from joinable produces similar results to the ground truth most of the time, or realistic configurations. In summary, we find that joinable's bottom-up approach can be effective at pairwise assembly and generalizes to arbitrary parts without object category labels. A clear direction for future work in this area is to tackle the challenge of multi-part assemblies and combine the benefits of bottom-up and top-down learning. This will open up numerous applications, from CAD-aware generative models to CAD assembly automation. We've looked closely at different tasks that solid models can support and how to use machine learning to perform these specific tasks. Let's now take a look at some future applications that could be enabled using the dataset. The ability to find and place missing parts in an assembly can help eliminate repetitive work for designers. In a similar way to image inpainting, we might mask out a part of an assembly, then try to identify the part and correctly place it back in the assembly. Critical to this work will be the development of a representation of CAD assemblies that combines both local and global information. For known or common components, it shouldn't be necessary for human designers to perform every modeling operation. Instead, given a sequence of CAD modeling operations, we can imagine a system capable of auto-completing the next steps in the design, much like we do with text input for search or messaging. Machine learning also has the potential to dramatically change the interfaces for how we design in CAD. For example, the ability to blend between designs and create hybrid designs opens up new ways for creative exploration not previously possible. It's an exciting future ahead, and we look forward to seeing what you all create with the Fusion 360 Gallery dataset. Hello and welcome to the...
Wow, that was really, really cool. Now there is some time for some Q&A. I think Carl is here. So again, if you have questions, there is the Discord channel or the Zoom chat. Let me try to keep an eye on both. Okay, so is Carlo Joe here? Oh, there's so many participants. It's long to scroll through. I don't see them. So if Carlo Joe are online, could you please unmute yourself, open the camera, and speak so I can try to find you? Hmm. I don't think they're online. So if you have a question, you can use the Discord channel, and hopefully they're going to be there and answer your question. I would say in with the purpose of trying to remain on schedule. Yeah, I also think I haven't I've scrolled through. It's nice there. It takes some time to read through the names because the list is long. I also don't think either of them are online. Yeah, so there is always the Discord channel. If you have questions, they should be in it, and they should be able to answer. So I would say, with the purpose of trying to keep on schedule, the next talk is scheduled in about 10 minutes. So yeah, let's wait out. I mean, if you want to chat about anything, I'm here. I mean, we're all here. Okay, I think we are ready to start our next tutorial, and it will be a data set again, and Angela will be presenting it. And by the way, if you love her talk, which I'm sure you will, she also will be giving a keynote later in the main SGP. So yeah, she will be presenting live. So go ahead. It's all yours.
Okay, hi everybody. Thanks for having me here today, and I'm happy to present a tutorial on how to learn to understand 3D from large-scale indoor scene data. So, of course, we're interested in understanding 3D and understanding geometric structures for the sake of, for instance, applications like autonomous navigation, understanding where all of the other cars, where all of the other objects are in scenes for autonomous cars, or for robotics to be able to move around, navigate, and eventually interact effectively with a real-world scene. And of course, also for content creation and mixed reality in order to be able to create interactions, for instance, between virtual objects and real environments. And so, of course, in many recent years, we've seen that there's been a huge revolution in 2D image understanding and semantic understanding, particularly driven by the availability of large-scale annotated image data, along with developments in deep learning and convolutional neural networks. So what I'm going to focus on today is taking a look at the development of ScanNet, and in particular trying to construct a large-scale 3D data set that can provide a similar kind of jumpstart in understanding geometry and semantics. So this is circa basically 2017, where the 3D data sets that were available were substantial, for instance, for benchmarking, but not necessarily for large-scale training. And so what we took a look at here is how to collect bunch of scans from 3D scenes, real-world 3D scenes in real time in order to be able to facilitate basically large-scale capture of 3D environments. And so this is what this kind of real-time 3D reconstruction looks like. It operates on the fly and allows for basically efficient reconstruction of many different kinds of environments, which means that we were able to go around and just scan as many environments that we could acquire access to in order to build up a large-scale 3D data set of indoor scenes. And so that provided an order of magnitude more 3D data. Of course, it's not just the RGBD scans and geometric reconstructions, but we built up a scalable annotation process, which builds upon the 3D reconstruction, then an over-segmentation that is based on a Feld-Schwab segmentation, and finally an online interface for people to be able to provide crowdsourced annotations on top of the segmentations on the scans. And so this allows for an efficient capture. Here you see the scanning process where you see both the depth and the color. So a person can go around and capture a scan with some indication as to what is an effective, useful kind of 3D reconstruction or not, upload it into the server where it gets reconstructed, and then finally be able to annotate individual object instances with free-form text labels. So this allows us to build up a data set that contains about 1,500 annotated 3D reconstructed scans. So this involves annotations that are not only in 3D, but we can project these annotations from 3D back to the original RGBD frames. So here you can see that the raw about 2.5 million RGBD frames with the 3D semantic annotations being projected back into the color images. And that allows for also some information as to how we can start to understand color and geometry jointly together. So here you can see, in comparison to some of the other data sets that were available at the time, that ScanNet has provided significantly more labeled object instances with both the RGB and the depth and geometric reconstructions. So how can we leverage this in order to be able to understand what's going on in 3D environments? So one thing, of course, is since we have both modalities of RGB images and 3D geometry, how can we effectively combine them together in order to be able to inform tasks like semantic segmentation? So, of course, one thing to note is that the way that sensors sense depth is that the geometry typically comes in at a much lower resolution than color images. So if we want to combine them together effectively, rather than just projecting colors on a per point or per voxel label onto the geometry, we can more effectively compress information from a much higher resolution color image by first encoding them with a pre-trained 2D convolutional feature extractor, which spatially compresses down the information while extracting more semantic features in the feature channel domain, and then back projecting that, since we know the camera pose information in the RGBD reconstructed scans, into 3D, where we can then combine it together with 3D features that are extracted from geometry in order to be able to get semantic segmentation on a per point basis on the surface of the reconstructed mesh. And what we can look at here is the interaction between the color signal and the geometry signal for this semantic segmentation task. Here, this is the average class accuracy over 20 classes for semantic segmentation. And when using color only, basically taking away the geometry features in this pipeline, then we can get an average class accuracy that's similar in some sense to using only the geometry features. But if we combine them together, we can see it's actually a fairly complementary amount of signal that's being understood from this. So you can better able to identify things like pictures and windows and doors that are difficult to understand from a purely geometric signal. And geometry helps to distinguish between objects that are physically separate from each other, but they project close to each other in terms of the pixel space and images. And so we can also take a look at how this operates with different numbers of color views per associated geometry. And so if you increase the number of views, you get an increasing amount of performance here, although the amount of increase does marginally kind of decrease as the views become more and more redundant when you increase to an even larger number of views. So what you can see is that for this kind of approach to jointly understand from both the color and the geometry signal based on this first kind of color feature compression allows for a more consistent understanding of the labels. And in particular, you can see stuff like doors and windows are more accurately understood based off of this joint understanding from color and geometry. So this provides semantic segmentation. So we have a notion of what kind of object classes are there associated with the geometry, but not necessarily instances. So if we want to be able to segment out individual object instances, along with their semantic labels, then we can take a similar kind of approach to extract joint features from color and geometry. So extracting first with the 2D pre-trained convolutional encoder, back projecting into 3D and combining it with the geometry. And then performing 3D region proposal in this space where we consider small anchors for smaller objects with a smaller receptive field size, and large anchors for larger objects with a larger receptive field size. And this can then provide the detection for object instance masks based on these joint color geometry features, which allow for robust instance segmentation in 3D. So again, we can take a look at this interaction between color and geometry. And here, when we use the color only branch or the geometry only branch, you end up with a similar kind of performance. Whereas when we combine them together, you see there's actually a very complementary factor to both signals, so that they end up producing a much higher performance in combination together. So here you can see qualitatively what this looks like in terms of the object instance segmentation, where we end up with a fairly reliable detection of bounding boxes, as well as the object instance masks in 3D. So this was already several years ago, these works, I think, just but they provide an interesting perspective in terms of how we can potentially combine together these different modalities that we can acquire in terms of RGBD. So what we can see is that there's been an increasing interest in terms of 3D semantic scene understanding, and in particular on the ScanNet benchmark challenge, which evaluates tasks like 3D semantic segmentation on a hidden test set in order to try to provide fair evaluations across all methods. There's been a significant number of entries and quite a lot of improvement in terms of performance. Here you see an average IOU. There's already methods that are in this like top 10 set of methods, quite some competitiveness in terms of the average IOU performance here. And again, this one is on the same 20 class semantic segmentation. And what's notable here is since taking a look at these approaches, combining color and geometry together using dense 3D convolutions, what's been a huge effect on 3D semantic segmentation is the introduction of the sparse convolutions, and particularly with the sparse ConvNet and Minkowski-net engine that provide a basis for operating efficiently, memory-wise efficiently in 3D. And so, of course, here you can see the effect of the sparse convolutions is to save upon the representation of empty space that would be quite significant in terms of a dense 3D volume, and only apply convolutions where there is some notion of surface geometry. And so this is extremely memory efficient relative to a dense 3D convolution, and allows for going up to much higher resolutions. So all of these methods, I think, are operating somewhere around the 2 centimeter voxel resolution, and the vast majority of them operating on a sparse convolutional basis in order to be able to provide this kind of effective performance. So we also have instance segmentation, so detecting objects and segmenting out their object masks on the ScanNet benchmark challenge. And here you can see also quite some competitiveness in terms of the performance evaluations. And many of these approaches are also following a similar kind of trend in terms of computing an effective grouping of features that are low-level features that are computed in some kind of pseudo bottom-up fashion in order to be able to find object instances, since these 18 categories for instance segmentation tend to be somewhat physically separate from each other as sort of large furniture categories. And so this proves to be a fairly effective kind of approach in terms of understanding object instances. So now we see there's already some bit of performance saturation on this benchmark, which leads us to the question, well, a few questions in terms of open challenges, one of which is collecting real-world data in 3D is still particularly expensive in both acquisition and in annotation. So how can we efficiently learn with even more limited amounts of data, such that we can potentially scale up data acquisition and annotation in a more efficient fashion, or just learn more effectively from the limited data that we have available? And so here we have this data efficient challenge, which is separated into two kinds of scenarios, which you see here. One is that we have many reconstructions, but only limited number of annotated point labels. And the other is a limited number of reconstructions with full annotations. So here you can see that these two kinds of scenarios where we have the limited scene annotations, you have a very small number of points per scene in these four different number of labeled points per scene, as well as a relatively small number of reconstructions that are available. And we have these data efficient challenges available on the ScanNet benchmark for 3D semantic segmentation and for 3D instance segmentation in order to encourage development of methods that can more efficiently learn under limited data scenarios. And so what's been quite promising are several methods that have been developed recently. For instance, point contrast and contrastive scene contexts that leverage this kind of notion of self-supervised pre-training in order to be able to simply do a smaller scale fine-tuning for a variety of downstream 3D semantic scene understanding tasks. And they take advantage of developments in representation learning in 2D that take advantage of contrastive learning across different augmentations. And in this case, in particular, what we have in 3D is, for instance, different views that see the same point location that can be constructed in terms of a contrastive formulation to identify which points are the same and which points are different. And with contrastive scene context to take it into account larger kind of scene contexts in the same kind of contrastive formulation. And these methods have shown that they can actually consistently provide improvements across 3D semantic segmentation, instance segmentation, and also in the limited data scenario for a few points in IOU or MAP across each individual tasks. This can be quite effective in providing a pre-training approach to get the most out of limited data. And so here we've talked a lot about how to understand 3D, and I want to briefly mention also why that's important, potentially also with respect to helping understand 2D learning. So can we leverage 3D priors in order to better help 2D image understanding, since intuitively the images are being captured of a structurally 3D geometric representation? So if we can embed some kind of 3D priors into these learned 2D features, perhaps we can also learn more efficiently across challenges from 2D image understanding, like learning view invariants. So for instance, we can construct the scenario here where the 3D information provides information about different kinds of view invariances that we can explicitly then learn for 2D representations, as well as encoding geometric priors under these 2D, 3D correspondences. So explicitly associating geometry with 2D. And we can do these both with a contrastive loss formulation. So first, a view invariant contrastive loss that takes two color images with a shared 2D backbone and contrasts basically points that are associated together that are the same points under different views should correspond to each other in order to encourage learning view invariance in these representations. And then also learning geometric priors where we associate images and corresponding geometric volumes in a 2D, 3D contrastive loss formulation where we associate 2D locations and 2D features from the same locations as the 3D features in order to embed this notion of geometric priors into the learned representation. So we can combine those together in terms of a joint pre-training approach. Again, that's self-supervised based on just the nature of these RGBD reconstructions, is that they come with this color geometry association already without any extra kind of annotations. And what this can provide in comparison to a variety of alternative kind of pre-training approaches, in particular from ImageNet pre-training on 2D semantic segmentation, is more consistent and more robust results based on this 3D prior embedded representation learning for 2D. And in particular, this is also effective in terms of this limited data scenario where we have a limited amount of training images available across two different backbones, ResNet 18, ResNet 50, and the view and geometric priors are this purple line here, as you see that, in fact, even with a small amount of training images, we can recover a significant amount of the performance based off of just a full pre-training with ImageNet pre-training. So in fact, what's particularly interesting here is that we can leverage these 3D priors, in fact, to improve and help to learn 2D representations by explicitly trying to learn these notions of geometric priors of view invariance. So finally, this is an interesting kind of still open challenge in terms of how to effectively learn with limited sort of data. But in particular, I think there's another very interesting kind of challenge here, which is that the original ScanNet benchmark that we saw in terms of like pretty high performance in terms of semantic segmentation, instance segmentation, it evaluates only on 20 class categories that you see here, which is not a particularly realistic scenario. And is not really reflective of really in the wild 3D understanding. Whereas what we would like to be able to look into is really just large vocabulary 3D scene understanding. So in particular, we've just recently released the ScanNet 200 benchmark, which evaluates approximately 200 class categories. And so you see here, and this is again in a log domain. So there's a very strong natural long tail distribution where we don't see very many instances of rarely observed categories versus the more commonly observed categories. And this allows for a much more refined understanding of 3D scenes, or so that we hope that the benchmark will encourage in terms of the ScanNet 200 class categories that you see here in comparison to the original 20 class categories. And so the first sort of take that we've looked at here is to ground this large vocabulary 3D scene understanding with contrastive pre-training against powerful language features that have been trained in a domain where there's far less of a long tail distribution than we have in the 3D domain. So we try to anchor 3D features to, in this case, clip text features. in a joint latent space in order to ensure a more structured feature learning in 3D. And that kind of pre-training approach allows for a more effective grounding across language features. And this also shows, for instance, in this limited training data scenario, we can actually achieve a pretty high performance with a very limited amount of 3D data that's available. And that is decently close already in terms of the 100% 3D data available scenario that's here. But of course, you can see now in this approximately 200 class category scenario, the absolute MIOUs are far lower than they were in the 20 class scenario. And so, of course, there's much more to be seen in terms of how to actually tackle this large vocabulary understanding task with this inherent long-tail distribution, and in particular with respect to these 3D scene understanding tasks, semantic segmentation, instance segmentation, and under limited data. So I just want to end with a few notes in terms of these open challenges, I think, that are still extremely interesting in this domain as to how we can efficiently learn with limited data that's available in 3D, and how we can effectively tackle these kinds of tasks of large vocabulary learning and long-tail semantic understanding, in particular for the 3D scenario. So of course, we welcome you to take on this challenge on the benchmark that's available and develop also new and interesting methods in order to address these semantic scene understanding tasks. All right, and with that, I'm like to conclude. I'm also happy to take a question or two.
Thank you for the talk. So again, I'm trying to monitor everything here. I'm not seeing any questions. So again, there is the Zoom chat and the Discord channel. So I have a couple of questions on my own. The first one is, you have a website to help, the outsource the annotation, which seems like a crazy task. I have a question. Did you consider also outsourcing the scanning, or is it too complicated, delicate process that it's better that if it's done by someone that knows what it's doing?
Yeah. So at the time, we had it's a good question. We wanted to, in some sense, outsource the scanning, and to some degree, we did send. Just people that we knew, iPads with structure sensors in terms of the scanning and acquisition process. And we did collect a fair number of scans this way, but the vast majority was not necessarily outsourced. That was just collected by basically 4 people in total. And that was because, while we had a decently robust 3D reconstruction framework, we didn't really put in, we didn't have so much in terms of a full framework for how to respond to user feedback and interaction, because while our reconstruction ran in real time on while streaming to a nice desktop GPU, it didn't run on mobile on device, and so that made it a bit hard to fully crowdsource that particular kind of reconstruction. These days, there are now like 3D scanning apps and stuff like this that will take advantage of things like the iPhone LiDAR sensor. So I think this is potentially more doable, because now, like, when people scan, they can actually have a much better sense of what that reconstruction is going to look like in the end. Whereas we had to train people in order to scan with this knowledge of how feature detection and 3D reconstruction would work under the hood. So yeah, I think there's probably a better chance of this now if you can convince people to take more scans with available sort of scanning frameworks.
Yeah. I forgot how it was 5 years. So okay, follow-up question. Sorry, I'm maybe a bit scattered around trying to follow the things. So I have a follow-up question. So you talk about, new technology, the LiDAR in iPhone, etc. And during your talk, you were, seeing as a future direction working with let's say low quality or partial scan. I have the opposite question. Now there is 3D scanner everywhere, and hopefully the quality of these things is gonna go up. Do you see different direction going there, either more accurate data set or different challenges, like you talk about sparsity, different challenges for any of the tasks, if now we have, let's say, same resolution as RGB for depth?
Yeah, I mean, I think it's interesting to see how the sensors have developed over time, in the sense that I think commodity sensors have not nearly gotten as many improvements as we might have all hoped for, let's say, like 10 years ago. And that's probably for a variety of different kinds of reasons. But it is the case that I'm quite happy that there is actually now like depth sensors on phones, and that seems promising in terms of being able to leverage that. I mean, I think the quality of the depth on the iPhone LiDAR is not necessarily better than the quality of depth that we've captured for ScanNet itself. On the other hand, it seems similar enough that a lot of stuff could be potentially transferable, which is quite nice. In terms of developing higher quality sensors and stuff like this on a similar kind of capture device, I think I don't quite have the expertise to know whether that's going to happen in the immediate future, but it would be great if we could actually acquire more accurate geometry. I mean, I think what's particularly interesting with respect to the large vocabulary kind of scenario is that we will see somewhat of the limits of the current ScanNet data set, and to some degree also in the raw data capture, because there's a limited amount of geometric resolution with respect to the data, with respect to the reconstruction itself. And for small objects like, let's say, computer mice, small cups, glasses, forks, and silverware, and this kind of stuff, you will start to see the limits of this joint understanding of RGBD. And so I would be pretty interested to see further developments in that kind of domain, but I hope to push forward with that in terms of this large vocabulary understanding, where I think we actually will need more accurate kind of RGBD. Yeah, cool. I agree with you. 10 years ago, we would expect to have full-blown 3D scan, and instead now we are, I don't know, start seeing them in phones, but the quality it's what it is. Mm-hmm. I'm sorry if I'm monopolizing the conversation here, but I don't see any other question. I have maybe a meta question now. So this is. I work a little bit in generating a data set, and it's an enormous amount of work. And my question is, let's say someone here in the audience, thinks, it would be cool to have a data set. Do you have any advice of what to do, of what not to do, before starting, right? Yeah, I mean, trying to. Maybe that's obvious. I would say trying to map out the feasibility of everything that's being planned is a good thing to estimate. I mean, in the case of ScanNet with real-time reconstructions, at least we weren't going to be bottlenecked by, like, let's say, reconstruction processing time and stuff like this. But it's still like estimating the number of scans that we wanted to acquire. In that case, I think we had a target about 1,000. And estimating the amount of time it takes to capture and to annotate this number of scans, and making sure this was actually feasible within our available technology. I mean, I say that because I think, for instance, a lot of us have thought about, how can we capture, people in 3D scans? And for instance, that one is going to take significantly larger amount of time in terms of data acquisition, in terms of proper annotation. Would be great if somebody could figure out, how to do this at an efficient way at scale. And I mean, one thing that's worth noting, I would say, is like if crowdsourcing the annotations, which is kind of an attractive option because, like, you know, I think there's a lot of stuff that can be done there. The first thing is to make sure that the tasks are all broken down into something as easy as possible, even if it means that you have many annotation tasks in sequence, because otherwise, I mean, if you try to put this out on Mechanical Turk or something else, it's very difficult to get a large set of annotators that can actually, or who are willing to actually do the task at the level of quality that you would like to have. In particular, when we introduce new things or sort of more unusual things like asking people to navigate in a 3D interface, we need to introduce people to how to actually use that. And that's something that we did to some degree here, but it's by far not as easy of a task as, let's say, image classification and just typing in a label. But the goal is to try to break down these tasks into something that's close to as easy as that, and then verify, put in crowdsourced verification tasks. These are much easier for people to say, is that actually reasonable or not? And majority votes are reliable in this kind of sense, or even if the verification step is so easy that you can have just one person go through it for like, you know, a few minutes. This is a necessary thing when crowdsourcing annotations. But that is kind of the interesting aspect, is to, well, I mean, coming out from some of these logistical details than just thinking about, you know, what is the big picture stuff that's missing in terms of data for people to be able to jumpstart new tasks. That's always the exciting thing, I think, about making a data set.
Yeah, I cannot imagine the amount of work behind building, because you build the tool right from scratch, because there was nothing, right, for annotation and crowdsources and everything, right? Like you said, it's not like images, upload them and wait.
Yeah, I mean, so that's something that I mean, mostly Manolis and Angel, I would have to say, on that side, we're spend a lot of effort to build this annotation tool and to make sure that, you know, people understood, in fact, it's a 3D scene. Because of course, you know, like the first things that people might do if they're trying to do the task well is to just annotate everything in the view and nothing else, which is a bit of a problem with a 3D annotation. So we have to develop these kinds of little hints to tell people, in fact, you know, this is a 3D scene, you can navigate around. If you move your mouse left and right, then you can actually rotate the scene, and these kinds of things in order to get people to be familiar with even the data modality itself is, I mean, I would say there's a lot of interesting, let's say, you know, HCI kind of aspect to that is still underexplored, but it's pretty interesting.
And are this tool, you know, the thing you develop available? Let's say someone wanted, you know, to do something similar, or, you know, annotate 3D scene. Is it something that could be used?
Yeah, so the what we used for annotations is fully open sourced in terms of this SSDK, the Smart Scenes Toolkit, and people can try it out, set it up in order to be able to annotate their own reconstructed meshes if they would like, and as well as the rest of the ScanNet processing pipeline, which is, to be fair, slightly non-trivial in terms of getting the whole thing set up, but all of it is available to try out in terms of the entire pipeline.
Cool, thanks. Let me see. I haven't stolen anyone's time. Cool. Well, thanks again for your tutorial, and I want to remind anyone that Angela is going to give a keynote talk during the main SGP. So yeah, if you're interested in her work, please join. And thank you again for your talk.
Thanks for having me.
Okay, so now we'll do a dataset talk now. Since the session is called Dataset and Software, now it's the time to move into software. And our next tutorial is going to be about replicability in computer graphics, and it's going to be a video, and it's going to be given by Nicolas, Julie, another Nicolas, and David. And as always, there's going to be time at the end for some Q&A. So please write your question either on Zoom or the Discord channel.
Hi everyone, this is a joint work with Nicolas Bonil, David Curjoli, Julie Digne, and myself, Nicolas Melato. The findings and recommendations presented in this talk mostly come from the paper Code Replicability in Computer Graphics that has been published at the ACM Transaction on Graphics 2 years ago. If you want to read more on this topic, I recommend you to have a look at this paper. Let's now move on to the main goal of all of this, which is we want to be able to duplicate research results that are presented in published paper. Given a paper, I want to be able to run some code, scripts, or binaries that will allow me to produce results that are representative or similar to those shown in the paper. Some of you may wonder why this is important, right? Duplicating research results has several benefits. First, let's consider the fact that, as researchers, our goal is to discover new knowledge and share it for the greater good, to our community and to the public. Here, duplicating research results helps to validate a given implementation and prototype, so it then can be used by researchers, companies, and public for the relevant use cases. Secondly, it has a strong impact on the research process itself. It helps to further evaluate and validate approaches that have been already published and compare them to ongoing research. Papers are selected by peer review, and it may happen that bugs, bias, or undetected limitations strongly affect the performances or the impact of a method. In order to detect such issues, reading a paper is not always enough. It might require us to run and use the published approach with different settings than those used by the authors. Again, duplicating the original results is mandatory to validate that the detected problems does not appear with the settings used by the original authors. Finally, it has been shown in several research communities that the number of citations of a published paper can be significantly increased when the author shares the code or the binaries used for their experiments. This leads me to the concept of replicable, reproducible, and repeatable research. These concepts can be used to qualify work in any research field, right? In this talk, we'll focus on the specificities of computer graphics and computer science. I guess that some of you may have already heard about these three terms. In fact, depending on who uses them, they might be defined differently. For instance, the Association for Computing Machinery and the National Academy of Science use opposite definitions. So in this talk, we will follow the ACM definitions, such that repeatable research means that the authors can duplicate their own work. We leave this concept for now, as it relates more to the research process itself, rather than to the research outcomes. So we have these two concepts, which qualify if other researchers can duplicate results using either the original artifacts produced by the authors or their own artifacts. Reproducibility is something difficult to evaluate, as it involves both the authors and the other researchers' capabilities. We can say that a paper is reproducible if the author provides all the required implementation details in the paper, The author provides all the required data and other details related to the experimental process. And the other researchers have the technical skills to duplicate the experiments, and they also can reproduce the technical environment for the experiments, both in terms of hardware and software. Imagine, for instance, a small research group willing to replicate the latest large-scale neural network requiring a data center for processing. It will not be possible, whatever the skills of this research group. In this presentation, we will rather focus on the replicability, something that can be evaluated and something that you or any researcher can actually work on. So, as you can understand, replicability is mostly about sharing artifacts that can be used by people to duplicate the research results. Of course, the first thing we think about is code, right? In practice, it's more than the code that needs to be considered. There is also data, pre- and post-processing pipelines, if any, software environments, documentation, among others. When you share artifacts like that, you might keep in mind that anyone might want to use them, whatever their background, if they are students or experimental researchers, engineers, and so on. For instance, the documentation is something critical in order to explain to people what needs to be installed and what are the steps to follow in order to use the code and the data. Without it, it's very unlikely that people will know what to do, and so your paper will not be replicable, even if you share the code. Note that, in some cases, when the intellectual property rules do not allow you to share the code, for instance when companies are involved, the authors can share precompiled binaries. As long as the piece of software can be used properly to duplicate the results, this does not affect the replicability. This may, however, question the evaluation of the contribution and results, as there are some hidden parts. But at least we can elaborate future work on the proposed pipeline. I hope that I convinced you that replicability is something important. You might also be aware that replicability may have a cost. It takes time to produce all these artifacts, and in some situations, let's say I'm staying only 1 year for a postdoc in grad team, it might be tempting to skip this and just go on to the next project. In the second part of this talk, we'll focus on the tools and the guidelines that will make this process easier, both at the individual and the community scale. So, as you remember, this talk is about replicability in computer graphics. It's interesting to know if our research community is involved and aware of the benefits of having replicable research, and if it exists initiative to favorize and recognize replicability. Let's first have a look at the tools and initiatives that favorize replicability at the community scale. We have 4 main categories: publications of artifacts alongside the paper, recognition marks, collaborative platforms, and dedicated publication venues. Note that we will discuss the technical and practical solution later in the talk. A first option is to publish the author artifacts with the paper, as many authors already do on their website page. Recently, the editors started to add the option to store and distribute code as additional material directly in their library. It improves the accessibility of the code over time. We'll come back to this later. Note that in most cases, this artifact publication is optional and based on the author will. Some editors, such as Nature since 2018, now state in their policy that authors are required to make materials, data, code, and so on available to the readers. In our community, the Journal of Computer Graphics Techniques has the same requirements. Another option is to promote papers by recognizing their replicability. You get a board of experts, researchers, who evaluate and acknowledge the fact that a paper is replicable. So awards, such as the SGP dataset and software awards, are given by a committee in charge of identifying and selecting awardees. In contrast, the Replicability Stamp Initiative provides a way for the authors to submit their paper and artifacts. The reviewers evaluate if the code replicates the results shown in the paper. Note that this process, replicability stamp, is included in the publication pipeline of some journals for accepted papers. It allows to save time and also to add the stamp as a metadata of the paper and to promote this information in the journal. A third option is to publish papers where one of the main contributions is that the proposed system or method is reproducible, or is the reproducibility of other works. This might be done in dedicated journals like EPOL, workshops such as RRPR, or tracks as the dataset paper at SGP. In some cases, papers providing useful tools or dataset can also be published in traditional venues such as SIGGRAPH. Finally, it's also possible to delegate the evaluation to the community by using collaborative platforms. Paper with Code is a platform that goes beyond computer graphics with massive use in the artificial intelligence and computer vision research fields. Here, anyone can add a paper and a link to its code, even the authors. In some cases, some users add an evaluation of the reproducibility according to their personal experience. In contrast, replicability.graphics is a platform that we published alongside our SIGGRAPH paper and which allows users to submit the evaluation of the reproducibility of the paper with a lot of details on the process. Version of the code, difficulty encountered, dependency list, the operating system used for the experiments, and so on. After submission, the evaluation is reviewed by a member of the committee and added to the database. A discuss system allows users and authors to comment this evaluation, allowing authors to fix the problem, and users to publish new evaluations superseding the faulty ones. Let's have a quick tour on replicability.graphics. When you land on the website, you get access to a description of the project, the team, and guidelines for contributors. When you go to the data webpage, you got at the top these two bar plots, which gives an overview of several indicators collected in the reviews. For instance, among the papers with code available, you get the number of replicable or partially replicable papers. We currently have 454 reviews so far that can be accessed by the table below. If you want to know how the indicators evolve depending on, let's say, the topic, you can filter the table and get the numbers. Now, if I want to know more about a paper, I can look for it. Let's say, here is the paper page. You got at the top the title, the authors, the venue, and links to the paper, the preprints, the code, and so on. The reviews are below. We have 4 of them for this paper. Note that these 2 here are marked as deprecated. Here you got the information about the review, link to the code, and here you can see the comments. Here we got David, who did the review, and he had several issues that prevented him to run the code. He managed to fix some things, but still couldn't replicate the result. Interestingly, for this paper, we discussed with the first author about the issue and it fixed it. So now we have the updated reviews about the updated code, and as you can see here, we got a replicability score of 5/5. If you want to add your own review, simply click here to access the instructions. As you can see, a review is an entry in a JSON file. So it's very easy actually to add your own review to the system. If you want to add your own review, you just need to add a pull request on our GitHub project. And this pull request, let's have a look at this one. So it contains the JSON entry, and it will be reviewed and merged to the system. The website will be then automatically updated. As you have seen in the video, it may happen that researchers share their code, but people fail to use it, which means that the author took some time to make the code available, but in the end, their paper is not replicable. This might be caused by several reasons. First, you need to provide the material required for the user to download, set up, and run your code, or binary. On our platform, we collected almost 200 papers with code and binary. For almost 25% of them, we couldn't properly configure our system to run the code. In some cases, it might even happen that the download links were broken and we couldn't even download the code or the binary. In the end, we could replicate most of the results found in the papers for only 55% of them. Well, having the paper replicable on one computer is great, but you need a bit more to make it truly replicable. First, you need to add the authorship and licensing information to be sure that authors' contributions are properly acknowledged and that people will be allowed to use the code in any situation. Second, you need to document your code so people can understand it and potentially build upon it. Let's now have a look at the tools and methodologies that can help you to make your paper truly replicable in the long term. Don't see this as a recipe you must follow, but rather as a set of guidelines that needs to be adapted to your specific situation. So let's start by the beginning, the download step. The main goal here is to be sure that the code will be available for years. As many other jobs, researchers might move from one lab to another over years, right? Each time you move, you get a space to host your personal web page that will be destroyed when you leave. So don't use this space to host code. This is also true for the web page of your research group. It might last for a longer time, but still, it might be removed one day. Prefer using dedicated platforms, such as GitHub or GitLab, that you can directly refer on your web page. These platforms are also very important as you gain version control, issue tracking, and many other features that are helpful to build a community around your project, if you wish to. But of course, even GitHub may be offline one day. I know it might look a bit unlikely, but who knows? Things can change over time. In order to be sure that your code will remain available in 50 years or more, you need to consider other tools, such as the Software Heritage Initiative or the GitHub Archive program, which propose a base layer strategy where code is archived at different frequencies with advertised lifespans of 500 years and possibly 10,000 years. Okay, so after fetching your artifacts, the user needs to configure their system. First, they need to install the dependencies, which are all the pieces of software or code that are required to compile or run your code, and so are part of your code base. As shown in our paper, having too many or too large dependencies often complexify the replicability process. Of course, you don't want to reinvent the wheel, right? It's fine to have dependencies, but try to minimize their number and size. Don't link to OpenCV if you only need something to load an image. Also, identify and advertise the version you use for all your dependencies. Think that their API and their behavior can change over time. This is very critical for rapidly evolving environments such as TensorFlow or proprietary languages such as CUDA. Keep in mind that it might be difficult to install old version of this dependency in 5 or 10 years. So try to stick to usual operating system and install dependencies using packages management services such as pip, for instance. Even in the long term, it should be easy to set up a virtual machine to get your code working. You can help users by providing containers, like a Docker for instance, embedding all the required environment. Remember that keeping things simple is always a good option. Minimize user action, rely on automatic configuration and build systems. Also, it's tempting to polish your research prototype and turn it as a library with fancy functionalities. Remember that this might be great for the community, but it also takes time. So you need to find the right balance between your research and the software development activities. Prototypes are often enough for replicability. And I guess this is the most important slide of this talk. Add documentation. Remember that the first time you got a piece of software and someone asked you to make it run, right? It saves a lot of time to have all the information about the requirements, the dependencies, the build instruction at the same place. If people want to use your code, they often need to know who wrote it, how it changed over time, and so on. And of course, documenting your code will help people to understand it and maybe extend it, improve it, and build upon it. Now that the setup is ready, the last step is simply to run the code, scripts, or the precompiled binaries. Again, keep things simple and minimize user actions. Don't expect users to code, right? If your paper proposes a data-driven approach, provide the data, and if possible, the pre-trained models. Don't ask people to train a network for days or weeks just to replicate your work. It takes time, but also, if something wrong happens during the learning process, the users will be stuck at this stage. Similarly, provide all the instructions and scripts to prepare the data. Describe how to run and how to use or interpret the output. Here again, as you see, documentation is the key. People need to know how all these steps need to be followed and to replicate the experiment. You can find several examples in the documentation page of any of the open source projects that we have in our community. Okay, well, before finishing this talk, I would like to add a short note on licensing. Providing a license is mandatory to define what can be done with your artifacts. Without any license, nobody else can copy, distribute, or modify your work. Many licenses exist out there. Some of them are very permissive, and others allow to control reusability. In any case, it's very likely that your research group or the university already has an open source policy defining which license to use. So just ask. Okay, so we have now reached the end of this presentation. In the first part of this talk, we have seen why it is important to favorize replicable research. It has a strong impact on the authors and the paper's visibility. It accelerates the research process by improving reliability and feedbacks. It facilitates the comparison and provides codebase and dataset that can be shared across the community. Remember that students, researchers, companies, and even the general public can benefit from it. Also, remember that releasing code can be a time-consuming task, so try to get good habits. Keep things simple from the start, use tools and libraries when you need them, control the size and the complexity of your code base, and provide data and pre-trained models. And of course, write documentation so people know what to do. Thank you for your attention and for following this talk. We will now start the Q&A session.
Thank you for the talk, and I think both Nicolas and David are online. Yeah. Oh, see. Yes.
Hello.
So there is a question on Discord. Okay, let me start with my question, which I know, and then I'm gonna read. Oh, and there is a question here. I like that. Okay. Yes, there is a thank you. Yeah, really thank you. So let me start with my question while I read the one on Discord, and then I'm gonna ask it. So it's more like a curiosity. I found that it was an impressive work, and you did most of it. I'm curious, did it catch up with the community? Do you see some momentum now, and it's going well, or is still most of you doing the work and adding new stuff?
Okay. So if we look at the website, the last contribution were like 10 months ago or something like that. So yeah, I think we receive a good feedback from the community from this work, clearly, but we failed to. I think we failed to get a proper community starting to evaluate and submit the recommendation for the papers. So yeah, I don't know, David, if you want to add something, but
no. It was. I mean, we tried to set up all the processes or the framework to be able to accept contributions, but yeah, we don't get that much contribution outside of the project team, I would say. So no, it's still valuable for as a long-term information about past papers, past SIGGRAPH papers, and a kind of overview of the replicability of the community at that time. But yeah, no, we don't know exactly. We didn't expect, to be honest, to have that the website would be used by a large part of the community. We don't exactly know what would be the best way to update, or what could be done on the website side to improve that, actually. So it was one experience, and yeah, it's just a what's probably it doesn't match with the way that the researchers want to investigate replicability on papers. But there are alternatives. I mean, it's not that a big deal. There is a replicability stand that is another way to get feedbacks from the community on the replicability. So that's fine.
Yeah, thank you. I think this is a nice follow-up from the question from Sylvia that she asked before. So yeah, I'm going to try to summarize a little bit here. So she's saying that yeah, many of us, when we are students, we have this amazing code and we love it and we like to work on it. I would say not only student, but then at the end we are judged by number of papers, and it's really difficult to justify any large effort put into coding. So the end of the question is, what do you think we can do as a community to change that and try to make code more valuable?
Okay, so if I may, in the SIGGRAPH paper, we discussed about several recommendations for both the authors, but also for the community or for the editors. And one of the recommendations would be to, I mean, there are plenty of different ways to improve the replicability in a large for a community. One way would be to give time to the authors to share their code during the submission pipeline of the paper. So there are strong recommendations that are pretty hard to implement. That would be to expect that all papers come with code. But for plenty of reasons, this is not acceptable as a community, I would say. But there are softer recommendations, like for instance, when you have a deadline, to have like 2 or 3 weeks after the deadline, that you can then to have another deadline for the code just 2 or 3 weeks after the paper deadline, to be able to give time to the authors to clean up their code and share it in a good way. And for Sylvia's question about the what could be done what could be done beside these recommendations, I don't know. I mean, doing nice code and share the code is something that is always valuable for the author of the paper, and but it's really a matter of time. I would say sometimes you have some pressure from your institution, you have some pressure from your advisors sometimes, but it's pretty hard to find time to do a very clean and to share the work that you have done as a code. But on that point, yes, having awards is important. Having a recognition from the community on that software is super important. And as a long term, if you are a student and you want to share papers with code, I mean, it will always be valuable in your when you apply for position in the industry or in the academia. I mean, it's still something that is well recognized by the committees, I would say.
Yeah, thank you. Yeah, Daniela has a really provocative suggestion in which maybe we should switch things around and have now the main publication is the PDF, but maybe since we are at the end, most of the thing we're doing is producing code. Maybe it should be the other way around. Right? The PDF should be the optional thing, and the documentation and the code is the main thing.
Yeah, exactly. At this point, the code is just an artifact of a paper. But yeah, as you say, probably now it's time to shift it a little bit, saying that what's important is the contribution, the code, and the paper is just an artifact of that. That would be nice. I mean, it won't be the answer for all papers and all topics in computer graphics for sure. I mean, we do have very fundamental, very mathematical papers that don't require or don't with less code involved in. But still, yes, just to consider the code as an artifact, as a paper is of some scientific fact, is something that is important.
Yeah, so there is a lot of discussion. I love this how it's happening here. So I'm sorry, I'm dyslexic. I really have a hard time reading names. So Berend is suggesting that together with the award we have, for example, about software or data set, maybe having a best reproducible paper, or maybe something even on your website to incentivize. Yeah, I'm almost there. I'm gonna spend this 2 hours building better documentation to push it to the top. What do you think about that?
Maybe, I mean, maybe it's a good idea to think about solutions that could be shared across different conferences and journals. So you could have platforms like, for instance, you got the replicability stamp, and if it's linked to all the conferences, you know which paper are replicable or not. And if you do the same for the code reviews and the like the thing we did with our website, then that could help people, irrespectively of the fact that it's published as SGP or anywhere else. So I think as a community, maybe we could try to find the platforms we want to promote and then link them to the journals and conferences.
Yeah. And I have, I think, a series of, let's say, more technical questions. So there is some question about, tool. Tool I never heard about before. So like NixOS, NixShell, GUIX, and then in the Discord channel there are also question about what do you do with dependency, etc. Do you have suggestion things?
Yeah, I would say there are plenty of different ways technically to make sure that the dependencies are correctly set up and that the version of the dependencies are correctly set to build the project. But So it's important to have a look, to know that these technical solutions exist and that you can just investigate what is the best one for your paper and for your content. There's no, I'm not sure, I don't think that there is an ultimate solution for that. I mean, we do, even if we evaluated some project for the SIGGRAPH paper, which was based on a very clean Python package, pipe install stuff, etc., etc. But we did have some issues also with this kind of package manager. So there's no good or bad technical solution. I would say that the most important thing, as Nicolas said, is to have something that is well documented for even for the build instructions, in a way that whatever, I mean, having a clean CMake file, having a clean NixOS or pipe or Docker image or Docker script, whatever. I mean, this is something that is still very interesting to have. But yeah, this kind of tools probably won't last forever. So having a documentation aside with the code is something that is the most important thing, I think.
Yeah, and you may have different tools depending on the fact that you're on Windows, Linux, Mac, yeah, maybe sometimes you want to be compatible with all of these, so you need to have a specific solution for that. I mean, yeah, there are many different technical options, and yeah, it depends.
Yeah, so in the Discord channel, there is heavy suggestion about, I'm super scared about repeating that. I'm personally against it, about using browser and, you know, putting everything in the browser with, I think, 3JS and stuff like that. This could be an option, but then they were mentioning about, you know, look what happened with Flash. So let's not go full on browser mode. But yeah, do you, I don't know. I mean, I guess that since you start working on it, you have replicable code. What do you do?
Yeah, I think so. It depends on the topic you're working on. For instance, if you do animation and you want to provide a solution that will be close to what is used in the industry, your solution will be to have a Maya plugin, something like that. And then this, you cannot move that to the browser and get an online demo. It doesn't make sense. Or if you do it, it's another thing you do. So it really depends on the topic. In geometry processing, you already have many libraries that are really nice, that do allow you to load data and display and so on. So what I do and what I try to, so it's just my personal opinion, but what I do is I try to be compatible with these and benefit from this framework to be, so it's easy to use, and my code can be plug and play in these libraries, and that people are used to it, and so they will be able to use my code. I don't want to, maybe sometimes if you go too fancy, it's difficult to use your code. It's like when you do rendering, if you are compatible with Mitsuba, PBRT or something, then you're good.
Yeah, I mean, personally, I don't like that you continue to talk about documentation. It's something I hate doing, but I should do it more. I know, it's a big sin. Yes, sorry, I'm you know, kind of trying to follow. There is a lot. I really like a lot of conversation on the Discord channel. Yeah, talking also about the software heritage initiative. Let me see. There were other questions. I think we're almost running out of time. Yeah, so let's say since I lost track of everything, I'm sorry. There was so much stuff moving. Yeah, this is really cool that there is so much interest by the community. So encouraged to continue the conversation on Discord. Don't use Zoom, because Zoom is gonna die when the seminar is over. So Discord is gonna be there forever. Also for Nicola and David to look on the Discord channel and try to answer or give your opinion about everything. And yeah, for all of us, maybe we should try to contribute more to and do pull requests to replicability.graphics to try to make it move more and offload the effort from the development group.
It could be nice, yeah. If the community is interested, we can adapt our approach and our platform to the needs and what people want to do. So yeah, let us know what's wrong, and if you want to contribute, feel free. Yeah.
Yeah, thanks for the talks and exciting conversation at the end. And now talking about reproducible code, we're going to move to the next talk, which is going to be given by Amir, and it's going to talk about is library software replicable, and this was the SGP 2021 software award. Its work on directional field.
Hi, and thank you for the introduction. So I'm going to share my entire screen. I hope, what's that? Yes, okay, good. I hope you see the presentation. Okay. So I have given variations of this in the past, but this is a little bit more about specific design patterns I use to do this thing in Directional. Okay, I will give, of course, a lot of background for this, but still. So let's begin without further ado. Here is also a link to the Directional library. So what am I talking about when I'm talking about the contested definition of directional fields? Basically, you have some kind of domain, geometric domain, and you have a collection of vectors at each point. That's the definition, the most basic one. It can be either like an image where you have, for instance, these wind patterns, so it's a single vector that marks the flow, or some kind of surface. This is the most well-known example to us geometers, but not to anyone else. So you have some kind of two-manifold, and there's a field which is tangent. It means also orthogonal to the normal. And for it can have like fields that are also symmetric, like a cross field. And there is also something a little bit less known, but more known to us, and that's something that is ambient inside some kind of volumetric domain, usually a bounded domain, and then the field is some kind of orthonormal frame or any other variety. We'll mostly focus on the second one now, that's because that's the one that Directional currently supports the most, as I will show you. Where do we see those? It almost goes without saying, but I will still say a lot of stuff. Okay, we see them everywhere in blood flows, in hair combing, in information fields, magnetism, road congestion analysis. In our more applications, we see those kind of things in the meshing pipelines, where we take a surface, we do some alignment field that is smooth, aligned, nice, maybe curvature aligned, planar or other stuff. We integrate it into a parameterization, and then we take a mesh out of it, either quad or otherwise, like those triangle and hexagonal meshes, and also in 3D. Sometimes we want meshing with an extra function, for instance, a quadrilateral would be planar, or a hexagonal would be planar, or the vector field trace lines that are geodesic on the surface, so you can, for instance, fit them with ribbons. And there's also other applications that use variations on vector fields, such as the design of minimal surfaces where you only know the boundaries, or the design of developable surfaces. And you can take the notion of those vector fields and use other symmetries to also have different kind of designs, also in the realm of field to integration. For instance, here are two things that are kind of complementary. One is less symmetry, using a field that has only two directions that are symmetric, and therefore you can design stripe patterns on surfaces with this field, or fields that have a larger symmetry, more than 4, more than 3, 5, 7, and something like this, that you can design Penrose patterns on surfaces with. Fields are not only used on, of course, surfaces. We can use them in the plane to guide sketching and shape from illustration, or reconstruct from given illustration what the vectorized shape would be, and also use them to guide or analyze, when we get them as input, the results of simulation. For instance, having the wind patterns and correlating them with precipitation patterns, or use them to otherwise do anything that is used in fluid simulation and study the properties like divergence and curve. Fields have been recently, well, everything in learning is kind of recently geometry, used for learning alignment patterns or any other geometric information which is much more well coded in fields on surfaces. And basically that's on really one leg, even one toe, the applications we use them for. So let's discuss a little bit some of the properties that we have for them in the continuum, and how do we represent those properties and use them in the discrete and for which kind of field. So let's discuss a little bit what do we know about fields in the continuum. So I will mainly talk about fields on surfaces, and that means this is only provisionally for now. There is some kind of surface and there is some kind of vector field on it. Okay, you can see it on a discrete surface to the right, and you can already, even if it's a discrete surface, you can follow with your eyes the patterns of the flow, and there is even a nice vortex singularity in the middle. You can see it's also symmetric. The field can have different symmetries, or specifically rotational symmetries, where the field, for instance, does not have sign. That's a 2-rosy field, or to the right, where the field is like a cross, that's a 4 rotational symmetry field. Or they can be totally arbitrary, like just any free vectors on a point. They're expected to be somehow smooth, and then we'll talk about what smooth is. So it means like similar locally. Okay, and then you can design something that looks like this. There's fields that are kind of symmetric in the top, but less symmetric in the bottom, but more aligned to the boundary. So let's be a little bit more formal now. Basically, when we talked about fields that are tangent, okay, so a tangent and directional field is a map between what's called the tangent bundle. That means in every point on the surface, there is assigned a tangent plane. The collection of all those tangent planes is the tangent bundle. So it's the surface with the extra planes. So this is a map between the tangent bundle and basically R3 times n, which means for every n, you have n vectors, you have an R3 vector. Okay. Now, some people will screech at this definition because it's very extrinsic, actually. And I'm sorry, but to make this a short lecture and not like a 2-day course, we'll have to do it this way to make it more understandable. And but of course, there's many other ways to define it in an extremely intrinsic way without coordinates. Okay, since we want a vector field that is tangent, and specifically on surfaces, we have something that is in an ambient R3 space. We have codimension 1, which means the normal to each point is a single vector. Okay, then it means we actually have 2 degrees of freedom for every vector times n vectors. Okay, so every vector is within every point is within a plane, so it can only be parameterized by 2 numbers. The third one is something in the direction of the norm. And I said parameterized. How can we do that? So in every such tangent space, a tangent space is the collection of point and tangent plane, like as an element of the tangent bundle. We can admit local basis vectors, which are also fields on their own. Some basis vector 1 and 2, or x and y. And then every vector can be represented in the true degrees of freedom in this local Cartesian coordinates in this space. It looks like this. You can have many alternatives. First of all, you can have just a complex representation. That's not an alternative. It's just the same thing. It's isomorphic. Just imagine the B1, B2 is a complex plane. We use that a lot, actually. And you can also represent it using a polar by taking the logarithm, the Euler logarithm of this map, and representing it by an angle around it. We'll talk about this briefly later. Okay, so this looks like this, represented by an angle from, for instance, the x-axis and the magnitude. This is all still in the continuum, yes? And now, okay, we talked about each point, what happened in each point, the representation. But to actually do something with a field, we need to have some kind of notion of environment and smoothness and some kind of thing that is, everything is under the umbrella of something called a connection. Specifically, we need to differentiate or compare a vector in 2 points on a surface that are infinitesimally closed. It's usually explained in a very difficult way. I blame Riemann. But there's a very intuitive way to explain this kind of thing. Basically, it's exactly like differentiating just a vector, except you have to take into account the change of basis. So what's called the covariant derivative, if you assume some kind of metric, actually the definition of this connection is the metric. Okay, it basically has 2 components. The derivative of a vector along some kind of direction W, okay, where you move infinitesimally small, is just made out of 2 parts. First of all, literally the derivative, the directional derivative, but there's the extra. And this extra is just accounting for what's called the angular velocity of the basis, how much the basis changed. Because we do that in the 2D coordinates. So in order to compare, we can have to comb the bases to each other to define some kind of notion of parallelity. Okay, that's all to it, basically. So a connection is this definition of J. And when you have this definition of J, you can differentiate between vectors in 2 neighboring points on a surface. Okay. Once you have defined this connection, you can define also parallel transport. It means 2 nearby vectors that have covariant derivative 0. Okay, so the vectors are considered to be parallel. You just transport the vector without any extra rotation with regards to the connection. And now there's a very interesting notion of something called an holonomy. And this is what happens when you take a vector and you transport it, transport along a line, and then you return to the same point. Most often, and in fact, in every case of a surface that is not trivial, the vector will return to the initial point with some angle, as you can see in the right drawing. Okay, and what is this angle? So one very basic notion of vector fields on curved surfaces is that the difference between the angles, this holonomy, is actually just the integration of the curvature this patch has, the inside of the Gaussian curvature, modulo 2 pi, because holonomy does not take into account any full rotation specifically. So you need the patch to be smaller and smaller and smaller if you wanted to converge to the Gaussian curvature that you hold within the patch. And I said it does not account for any full rotation, so let's talk about this specific point. We have a way to measure this, okay? If we have any field, okay, and we look at how it goes around any closed loop, we can count how many rotation it does, which is always integer because any field will return to the same place, okay? This is a field that is not parallel. This is just a vector field. So it means that going from point to point requires some kind of rotation. We're going to talk about it. How many? So we can count those rotations, and this is the index of the field. So for instance, here there's a full rotation. It also relates to the turning number of the field, which is 1. Okay, this is still a full rotation, so this doesn't discriminate between sinks, sources, or vortices. And here there is actually 0 rotations because the field on the integration doesn't rotate. Here there is a -1. Okay, so it rotates backward relating to the direction of the rotation. And so our singularities are places in a field, okay, that have this kind of thing. Usually when you get used to vector field, you can see with your eyes the index. For instance, you can see here that the red points are kind of hyperbolic points where 3 lines meet, and they're minus index. And those blue points, these horseshoes, are +1 indices. What do we know about singularities is that they converge to the Poincaré-Hopf theorem, and that means the sum of all indices is a topological invariant. It's just the Euler characteristic, basically, times 2 pi. Okay, G is the number of generators, and B is the number of boundary loops. And now here is a point I want to tie back and explain a vector field is indeed something that's a different connection. Okay, so when you have a vector field, it's never really a parallel transport. It means you have a given vector at each point, and it's a single vector. And that means 2 vectors, neighboring vectors, cannot in general around the entire mesh be parallel transported. They incur some kind of different angle than the, let's call it original native connection. So the vector field itself induces a connection on this manifold, so with different rotation. And that means that a vector field by itself introduces a new parallelity. A vector field can tell you something like, those two gray vectors are now my new parallel, not the old natural parallel. And that means the vector field will induce by its own a new curvature. And this curvature is literally just the singularities of the field. Okay, because there's only non-trivial rotations where you have singularities. Still, it preserves the total curvature. Now, when we talk about M fields, there's actually nothing more to it. It's exactly like a single vector field, except you're allowed to do, instead of just full rotation, when you go around the cycle, you're allowed to do 1 divided by n rotation, so you can have fractional indices. And it will look like this. For instance, equals 0 is this nice tweed pattern. 1 divided by 4 is like you took out one quad and it looks like a shoulder. And -4 is like when you added a patch. So those are also singularities of quad meshes that will have those same valences. And now we reach the point of the discrete representation, and specifically what we do in directional. Let's talk about first the challenges in the discrete setting. The main challenge, well, the only challenge, is discontinuity. So it means we will have discrete tangent spaces that we'll have to figure out what happens in between, or between them. So first of all, what is even a connection in this setting? You have two distinct tangent spaces. What goes between? If you have several vectors, which vectors go to which other vector? And then how do we interpolate in between? So the new paradigm I use in directional is abstract. It means something of the sort. We don't represent vector fields on necessarily something that is a mesh. We represent them on something that is a discrete tangent bundle. That means there's some kind of graph, which is too manifold, and I will talk about what it means a few slides ahead. A graph of tangent spaces. There is a point, and there is a normal to every point, and a local basis, and there are edges between them. And I represent vectors intrinsically by those two numbers on every tangent space. And I also usually will have some kind of way to convert between extrinsic and intrinsic. Again, assuming those things are 2D and live in a 3D space, but that's not a must. Okay, this pattern is general enough to admit purely intrinsic things. And then what is the connection? I have a function on the edges of this graph. By the way, this graph is represented by something a class I call Cartesian fields. And this graph and this function is the connection, and it just represents the translation between the bases. How to rotate one basis to the other, when if a vector is rotated purely by that basis, it means it's parallel. So this encodes the transformation of the bases, and therefore how to do covariant derivative discretely. Covariant differential, let's call it like this. And next thing we need on our discretization is a notion of matching, which means we have two spaces, several vectors between them, how to make the choice. Okay, first of all, you can always make some kind of choice, but we reduce it to a choice that is always order preserving. That means if you choose this red to the red, then the blue goes to the blue and the green to the green by the same order. And this gives you n possible choices. Which is the best to choose? Well, there's no best, but there's a solution that we're going to be something what they call minimal effort. The minimal effort solution means how do we match those vectors in an order preserving way, such that we have to rotate the list after applying the connection. Luckily, all those options differ from each other by exactly multiples of 2 pi. So there's always a single choice that is between minus pi and pi. And this choice is called principal matching. You can use the principal matching in directional and there's also a tutorial about it that will show you how the principal matching looks between those two vectors. So even if you matched, you need to think about what happens in between in terms of rotation. So there's no one choice, there's many choices. There's the choice to do the smallest rotation, which is what the principal matching wants. And there's the choice to do any other rotation, which can be directly encoded, okay, like a period jump. When we have our Cartesian representation, which is what currently Directional supports, we can only assume the principal one, but the library also supports dictating, like index prescription, that you can prescribe those rotations and get a field that interpolates them. And now I said that it has to be a two-manifold. What does that mean exactly? Because what I told you so far is just a graph of tangent spaces. This could potentially even be in 3D space, just a point cloud in any d-dimensional space. Yes, except now I force it with a new structure. And this structure is a local disk topology that is culminated by the fact that I have those circle topology cycles between those tangent spaces, so tangent space cycles. And those actually are what encodes the holonomy of my, that has to be a surface because it has this topology. What is this holonomy, this Gaussian curvature? Now I worked in reverse. Instead of actually having a Gaussian curvature like something I measured from the surface, I now define Gaussian curvature from R, the connection. So I'm taking the entire connection around any one of my cycles, and the argument of this is my G, the curvature of this cycle. And note that I haven't, this is still not dependent on any faces, vertices, or anything yet. This is very general. Okay, so if I do the parallel transport, then I will have the Gaussian curvature of this. Okay. But if I do have a given field that is not parallel, and that means there is some kind of deviation angles from parallelity, this theta, and this theta is indeed a trivial connection. That means that the sum of thetas around these cycles are like what we had in the continuum. It means that I have an index. First of all, I have to cancel out the curvature because I return to the same vector. And then I'm also counting the number of full rotations, which is the index of this field. Specifically, what you see here as index 0, but I could have also done full rotation around it to have some kind of index. And that's still measurable on this kind of abstract thing, still no faces or vertices. Okay? And then a singularity would indeed have some kind of matching cycle that measures this effort, those theta angles, and I don't return to the same place. And then I can measure the singularity of the cycle. So let's talk about actual concrete representation that have been given in the work. Broadly, at least on meshes, they have been categorized into vertex-based, edge-based, and face-based. Okay, and specifically, currently, Directional caters to some face-based and some vertex-based representations. And let's talk about how it's being done. Face-based field, which was the original one that started from Directional, at least in previous versions, are kind of straightforward. That means the tangent space is a face, the normal to the face. It's very obvious how to encode this kind of thing. The vectors are painted on. And then usually they're piecewise constant, but it's not a must. This continues at edges and vertices. What's particularly good about face-based fields is that their structure preserved, they have an extra structure. What is the extra structure? They kind of have this finite element cochain sequence, if I have to say this nasty word in a way, in which you have a scalar function and what's called a co-scalar function that you are the gradient and co-gradient of with some kind of harmonic field around it. And that's the last I'm going to say about it because it's a relatively short presentation. And this is something that doesn't exist in all other representations, and with a star that I will mention later. Okay, so that's what's extra nice about face-based fields. How do we combine all those abstract properties in face-based fields? So tangent spaces are indeed faces. Adjacency relations are dual edges, that means face minus face. The cycles are then the vertices. And the connection is the representation of the mutual edge when you account for it, basically. That's how it's a little bit like flattening the two faces and then combing the base until it's the same and then comparing. Okay. Consequently, Gaussian curvature is just angle defect, which is very comfortable because you have an expression for it that you can measure. Varix-based fields are also another very popular alternative. Their common flavor usually is when they're done intrinsically, instead of an obviously flat face like a face, what you do is use some kind of you use the vertex and it's wandering as a cone, and you parameterized the one ring as the tangent space on that cone. Okay, and that kind of means you work in a logarithm map. That means you kind of when we have to measure curvature of this, the curvature does not exist anymore in the vertex in this setting per se, because when we parallel transport, we do it from vertex to vertex to vertex, and it kind of pushes curvature inside faces, as I will also show in the next slide. What is the connection? It's exactly dual to the face space. Basically, two vertices have the same mutual edge. This edge is represented in the faces in different bases, local bases, those logarithmic bases. And then you just use the rotation that maps the representation of an edge in one to the one in the other. So we'll show in the next slide. They're very nice. They also have some guarantees because vertex-based functions are usually much nicer behaving than the face-based functions. And they allow for second-order pointwise operators. The biggest minus is that so far, and it's probably because of when you count degrees of freedom, it's not very likely, they don't have this nice structure presented. You don't have like a scalar function for which they are gradients or something like this. So concretely, when I implemented them to do Varix field, tangent spaces are intrinsic on this one ring with this logarithm map around the vertex. Cycles are on faces, therefore, and the connection is, again, the mutual edge. Gaussian curvature, it's not obvious to measure, in terms of just geometry. Instead, I measured it by the counting for how parallel transport deviates. Okay, so it's induced by the connection. On every triangle, you can simply count all those things. I don't know if there's a closed form for it, honestly. I tried to look it up. It's definitely local, and it definitely relates to the Gaussian curvature of the vertices around, but I don't know exactly how. Okay. At this point, I also want to show you this. Let's go to this. You see the demo, right? Someone say with voice, please, if they don't. Okay, so this is exactly, since I abstractify Cartesian field, I used some kind of algorithm to do small bits between them in exactly the same code for face-based or vertices. So you can see concretely, this is a face-based field. You see there's a vector in the face, it's actually a 2 rosy, and the singularities are obvious on the vertices. Whereas this is a vertex-based field with similar constraints. Okay, they look very much the same if you look far away enough, and the singularities are discovered on the faces. Okay. Let's resume. Okay. Now, I'll put a little 2 stars in it. There's also very new and actually a very nice representation that's called edge-based fields with non-conforming spaces, like Cruzia-Ravier, I probably didn't say it right, phases, where there's an intrinsic vector on every edge, and it's interpolated piecewise linearly to the inside. In fact, this still has all those definitions of connection, so, very near future work to implement this with Cartesian field. Now, another star I put in is that before this representation, edge-based field used to refer to differential forms integrated in on edges and the entire deck thing. This is a whole different opera. Okay, so this is a whole new different representations of vector fields with which I didn't touch, and we require different interface. In fact, this is still very near future work for directional. I have it implemented, but not so far, not very codified, and this also transcends much better into higher dimensions. So it's very useful, differential forms, but this is not what this talk is specifically about. Okay. Then let's talk now a little bit about representation, which is distinct from discretization. So you can choose a discretization face, vertex, or edge, and on top of which you can represent the field in different ways. One of them is a single vector field, okay, that either has a Cartesian representation as a raw field, just xy, or intrinsically an xyz on every point. Okay, and something that is also a little bit future work, a direct polar representation just by angle and rotation and magnitude. Okay, so one can also represent this field as unit fields. It's less simple in Cartesian representation. It's just a flag for here, where in polar it's much simpler. For n directionals, the raw field representation is literally just represented a lot of xy's, okay, but it doesn't carry symmetry. So for symmetries, there's different types of representation, also in directional. For symmetric fields, which are n-rosy fields, either cross fields, 5 fields, 2 fields, or whatever, there's 2 ways to do it. One of them is just have a single representative. This is something I used to have. It's a little bit legacy in directional, which is just one of the roots, and then the other routes are defined by rotations. Or, and this is something that is more popular in recent years, since you have a Cartesian representation xy of all the roots, which you can take also in complex numbers. Instead, what you represent is a whole new number, a whole new vector in every face, which encodes all the roots in the same time. So if an xy is some kind of cosine phi, sine phi for some angle, it's a cosine of n, of n times this, and that's called a power field. Why is it called a power field? Because if the field, Cartesian field, is represented by a complex number, if you take it to the power of n, then all the square roots of n imply all those possibilities. So that's, this power field is also an option in direction. What happens if it's non-symmetric in general? So what we usually want is to be order preserving, but not care about the specific ordering of those roots, not encode them. We have to figure them out by principal matching. Okay, so we want to have a map that it means those two are the same, although they're differently ordered. So for this, we use another representation over the 8 years ago, SGP, that basically, instead of representing a field using just taking one of the roots to the power of n, we represent the field using a polynomial, where all those vectors are the roots of the polynomials as complex numbers. So our representation is actually the coefficients of those polynomials. This a plus b plus c, ab plus a, c plus b, c, and so forth. Okay, this is our representation, and that's called an n polyvector. And this is used as polyvector field in directional. And also note, this can be used on Varix-based field, phase-based field, and anything else naturally, because everything that this only needs is just a connection. Okay, a connection and a local basis. Okay, so when we use complex numbers and we have complex polynomials, then we represent the field using the coefficients of the polynomials, which roots are the field we want. Okay. When the field, in fact, power vectors are represented as a subset of polyvectors, since a power vector is a polynomial where all the coefficients except the last one, the one that is free, are 0. Okay, that's exactly the multiplication of all roots, which is the power vector. Now, the other asterisk I want to put here is that there are other alternatives for representation, also future work. They're more future work because they're less obvious how to do them in a way that is kind of the paradigm of a discrete tangent space with a vector on the tangent space and connection between them. So this requires like another type of interface, like DEC, that directional could support in the future. Hopefully, it will also help with some people from the community. Okay, now let's talk a little bit about design in the time we have. So I told you how to represent and how to discretize, 2 different things. And now the question is, what do we actually want to achieve? So the first thing we usually want to achieve, like the underlying bread of this sandwich when we want to have a field, is fairness. We usually want a field that is smooth as possible underneath all other constraints we want, okay, which is either compare the rotation angles in some kind of angle-based approach, or for instance, if this field is a power is a Cartesian field that is a power field, have this representative be as equal as possible. How do we do that? When we want something to be as smooth as possible, that means usually we want to minimize its Dirichlet energy. How do we measure the Dirichlet energy? By using the connection, which means we take this covariant derivative. In the discrete version, we say in 2 tangent spaces nearby, and here again I go to the abstraction. Okay, we have 3 components. First of them is a metric, like a stiffness. That's also something that is given to you by the specific implementation of Cartesian field. Then there is the connection. It's also a property that you needed. And basically, you're solving a system in which there's an energy VI wants to be like VJ as much as possible, given the connection. This is a Dirichlet energy, and therefore it means it's implemented by a discrete connection location, which is defined by the connection and the stiffness. For instance, here an example in power fields, we use an n-rosy pair. We have some set of constraint faces. We take the power of the vector we want to have, minimize this Dirichlet energy with one twist. That since we have a power vector, we need the connection in the power of n. So it's like we're measuring the smoothness of every vector individually. Let me briefly show you how it looks like. Okay. So this is like this. You can have a vector here and what I did around. And here I will try to make it a little bit worse off. Okay, and the rest are interpolated by minimizing the Dirichlet energy. Okay. Play this back. This is, in terms of directional, very simple. After you chose a discretization that is a Cartesian field, you implemented everything that you need in this interface Cartesian field. You can call power fields and power to raw and then principal matching to show the raw fields. In fact, this is what you saw in the demonstration of Varix-Based Field. I literally called power fields on both and just replaced the class Cartesian field with a vertex of phase. So when you implement an autopolar class, you can enjoy those algorithms directly, since I said directional separated now discretization and representation. Okay. Polyvector fields are very much the same, except that instead of just a single power vector, we compare all the coefficients in the specific connection that we need. But again, the only thing you need is what are the tangent spaces and what are the connection between them. And if you implemented such a class like a vertex field or phase-space field, you can go and have yourself a polyvector algorithm. Okay, and use polyvector field, feed some kind of Cartesian field, and polyvector to raw. Let's also see a very short example. What's nice about polyvectors is that because they're non-orthogonal, they can cater to this. So I didn't go specific, but one can have either soft or hard constraints. So for instance, when you have, these are the constraints, and you can see here in this corner, it's very non-orthogonal. When you use hard constraints, it looks like this. Okay, so it gives up orthogonality a little bit to make this happen. When you use soft constraints, which are very soft, you get something that is more orthogonal and doesn't exactly interpolate the constraints, sort of, except in very hard places like this. So you can play with it in direction. Okay, we're advancing well. And this is a little bit something different that is used to create a field, which is index prescription. That goes kind of the other way around. Instead of trying to find a field with constraints, what you do is basically input where are the singularities instead of finding them out. So it's kind of an opposite problem. You put singularities in specific places. Again, since it's supposedly accept Cartesian field, if it's a vertex, you put singularities in faces, and the other way around. And you still solve for a Dirichlet energy, but it's on the rotation angles, providing that you interpolate the curvature you were after. That's also a popular algorithm called trivial connection. Okay, and there's variations of this. So let me show you also a small demo, and we're almost done. Okay, so this is specifically on phase-based field, but it doesn't matter. I can put a singularity here, increase the index like 3 times. Now it's bad because I put too much index. I have to counter it. So let me counter it. Now I counter it. Now I have a huge index here and a small, well, a huge index just opposite here. And of course, I can also do that for generator cycles, which are independent. So I can increase the rotation around handles. Okay. Yes, we're almost done. Okay, we'll just, because of lack of a little bit of time, let me jump a little bit ahead. Okay, yes. Okay, so let's talk a little bit about constraints, what we usually want. A constraint that I already showed you is alignment. That means we want to put some vectors in some phase and have the field aligned to them. Directional allows you partial alignment. That means you can put any number of vectors you want in the face and we'll try to accommodate them. If you want perfect alignment and you didn't put too many vectors, that's all in the power field and the vector field algorithm, then you will interpolate them. There's also, in conjugate frame fields, you can have other geometry style constraints. For instance, that the two vectors in your tangent space, they zero out the second fundamental form. Basically, it means that they locally generate an infinitesimal planar quad, which is used to do planar quad meshing. Another constraint, this currently only works on face-based fields because Varix-based fields don't have this kind of thing, is being structure preserving. That means we compute a field that if it's the gradient of another field, then it has curve free, or if it's a co-gradient of another field, it has divergence. This is used by mixing conforming and non-conforming elements. Where do we use it? We use it to compute fields that are integrable. Integrable means we compute a to be curve-free, and therefore they have zero error. If a field is not integrable and you're trying to integrate it with some kind of scalar function, you get unbounded error, okay, or even flip overs. But if it's integrable, is what you see is what you get. You get perfect alignment. Okay, how do we do that? If you want to integrate, this is only for face-based field, yes, into a piecewise linear function. When a piecewise linear function is a gradient, it means it's curve-free. That means its tangent agrees on the edge. Okay, and in fact, it's also the other way around. If in a simply connected surface, the tangent agree on the edge, then it's curve-free, then it's integrable to a scalar function. Then what we compute are fields that are curve-free. Except there's a twist. We do it under something called a Kerr matching. So the field is curve-free when you match two vectors, and those two vectors are curve-free independently, pairwise. That was the word I'm looking for. When you have a curve-free field, that means you can integrate it into a UV parameterization, which has some kind of symmetry, which is seamless. And then you can integrate this into a seamless function, which you can dress up with texture. So this is also something you can do with directional using integrate. You just feed the field, currently again only face-based, and it integrates it into a seamless function. Okay, that's defined on the corner with some kind of transition function that you see here in the middle. And you can also add integer rounding to get to fully seamless. There's also another component where directional traces those things actually across triangles, even in different orders, so you can take those parameterization and you can mesh them. What you see in the right is an actual a mesh lab picture of a mesh. That's basically it. I just want to talk about some stuff that are like future challenges in brief because I'm out of time. So all of this basically says that we have kind of a nice graph with all the connection nodes and so forth, but of course we know that now there is stuff in the wild and we don't have an answer for it. Meshes are self-intersecting, nodes are not well aligned, not watertight, okay? Most existing algorithms will just fail. We don't know those connections. Okay, so there's interesting directions on maybe working out envelopes and fields in those envelopes. A very interesting paper from 2 years ago of Tufted Covers, also working on something that is specifically non-manifold with fields, maybe working on level sets. It's a little unclear. And also something else, a challenge, is big geometric data. All the things I showed you before mostly solve linear systems. And they try to get a very smooth mesh, it's very smooth field on a very, very big object. And that seems like a little bit of a waste. So what is nice to do is, instead of solving those sparse huge linear system, is maybe working in some kind of multi-grid way to simplify fields back and forth. And here are some references for some resources that are not mine specifically, of directional field processing sources. This excellent survey by De Gressado. Geometry Central is also a library that has a lot of directional fields components. And Digital and Comida also have things that pertain to parameterization, things of the sort. Digital also has, if I remember correctly, a very big deck component, which is something that is not easy to find in existing open source stuff. That's it, basically. So thank you.
Thank you, Amir, for the really nice talk and introduction. Introduction on directional field. I learned a lot of things. I think we are really out of time, so I would suggest if you have questions. In fact, I saw a question on Discord to move the whole conversation on Discord and move to the directly to the last tutorial of this section. And yeah, the session was titled Dataset and Software. This is a little bit different. So this talk is going to be given by Sylvia, and she's going to be talking about Blender for academic paper. I'm super excited about this talk, and this is something I wish I would know when I started my PhD. And yeah, let's start immediately since we're already late.
Hi everyone, I'm Sylvia. I'm a PhD student at the University of Toronto, and welcome to my Blender tutorial. Blender is a free and open source computer graphics software, which includes a massive amount of functionality. And it's, I think, one of the greatest successes of the open software concept that I can think of. But because of that, it can also be a little overwhelming to start with. And if you just Google like Blender tutorials or how to learn Blender, you're probably going to find a lot of great resources, but that are not aimed at the academic use case. They're aimed at, for example, if you're an aspiring artist and you want to learn to do 3D modeling or 3D animation or things like that. So they go in much more detail than what you need to make a figure for your paper. And if that's something that you want to do and you want to learn, great, go for it. It's an amazing hobby and it's really fun. But if it's 3 days from the SIGGRAPH deadline, you don't have the time to go through 20 hours of video on how to model a donut. And that's the kind of audience that this tutorial is for. Finally, this is going to be an absolute beginner tutorial, so I will take it very easy and explain everything that I am doing so that if you have no experience with Blender, you can open it and follow along with me. If instead of this, you're looking for a quick step-by-step reference, you can go to bit.ly/blender-guide, and you can find my step-by-step guide that you can just follow and get it done with. Okay, so let's jump in. Let's assume my setup is like this. I wrote my algorithm in C++ or MATLAB, and my algorithm outputs this geometry that I call myshape.obj. And I want to render it to make a nice paper figure to showcase my method. So let's open Blender. To start, let's click somewhere to get rid of this annoying window in the middle. So click anywhere. And the first thing we're going to do is actually going to be the most critical. So try and follow me here. Because as we open it, we can see this slightly overwhelming user interface. And we're actually going to select one option, change one option in the default of Blender that will help us navigate the user interface without having to remember a lot of key bindings or where each specific button is. So we're going to go to Edit and then Preferences. And then in this sidebar on the left, let's go to Key Map. And here in the middle, we see that there's the second option is Spacebar Action. So what you're going to do is you're going to click on Search. So make sure that this is set to Search. That's all. I'm going to show you what that does in a minute. Okay, so now we can start by moving around in the viewer. In my laptop, I rotate by dragging with 2 fingers, and then I use Shift and Command plus the same dragging motion to rotate, pan, and zoom. So it'll look something like this. It's rotating. Clicking Shift lets me pan the camera, and pressing Command lets me zoom in and out. So those are the controls in my laptop. If you're using a mouse, it's probably more intuitive than that, or if you're using a different laptop. But these controls are something you can look up, and they're usually very intuitive. So let's begin. The first thing we're going to do is we're going to remove this default cube that we have here. And we're going to do that by selecting the cube. So if I'm selected somewhere else, I'm going to click on the cube, left click on the cube, press X, and then Enter for delete. Good. So now we have an empty scene. let's import our geometry. To do that, we're going to go to File, Import, OBJ, which is the format that my geometry is in, navigate to where that shape is, and press Enter to import it. Yay! So now we can see it in the Blender viewer, and we can use we can click on it and use these controls on the right that says location, rotation, and scale to move it around. So if I want to move it around in the x-axis, I'll change this value. If I want to move it around in the y-axis, I'll change this value. And in the z-axis like this. But it often is useful to just make the z-axis 0 so that it's standing on the ground at level 0. And similarly, we could rotate it. This is useful if the shape, for example, comes facing up, so like standing on the ground and you want to make it upright, you rotate with respect to the x-axis usually. And that's it. We have the shape in the middle of our scene. Now, to make a pretty picture of our geometry, we need to render it, which is just a fancy way of saying we're going to simulate what it would be like to take a photograph of it. And the process from here on, something I actually find really interesting, is that it mimics a lot the process of setting up a picture of something in the real world. And of course, if you want to take a picture of something, the first thing you need is a camera. So let's set up a camera. The easiest way there are many ways of doing this in Blender. The easiest way to do this is just to pan around in the viewer. So I'm just gonna look at my shape, trying to find the nicest angle. So I think this one's actually pretty good. And I'm going to, and now we're going to use the option that we changed before. So press spacebar, and there should be sort of like a text field that appears, a search field. And in this search field, we're going to type align camera to view, meaning we're going to add a camera that is looking through the same view that we're currently looking at. So let's type that, align active camera to view. You see there that there's some sort of shortcut that's like Option plus Command plus numpad 0. These are the sort of things that you're going to find if you try to Google for this. But being able to use the spacebar as a search field will mean that any option that we don't know the key binding for, we can just type it out. And we're going to do it a lot through this tutorial. Okay, so let's press Enter. And a camera will appear that is looking at the shape. So we'll see like this sort of frame appear that's showing what the picture would look like, or rather like the region that would appear in the picture. Now that looks like it's slightly too down for me. Like I want it to be looking it's usually good that the object is in the middle of the frame. So the way I'm going to move my camera is by clicking on the camera in the top right here. And I'm just going to move it like it's any other object. So I'm going to move the Z location, move it up slightly, and get something like this. Okay, so now I can zoom in. And this is sort of what the, whoops, sorry. Okay, so there I moved away from the camera because I accidentally rotated away from it. That's fine. All we need to do is to click on this camera symbol on the top right here. And we're going to go back to the camera view. Okay, so I think that's a pretty good angle, and we have a camera. Now, what we're looking at right now, it is the part of the scene that is going to be in the camera frame, but it isn't actually simulating a picture. This is actually the Blender geometry preview that isn't actually simulating how light would hit the shape and how it would reflect and what material the shape would have. It's just doing a very simplified, very fast rendering to show us the geometry of the shape. This is what Render calls the solid shading. It's very useful for modeling or when you're setting up the scene because it's very fast and light to use. But what we want to do is to see what the picture would look like. So for that, we're going to move away from the solid shading to the render shading. And again, we could learn exactly what the key binding is or where this is on the shape, but I'm just going to do spacebar and render. And there you go, that's shading rendered. So we're going to click on that one. And something like this will appear. It'll take a little bit in my computer because it's I'm recording the screen at the same time, so this is the slowest I've seen my Blender work ever. So okay, this starts to look more like a picture. At least there are shadows, and there seems to be like a light coming from the right. So it's more physically based, let's say. Now, one quick thing that is a little interesting is that if I move around, and you can try it in your computer, if you move around, you see that the shadow actually changes position slightly when you move around. Now that shouldn't happen, right? The shadow only depends on the geometry of the object and where the light is. It shouldn't depend on where my viewpoint is. Now that's because Blender currently, by default, is not doing physically based rendering. It's not simulating actually how this would look like if it was hit by a light in the real world. It's instead doing a very fancy approximation that's extremely fast, but we don't care about it being super fast. We're happy to wait 1 minute for our picture. So we're going to change the rendering engine to a physically based one. So go back to the camera view. To change the rendering engine, we're going to go to the render properties, which is this sort of icon here that's sort of like the front side, the back side of a digital camera. And we're going to change the render engine from Eevee, which is this really fast approximate engine, to Cycles, which is a physically based ray tracing engine. And there you go. Then the engine will change, and you'll see that the picture starts to look super grainy, and depending on what graphics card you have, either very slowly or very quickly, converging into something that looks a little bit smooth. This is because now the engine is actually tracing many light rays to simulate how they would interact with the scene, which is computationally much more expensive, but with a little time and enough samples, it converges to a much nicer picture. Now, something that didn't used to happen in previous Blender version, that's kind of a gotcha if you are starting out, is that by default, this rendering engine is going to do many, many more samples than are necessary. So let's change that now so that we remember to a more reasonable number of samples. So if we go to the render properties, just where we changed the render engine, and we go down to the sampling dropdown, we see that we have a viewport section and a render section. This just means how is it rendering it for us right now in the viewport, so like in this preview, and how is it rendering it when we actually click render and produce a PNG image. So let's change the viewport one to a reasonable amount. A reasonable amount is 30, for example. And let's change the render maximum samples to another reasonable amount, which let's say it's 50. Now, if you're actually doing this for a SIGGRAPH or SGP paper, you might want to make those 200 or even 500 if it's a very complicated scene. But anything more than 500, I think, is usually wasting time. Okay, so that being done, let's now look at the render preview. What is wrong with this image? Well, many things. This doesn't look like a SIGGRAPH figure just yet. One of the reasons is that this object looks like it's made out of chalk, right? It has like this gray feeling to it. That's the material. That's Blender's default material, and it has this like chalky vibe. And it's default because we haven't picked a material for our object yet. So let's do just that. Now, designing material in Blender is a super interesting thing to do, and you can find many tutorials online depending if you want to make it look photorealistic or to have specific properties or to look like some material that you took a picture of in the real world, or you have specific colors and all of that. But for a paper figure, we don't need to learn photorealistic material creation, and we probably don't have the time for all of that. So instead, what you want is a material that's aesthetically pleasing, that isn't too reflective, but that it has some reflection so that you can distinguish the geometry, and hopefully that it has colors that are, different color options that vary enough for each other so that you can have a figure where you compare different algorithms. So for example, you have the input in one color and then your algorithm in another color and someone else's algorithm in another color. So that's really all you need if you want to make a paper figure. So I made a bunch of materials that do just that. All you need to go is to go to bit.ly/Blender guide. So let's do it together. See if it works. bit.ly/Blender-guide. And you'll reach my website and scroll to step number 0, and you can download my Blender template file. Okay, so I already have it, so I'm not going to download it, but you can do it in your computer. And that template file includes many materials that I designed so that you can use them in your paper figure without really needing to understand how Blender materials work. So let's use them. We don't actually need to open that template file. Instead, what we're going to do is we're going to sort of grab them and move them into our project, our current project. In Blender, that's called appending. So let's go to File, Append, and now let's navigate to my template. So that would be Downloads for me. So we're going to enter the template file. So let's double click there. Then go to Material. And here we have a list of materials. Oops. We have a list of materials. So let's select all of them. And let's click Append. Now nothing has changed because we haven't assigned those materials to anything, but now those materials are loaded into our project. So all we need to do is select our object, like this, and go to Material Properties, which is this icon, this sort of like red and black icon in the bottom right of the UI. Just that. There's going to be like a lot of numbers, a lot of things in the interface. Let's not look at them. Don't look at them. All you need to do is click this black and white sphere, sort of the same icon, but now in black and white, and select one of the many materials that we just appended. Now, one that I like that you'll see in many of my papers is the soft green one. It looks something like this. But for this shape, I actually like the yellow better, so I'm going to pick the hard yellow one. These are all colors taken from Dr. Cynthia Brewer, so that they do like a nice qualitative color map, so that you can have like different objects with different colors, and they're like well separated and distinguished from one another. Okay, so we finally have a material. Now at this point, this is usually a nice point to look at what our final rendered image, so our final like PNG that we would paste into the paper would look like. And again, we could try and search for this in the UI, but why do that if we can just press spacebar and render image? Okay, so let's click on that. And now, before I click, I'll tell you that's going to take a little bit for me, especially because I'm recording the screen at the same time, so my computer is working overtime right now, and also recording my own video and audio. So I'm just going to fast forward in time for a little bit. But for you, it should take a few minutes depending on what your graphics card is. And we're done. That looks pretty nice, doesn't it? I like it at least. So here's a rendering. Now, what are some things that we can easily improve about this? Well, one thing that you'll notice if you look closely at some really nice SGP or SIGGRAPH papers is that objects are usually not floating in space. Instead, they're like laying on a ground on which they're casting a shadow. And that really adds a lot of, I don't know, I think it's very aesthetic to see the ground shadow. It also helps visualize the geometry. So overall, it's a nice thing to do. So let's set a ground plane on which this shape can cast a shadow. So by the way, you can save your rendering, go into image and save as. But I'm not going to render it because I think we're going to improve it. So let's add a ground plane. We could remember what the shortcut for adding a plane is, but again, why not just use spacebar, add plane. There you go. So enter it, and we added a plane. Now that's a very, very tiny plane. So we're going to need to make it bigger. By the way, as a side note, if your computer is busy with other things, you have a bunch of YouTube videos playing on the background like I usually do, it may start to struggle because we're still in the rendering preview. So it might be struggling for you. If that happens at all, you can always go back to the solid shading that we were using before, by doing spacebar and solid shading. And we're back here, and it should work fairly fast at this point. Okay, so we have our plane that was too small. So the way we're going to make it bigger is by going to the object property. So clicking on the plane, going to this sort of orange square-ish thing on the sidebar. And we're back to our familiar location, rotation, scale panel. We're obviously just going to scale it in the X and Y coordinates so that it's bigger. I'm just going to make it, for example, 20. So it's a really big round plane. I don't have to worry about the shadow ending abruptly. So that's our ground plane. One thing that I recommend you do, this kind of like a trick of the trade that I've learned, is that once you move or scale something, it's good practice to apply that scaling. So right now, the way Blender is internally showing us this preview is it's thinking, okay, there's a plane. The plane is a 1x1 square, and then I have to scale it. Instead, we're going to tell Blender, no, start by looking at a 20x20 plane. Don't pretend, don't do that scaling step in the middle. And this is a bit nuanced, but it'll help you, if you don't do it, somewhere down the road, you'll find a bug that fails just because you didn't apply the scaling. So it's good practice that every time you do this, you do spacebar and apply all transforms. That's it. And click that, and now you'll see that the scale went to 1, because now this is a 20x20 plane. That's not scale. It's just a fixed geometry. Okay, good. So let's go back to our render preview to see what the shadow looks like. And I'm going to click on the camera thing so that we see it from the angle that we care about. Okay, that's for sure a shadow. That starts to look nicer. So another thing that we can notice if we look at SIGGRAPH papers or SGP papers is that you usually can't actually see the ground. All that you see is the shadow that's cast by the object. Now, this is, of course, not physical, right? If you see a shadow, then you should also see the ground that the shadow is being cast on. So it's a bit strange to think about, but it looks good when you put it on a white background, because it's kind of like the background is the ground in a way. So it looks aesthetically pleasing, even if it's not, it doesn't have any physical meaning. Fortunately, Blender lets us do just that. Of course, it's like we're taking a picture, but we can play tricks on it because this is a computer. It's not a real camera. So what we're going to do is we're going to click on the ground plane. We're going to go to Object Properties. Then let's scroll down to Visibility, which is one of these drop downs. Click on it. And then go to Mask and click on Shadow Catcher. Now, this is not something you would find in the UI by yourself. You can find it by Googling, but anyway, you just need to know that it's here. Let's click on Shadow Catcher. And now the ground is only going to be rendered through the shadow that it casts. So it won't reflect any light. It won't directly or indirectly. So it will have no effect on the picture except for the shadow. So we'll only see our object and the shadow it casts. Still, this image, if we render it right now, it will have a fully white or a fully black background, which we generally don't like because we want to be able to paste it into our paper, composite it with other pictures. So another thing we're going to do right now to get that really like transparent, only the object and the ground feel is go to Render Properties, then scroll down to, let me compress this, scroll down to Film, and click on Transparent. Okay, so now if we render it, let's go to Render Image and wait a little bit again. Great, we have our rendered image, and we can see that all that we see in the image, we don't see the ground at all. All we see is the object and its shadow. And the rest is transparent. So this checkerboard pattern is Blender's way of telling us there's nothing here. It's fully transparent. So this is the kind of image that we want if we're gonna like later composite it into a paper figure. So good. Again, we could save it by going to image, save as, but I still don't like this rendering, and because this ground with the shadow, it's like all it has done is highlight the one other thing that's wrong with this, which is that the lighting is pretty bad. It's kind of like it has like very direct, like noon sunlight hitting it from the side, which can be poetic, can be nice. If we're being artistic, I like this figure. But if what we want to do is show the geometry of the object, we usually don't want half of it to be almost pitch black, right? We want it to have some balanced lighting that shows all the parts of the object so that we communicate our research well. So let's set up lighting. And again, this is an incredibly complex topic, how to set up lighting for a picture. If you know anyone who has done photography, you know this is extremely hard, and that's why there are photography studios with lights set up and all of that. And if you Google setting up lights in Blender, studio lights in Blender, you can find massive tutorials that teach you how to set up lights, and they usually end up having like a bunch of very strategically placed reflective panels and all of that. And you could do that. If that's something that interests you, go for it. It sounds really fun. But again, for the I just want to make a picture of this and put it in my paper use case, there's actually a much simpler way that I discovered that you can get good lighting. So this is slightly elaborate, but you only need to do it once. So what we're going to do is we're going to find the folder where Blender is. So we're going to find Blender in our computer. For me, I think that would be in applications, maybe. Yeah, there you go. I have several versions of Blender. That doesn't matter. So let's enter this. Let's look at the files of the application. This will depend on your operating system. For me, it's show package content. So let's go in, and then let's go to contents, and then your operating system. Oh, sorry. Then resources, then your version number, then data files, then studio lights, and then world. Okay, let's copy this world folder to somewhere that's more accessible in your computer. So for example, I'm going to copy it to our SGP course folder. This world folder contains the default Blender lighting setups that it will use. So these are all relatively good lighting setups that Blender Blender has much smarter people that know a lot more about lighting, and they've all decided that these are good. These are properly set up, they're good enough, they're balanced enough, they work for different purposes, and they're very diverse, so you can try different ones. So why would we claim to do anything better than Blender if we can just use these? So to use them, we're going to need to do a few slightly complicated steps. We're going to go to this sort of like clockwork or like clock-like icon in the bottom left, and let's click on Shader Editor. Then we're going to click on this place where it says Object and choose World. Okay, and let's drag this open. You may have to click on Use Nodes here for anything to appear. So click on Use Nodes, make sure that's checked. And we should see two nodes that look something like this. Let's zoom in, something like that. We're going to add, all we're going to do is we're going to add a new node and connect it to these. Again, you don't need to understand what's happening. Just do as I say and everything will be okay. So to add a new node, I'm just going to, again, do spacebar and then environment texture. So that's the name of the thing that we're going to add, environment texture. And let's put it here. So let's left click to set it up. And let's open and go to our world folder and choose one of these. Now, I like the forest one because it's like very balanced. It's not very sharp, but you can feel free to try others. So forest. And now let's, this is important, drag the output of this node to the input of this node. So that will apply this forest environment lighting But we still have the default Blender light, which was a sun. So we're going to actually click on the light on the right panel here and press X to delete it. Good. So now we have our shape with proper lighting. And you can already see even in the preview that there isn't this massive sharp shadow that we had before. It seems much more balanced. We can see all the parts of the shape. So this is starting to look pretty good. So let's render it and see what happens. And there we go, a beautiful figure that we could paste into our next SGP or SIGGRAPH paper. Now this has been a very basic tutorial. If you enjoyed it, you can find more information as well as slightly more advanced tricks and resources from other people that go into depth into some other topics, even learning how to do this all as with scripts, as my lab mate Derek Liu has a toolbox for. You can find all of that at bit.ly/blender-guide. And I hope you enjoyed this and enjoy SGP. Hi everyone, I'm Sylvia. I'm a PhD.
Thank you. Thank you for this really nice crash course. And there was a lot of discussion on Discord, and I joined the list of people say I wish I would know this before. Yeah, it's super useful. And let me see. So there was some question and discussion about rendering point cloud. Do you have any experience with that? Do you know anything about it?
Yeah, point clouds is one of the things that's very badly handled natively by Blender, precisely because they're not thinking of like, oh, maybe the user is a geometry processing researcher that wants to show a point cloud, right? Like the use case for point clouds for them is more like a particle effect, right? That then like spawns things and it's animated. So it's one of these things where you have to like sort of like engineer how to use the thing that they have for what you want. So like there are ways of importing like actual point clouds, but then you have very limited functionality. Like people in the Discord were mentioning that you can't import colors. So like I have some examples in papers where like point clouds are like you segment a point cloud. So you want to show the point cloud in different colors. In that case, you have to import n different point clouds. But then if it's like a scalar field that you're showing, then you can't do that with like the native point cloud, or at least that I know of with the native point cloud Blender implementation. So you have to do, the thing I do is I write it as a degenerate mesh. And I know this is horrible, but I write it as a degenerate mesh with like every triangle is just one point, and then spawn a particle at each point, at each triangle, which basically creates the point cloud. But since you imported it as a mesh, you can still access like per vertex colors and per vertex information and even texture information. It doesn't need to be texture, it's just like when it reads it, it lets you read that. So you can have your vertex colors as the texture U coordinates and then pass that on to the color of the particle that's spawned, which is like a very horrifying trick, but it works.
Yeah, cool. Yeah, I agree. It's horrifying, but if it works, it works. You mentioned about color and per vertex or color. Let's ignore the point cloud math. If you have a mesh with some signal on it, do you have any suggestion how to actually use that signal into Blender?
Well, I guess it's like the good practice would be that one day you write what the node, like the material. If you go to like the materials that I showed, there's one very simple part of the material that's just selecting the color, right? You don't need to change like the reflection properties and all of that. There's one part that's just the color, like an RGB value. What you could do is and maybe I'll do this after this tutorial so that it's out there for everywhere. You could have different options for like, instead of just a fixed color, you can have like an input node that you like input from somewhere. And that like you do like a linear transform and clip it and put it on a color map. And that's the color that goes into the shape. That's like the good practice way of doing it. I mean, of course, not every like perception is not linear, so it's easier if you like think it through and like go into like some of the like perceptual color map studies that are like tell you like where to like stop the color map and all that. That would be good. Because that will let you like tweak the color map and change it in Blender. The quick, I need to render just this one figure because the cigarette deadline is in 5 hours fix is that you write it as the normals. You write the RGB values as the normal information, and then just import the normal. So like the normal is a field that you can write for any OBJ, and Blender will read the normals, right? But you don't actually have to tell it to use those normals. You can just say use flat normals, like ignore the ones that I gave you, and then those you can access them from the material nodes and pass those as values. So that's like the very quick. I just need this one render because like we're not gonna have time before the deadline. That's a fix.
Cool. I never thought about using the normal. I was using some crazy trick with some PLY, and it was always so time consuming. I should use it. Yeah, so there is another interesting question. Do you have any recommendation for rendering large batch of objects? Let's say I want to do the mosaic we saw, 2 talks or 3 talks ago, and I don't want to set up. Say you have 200 objects and you want to render all of them.
Is it like are you rendering like a scene with many objects or many scenes? I guess that's the question.
Yeah, I think many scenes. I'm reading the chat and interpreting. I would say many scenes, many objects. Many PNGs separately.
Oh yeah, then this is very easy to do. You just need to basically write. This is easy. It's gonna sound harder than it actually is because like I learned to do it, so like it's easy. There are toolboxes that do this almost immediately for you. But all you need to do is like make your Blender file, and don't put the object. Just sort of like decide where like the object location would be, and remove the object and save the Blender file that contains like the lighting, the shadow capture. It contains everything now. So then you do a very, very tiny Python script that says open like in a for loop, for all the objects I want to render, open this Blender file, import this OBJ, render. That's it. It's like 4 lines of code.
Cool. Wow. Yeah, I'm trying to.
It's very useful. I in my latest project. People always recommend Blender scripting, but I think it has like a very high learning curve. So I prefer that people learn the UI first and then they go into scripting. In my latest projects, I've been using scripting. It's very useful because you can like have a folder with all your results and like overnight leave it on that for loop. And then you wake up and you have like all the possible renders and you can choose which ones to add to your paper. You don't need to like commit to like one specific object.
Yeah. And you can also use a render farm or a remote separate computer and not overload your laptop if you have all scripted.
Yeah, for sure. Yeah, I usually render in one of our lab servers. Blender is also great for that. It's like one command line argument to render things in the server. So it really is like a great piece of software for academics in that sense, if you have access to that kind of thing. Yeah, actually, if you go to the website that I linked to, like the full guide, it includes like what if I want to render this on a headless server so that it doesn't destroy my computer. That was more relevant in Blender 2.x versions because but for 3.0. They improved the rendering so much that now you can render things on a laptop and leave it rendering, go grab coffee, come back, and it's done. It's like at that level. At this point, I'm rendering things on my laptop just because it's so fast now.
Cool. Yeah, then I should definitely update my Blender. Yeah, and thinking about coffee, I don't know in which time zone all of you are, but for me it's really necessary at this point. And this is also a good way of ending this session. So There is a lot of conversation on Discord, so yeah, if you can follow up that. Of course, now you were distracted by talking with me.
Yes.
Yeah, so thank again all the speaker for all this amazing tutorials, and we're gonna resume, I think, in 5 minutes now. Let me quickly check the schedule. Yeah, in 5 minutes, just time for a coffee, if you are in the right time zone. So yeah, let's resume in
Thank
5
you.
minutes. Thank you again. Okay, so let's resume. Let's try to not start being late. So we're going to start the last session of this graduate school, which is about geometric computing and meshing. And our first tutorial will be about geometric computing for biomedicine by Tao.
Hello. All right. Just to confirm, Tiso, I have an hour and a half, right? Or something?
Yes. Yes.
Okay, great. Let me share my screen. Okay, can everyone see my screen?
Yes.
Okay, great. My name is Tao. I am a professor at Washington University in St. Louis in the United States. And today I'm going to talk about the application or the use of geometry processing in biomedicine. So this will be a more or less an overview and type of talk, but I'll dive down into some technical details. Just as a disclaimer, I am a computer scientist. I don't have formal training or background in biology or medical research, but I've been working with doctors and biologists since my graduate training. And I found it a very rewarding experience for multiple reasons. One of them is that I get to use real data that's not bunnies or dragons. And with real data comes with real problems as well. In the process, I was able to discover some interesting new problems or new variations of old problems that we can study back in the geometry processing community. And last but not least, one of the reasons I like working in this direction is that we get to develop algorithms and software tools that are used by real people outside computer graphics or even outside computer science. And some of the solutions can be even life-saving. So that's quite a rewarding experience for me. I should say that this is a shortened version of a course that I'm teaching at WashU. This is a semester-long course with programming assignments and projects. So I shrunk the materials and modified the materials for the purpose of the graduate school. Why do I care about biomedicine? Well, biomedicine studies biological structures, and all these structures are actually geometry, three-dimensional geometry. And these geometry are multi-scale, meaning that they span a spectrum of scales. Coming from atoms, proteins, viruses at the nanometer scale, scaling up to cells and cellular structures at micrometer scale. And then grouping the cells together, you have tissues and organs that can be measured in millimeters or even centimeters, and all the way up to the entire the body of the humans, animals, and plants, which are measured in meter scales. Of course, you can stretch that scale all the way up to astronomical scales, but that's not usually where the biological forms take place. Already, we have a large variety of different real-world geometric forms, and biologists and medical researchers are very interested in the structure and shape and sort of the motion and growth of these different geometric forms, because these forms are associated with their functions. So how do biologists look at these geometric forms? I'll try to understand them, and the key technology that's being used is imaging. Yes. So over the past few decades or even centuries, a variety of imaging technologies have been developed, and nowadays biomedical research are very much image-centric. So I'm just giving you an overview of different biomedical imaging technologies, and because these are where the data comes from, right? So starting from two-dimensional imaging, you have the traditional light microscopy, where the images are taken under lighting, and through an optical microscope, they can have very high resolution, so you can see cells, in addition to tissues and organs. And then you can also look at the inside of the structure using X-ray radiography. You can have a sort of projection of interior of your structure on a film. You can use ultrasound, and this is often used for pregnancy tests and other diagnosis tests, where you can actually see inside the body within a cone-shaped region. Now, while these imaging methods give you two-dimensional sort of array of pixels, you can also perform a three-dimensional imaging, which I think is even more exciting, where you can see through the biological structure and produce a three-dimensional array of intensities or colors, right? So typical technologies include computed tomography, magnetic resonance imaging, MRI, and there are other methods that I've not included, such as PET, EM, and many other methods. The one on the far right is one of the newest sort of 3D imaging methods that can get down to the resolution of cells, individual cells, but seeing them in 3D. It's called light sheet fluorescence microscopy. We can even step up one dimension to 4 dimensions. This is adding the time dimension to the 3 dimensions. So you have imaging methods that can image a 3-dimensional image in 3 dimensions of subjects that move or change shape in time. So you can take a CT and MRI and do sort of a time series imaging, and then you can see beating hearts or a breathing lung. Right. So again, this is a short overview of the type of imaging technology that are being used, and these images really present both opportunities and challenges. Right. The opportunities are that now we can see these biological structures, which are usually invisible from our naked eyes. The challenges then is how to utilize these data, and this is where I think geometric computing can come in. Now, I have to say that geometric computing is not the end goal. It's really a method, right? It's a hammer, so to speak. And there are multiple hammers you can use actually to tackle the problem in biomedicine, and geometric computing is just one of them. Of course, I'm only talking about that because this is, we're in this community of geometry processing. So what can geometric computing do? Right? First of all, you can provide a geometric form or representation so that you can start to visualize a structure that's captured by these images. But then not only visualization, but for visualization, you can use geometry to actually define or reconstruct the 3D forms from images for example, shape analysis or topology analysis, or analyzing the mechanical properties of these structures. And you can take this analysis to multiple shapes and start answer questions about how do two different biological structures compare with each other. What are their correspondences, right? What are their motion trajectory? And these are all problems that can be solved using geometric algorithms. And going one step further, you can actually perform diagnosis or even planning a treatment, right? So one of the examples that I often use is a problem of planning a radiation treatment. And this is where you want to use radiation to burn out a tumor, but the problem is you don't want to hurt the surrounding anatomical structures, right? So once you have a geometric representation of both the tumor and the surrounding structures, then you can start to run optimization algorithm to figure out where to shine those gamma rays so that they would converge onto the tumor, but they would avoid as much as possible the surrounding structures. And I think probably the most sort of the frontier of the biomedicine in terms of geometric computing is to do virtual surgeries or surgical simulations. Now, this is a very demanding task because you have to be able to interact with tissues, multiple types of tissues in real time, and you want to provide the realistic feedback to the surgeons who are doing the simulations or the interactions. And again, this would call for multiple levels of geometric computing, from representation to deformation algorithms to mechanical simulations to visualization. And I'm sure I'm not covering some of the other ways that geometric computing can contribute to biomedicine. Now, you might ask, right? So why can't we just use existing geometric algorithms and apply to these images, this data? The things will be nice and easy. The challenges are these images are never perfect, right? And that's the I would say it's a common theme, right, among all biomedical image analysis, is that you're dealing with images that are either having limited resolution, meaning that the physical size of a pixel and voxel is just not small enough to capture what you want to capture. For example, in this image, right, this is a CT image scan of the human lung, and you would like to capture the lung airways, but then those are just represented as bits and dots in the images because they're just too fine at a scale to be captured by the image resolution. Or you can have a very poor contrast. So here, what I mean by contrast is a difference in intensity values between the voxel that you're interested in and voxels that you're not interested in, right? For example, you want to separate out the lungs from the surrounding muscles and bones. You want to separate the bones from the surrounding muscles and tissues. And typically, you have to rely on the intensity value. But depending on the imaging modality, depending on the material properties that you try to image, this is not always easy to do or not even possible. So there is a lot of ambiguity in the definition of structures. Not to mention the noise and artifacts that are inherent to the imaging devices. For example, you can see some speckles of noise in the images. So those are probably not what's actually in your body, but those are just noise that comes from the imaging method. And last but not least, with more and more images being produced and better sort of imaging technology, the images continue to get bigger and bigger. So many years back, having an image that's about 256 cubed is considered a very high resolution image. Nowadays, the standard would be 1,000 cubed in terms of the dimension of the voxels, and you're adding the time component, right? So that makes a very large data size. So with all these challenges and sort of issues with biomedical imaging, the challenge in geometric computing is using geometric computing algorithms is really to deal with the uncertainty, the ambiguity, the noise, and the data size. So how to scale up the algorithm, making them more robust to these artifacts and unwanted features. So I want to focus this talk on a couple of selected algorithms for geometric computing for biomedicine. This is by no means an exhaustive list, not even a representative one, because there are just many algorithms in geometry that are either motivated by biomedicine or can be applied to biomedicine. So this selection is purely based on my own experience. These are the ones that I'm most personally most familiar with, and I believe they're also very useful as well. So I'll first talk about contouring, which is a common technique for visualizing three-dimensional, two-dimensional structures from image and volumes. And then I'll talk about a topological simplification, which is a part of the segmentation pipeline to extract an object of interest from the image. And finally, I'll talk about how to compute skeletons for analyzing the shape of biological structures. Now, these are actually active research areas in geometry processing, but you probably don't know is that the first methods for in these directions were actually motivated by problems of biomedical image analysis. So what I'm going to do is the following, because this is a graduate school, and I want to try to catch sort of the both ends of the spectrum of attendees. To those of you who are not very familiar with these directions, I will spend some time talking about some fundamental techniques in each sub area. And for those who are already familiar with the fundamental techniques, I'll give you a brief review of the recent progress in each direction. Now, with a very limited time, of course, I cannot catch everything, and the materials could be either too easy or too hard for some of you, but I'll try my best. And I'll pause between these different directions to answer some questions, quick questions, and I'll leave some time at the end. Hopefully I'll have time at the end for more Q&A. All right, before I go in, any questions? Any from the attendees? Quick questions? Okay, all right. I will go ahead. All right, so starting from contouring. So the contour is defined for a function that's defined over a domain. So it is referred to the set of points where a particular function, where the function evaluates to a particular value, and this value is called the ISO value, right? So here is a simple example. Suppose I have a function defining 2D, which is x squared plus y squared, where x and y are the x and y coordinates. Then the contour at ISO value 1 is it's a set of all points where x squared plus y squared equals 1, right? So then, and that corresponds to a unit circle. You can change the ISO value, right? Make it bigger or make it smaller, and you will get different contours. Now, for this particular function, all of these contours are going to be circles. The contours have other names as well. They're in some community, they're called level sets. In 2D, they're also called ISO curves because the contours in 2D are curvilinear structures at a particular ISO value. So it's called ISO curves. In 3D, it's called ISO surfaces. In recent years, sign distance function have become a very popular way of representing 3D geometry. Right? In that situation, then your geometry is actually captured by the ISO surface at ISO value 0. Right? So that's one example is probably most of you are familiar with is the contour at 0 ISO value. There are some nice properties of contours. For example, they're always closed. That means that they partition the space into inside and outside. It's easy to understand because what's inside are the points that are where the function is above the ISO value, and for the points that are below the ISO value, that's the outside, and they have to be separated by the contour. In general, contours are nice and smooth and manifold. Manifold means that if you look at every point on the contour locally, it looks like a disk in 3D or a line segment in 2D. The only exceptions for this property is where the contour passes through what's called the critical points. I'm not going to go too detailed on critical points, but these are locations where the function's gradient becomes 0. In 2D, the critical points are the local minima, local maxima. In 3D, there is a third type of critical points called the saddle points. Right? So as long as you avoid the values of these local min, local max, and saddle points, then the contours are always nice and smooth and manifold for a smooth function. Of course, we don't have a smooth function when we give an image or 3-dimensional volume. All we have is a sampling of the function because all we know about the function are the values of the function at a pixel or at a voxel. Right? So the best we can do is to compute a discrete approximation of the contours. The approximation will be in the form of polylines, so consisting of line segments in 2D, or meshes, which consists of triangles or quads, right? or other type of polygons. So these discrete contours have become the standard way of visualizing 3D volumes. The other way would be the volumetric rendering, which does not involve too much of a geometry, but the geometric way of visualizing 3D volumes are usually through contouring. So if you look at any modern medical imaging software or medical image visualization softwares, they all have some implementations of 3D contouring or 2D contouring. So here are just 2 examples. One on the left is from a molecular modeling software called Chimera. It shows the electron density of a cryo electron microscopy volume of a large molecular assembly, but showing sort of different levels of that density map. And on the right is a stockpile picture of a CT image of human head. And you can see sort of multiple contours at different levels. And usually in the softwares, they allow you to extract contours at multiple ISO levels, ISO values, and that will give you an idea of sort of the content of the entire volume and not just at one particular ISO value. Excuse me. All right, so how do we extract contours? And usually this is done on the grid. Imagine that your input image comes in as a group of pixels and group of voxels. Each pixel or voxel comes with a color or intensity value, or could be RGB. In the world of biomedical imaging, RGB colors are rarely used. Usually you're dealing with a grayscale image intensity. And then you're also given ISO value that you want to extract the contour at. Now, for this part of the course, I'm going to use the conceptual model that each pixel or voxel is a point, not a square or a box. So it becomes a point on the grid, right? And every two neighboring pixels or voxels are connected by a grid edge, and a group of 4 pixels or group of 8 voxels forms a grid cell. With this model, then we can describe the output as a polyline or mesh in 3D that separates, right, the grid points that are above the ISO value from the grid points that are lower than the ISO value. So the output should kind of thread through these grid points, and that's why I represent them, think about them as points rather than squares. So there is enough space between these pixels and voxels for this for the output to fit in, right? So that's kind of the setup of the problem. Now, usually we think about an even simpler scenario where the ISO value is 0. The reason we only need to consider this case is that you can always convert any problem into the 0 ISO value problem by subtracting the ISO value from every value on the pixel or voxel. Now, in this case, our output should be a polyline or a mesh that separates the positive grid points from the negative grid points. Now, there are a large class of algorithms that can solve this problem. They can produce a result according to this requirement. Probably the best known method is called marching cubes. And this is what I'm going to talk about first, and briefly go over the marching cubes algorithm. The 2D analog of marching cubes is called the marching squares. It proceeds in 2 different stages. The first stage, it identifies each grid edge that connects 2 pixels or voxels with a different sign. Again, we're thinking about the problem of contouring at the ISO value of 0. Okay, so we only need to partition the grid points by their signs. So for each such edge, you would create a point that's the 0 crossing of the function defined by the linear interpolation of the values of those 2 pixels, right? And then you do this for every edge, a grid edge that connects 2 pixels with a different sign. That's the first step, is creating the vertices. Then in the second step, we have to connect the vertices up. And this is done by going through every grid cell that contains pixels not of the same sign. So for these cells, you would end up with either 2 or 4 vertices on the edges of that square, right? And then you connect those 2 or 4 vertices using 1 or 2 line segments. And you do that for every cell, and you get your curve back, right? And this would be your discrete ISO curve in 2D. Moving on to 3D, the algorithm is very similar. In fact, it only differs in the second phase. In the first stage, you generate all the vertices on grid edges. The challenge is how to connect those vertices up within a cell where the corners of the cell have different signs. Now, in 3D, you would want to connect them by triangles, right? Those vertices of the mesh, they have to be connected by triangles inside the cell. But the situation can get quite complex depending on how many intersection or how many vertices you end up with on the edges of the cell. You can get even multiple groups of triangles that you need to create. Now, in order to come up with a closed mesh that's not self-intersecting and that's a manifold mesh, you have to be careful in how these vertices have to be connected together. Fortunately, the connectivity of this vertices into triangles is only determined by the signs at the corners of each grid cell. So there are 8 corners of each grid cell, right? And if you look at the sign, then the sign will determine the number of vertices you have and which grid edge contains a vertex. So what is really nice about this method, marching cubes, is that it created a lookup table that's indexed by the signs at the corners of the cube. So there will be 256 entries. And in each entry, it tells you which vertices should be connected to form a triangle. So it only stores the connectivity, but that's what really, that's a challenging part, right? The geometric location of vertices is already determined by the first step using linear interpolation. So this becomes a really popular method because it's quite simple to implement, right? You visit all the cells, right? You look up the table based on the signs, and you connect the vertices using triangles corresponding to what you looked up in the table. So that's the marching cubes method. Of course, this is a method developed more than 30 years ago, and there have been a lot of improvements and different methods to try to solve this problem, which I'm going to try to cover some of them. The first issue with marching cubes is efficiency. As I mentioned, images, back when marching cubes was developed, that was 35 years ago, have relatively small size, right? Something like 256 cubed would be considered a very large image. But today's images are huge, right? And not only the images are big, the users might want to explore different contours at different ISO values of the same image, right? So a typical operation that a researcher would come in and explore an image is have a slide bar of ISO value and change ISO value on the slide bar, and they would like to see the ISO surface change in a responsive manner, and not waiting for even seconds or minutes. That's just impossible. But they want it to be sort of real time. So that creates a challenge for marching cubes, because marching cubes has to visit every single grid cell and grid edge to find out if if this grid edge connects to pixels or voxels that have different signs with respect to your ISO value. And as you change the ISO value, it has to do that search again, traversing through all the pixels and voxels and do the same test. That becomes really, really slow. So the first direction of improving efficiency is creating data structures, pre-computing data structures for a given volume that will speed up this process of finding cells that actually contain something of some part of the ISO surface, right? So usually the majority of the grid cells are empty. Of course, that depends on ISO value. So the challenge is how to create data structures that would, be able to speed up queries for every ISO value. One of the first data structure is a quad tree in 2D or an arc tree in 3D. And the idea is that you store, you organize all the pixels or voxels in a hierarchical structure, and you store the minimum and maximum value of the image intensity at every node of the tree of this hierarchical structure. When you contour, you go top down, and you only go to a subtree if the min and max value stored there contains the ISO value that you want to extract contour at. So that can really speed up the process of looking for the cells that contain something. You can also store the range of intensity for each pixel or each voxel as a range, as an interval on the real line, right? And then there is an optimal data structure for finding intervals that intersect a particular value, like your ISO value. It's called an interval tree. And this has been proven to be the optimal way of finding the pixel or voxels that contains some part of your of the contour. Now, another method for efficient query is utilizing the fact that ISO contours are usually connected, right? I mean, there could be multiple components, but usually you're looking at a connected piece of surface and not random dots in space. So one approach is to start with some seed point on each component of the contour and expand the seed to find out the entire surface. So that way you end up only visiting, right, the part of the volume that contains the surface, and you skip the rest. So there are a lot of works in that direction in terms of, you know, how to quickly find the seed points. And some of the data structure in computational geometry can be very useful here, such as contour trees. Yet another group of methods is based on the idea that if you only use isosurface for visualization, right, then there is no need to show the users what's hidden behind another layer of surface. Of course, this is based off multiple assumptions, such as there is only one user looking at the surface, and often there is no transparency coming in, right? So you can do visibility-based culling of the surfaces, only extract surface where the user can see it, or you can do some sort of level of details. So the triangles are extracted at a very fine scale, closer to the user, the viewer, right? And at larger scales, further away from the viewer. And last but not least, the GPU accelerations have been extensively explored for improving the efficiency of contouring. The second issue with contouring or using marching cubes in particular is mesh quality. So marching cubes and some variants as well tend to create very skinny triangles. And those triangles are a nightmare for doing computations on the meshes and physical simulations using finite element methods. So there have been methods other than taking very different approaches to create the contours, unlike marching cubes. Some of these methods are based on Delaunay meshing, and others are based on sort of propagating and spreading particles on the isosurface, and yet others are based on local heuristics. And these methods generate very nice triangle qualities. They're much more suitable to do sort of heavy geometry-based computations on those triangles. Now, the other aspect of mesh quality, which is not really relevant for biomedicine, is reproducing sharp features. This is mostly applicable if you want to extract the isosurface of a man-made structure, such as mechanical parts. You know, in industrial engineering, they use CT and other imaging devices as well to inspect the quality of a particular mechanical piece. And there you would like to create surfaces that accurately reproduces sharp edges and corners, which marching cubes doesn't give you, right? As you see, marching cubes tend to give you blobby surfaces. And there are many sort of directions you can tackle this problem. Some of these methods, like do contouring, they move the vertices away from the grid edges, but into the grid cells. So you have more freedom of putting those vertices on the sharp edges and corners. And more recently, there are deep learning-based methods try to recover the sharp features by learning the profile of the local images. So I want to point out that there's a survey out there that if you're interested in the area of contouring or isosurfacing, and it covers a large set of methods that are pre-2015. So if you're interested, you can check out that survey. Before I move on to the next subject, I do want to talk about some interesting extensions from isosurfacing. One of the extensions is looking at multiple materials. So isosurfaces naturally separate the inside from the outside. So that means it's doing a two-material classification of the entire domain. But you can think about cases where you need multiple materials. This comes up a lot in biomedicine because oftentimes you need a way to visualize different types of structures, different type of biological tissues that are touching each other, right? So think about the brain made up of multiple anatomical structures, and each one of them has an interface with its surrounding structures. So you can extend isosurfacing methods between two materials to multiple materials using either a do method or you doing some sort of plane intersections within each grid cell. You can also filled up the interior of the surfaces using volumetric elements such as tetrahedra or hexahedra. And you can do that for either the two material case or the multiple material case. And these are still active research directions in terms of how to create elements with higher quality and how to accurately capture the topological sort of variations in the interfaces. Because as you can see, when you have multiple materials, the structure and the topology of their interfaces can become quite complex. Okay, so this is still a sort of active research area. In fact, one of these methods here is a paper that we will present in SIGGRAPH this year, which is a more accurate way of finding the interfaces between multiple materials. All right, so that wraps up sort of the first part, and I'm going to talk about the second class of methods. Any questions at this point? Okay, if you have any questions, feel free to type in the chat, and I'll try to answer them sort of when I get a chance to take a little break. Okay, I think we're good on time. All right. So I'm going to move on to talk about the second sort of block of problems in biomedical image analysis, which is image segmentation. This is a process of extracting the object of interest from a given image. So here is an example. On the left-hand side, it's a slice of a CT image of a human bone. And because of the particular direction of the cross-section, you actually see two different bones. They're very close and next to each other. And the surrounding images are just tissue and fat and skin and some other structures. And suppose that the researchers are only interested in the bones, so you would like to extract sort of the two bones as separate objects in the output. There are an ocean of methods that will allow you to do this step, this separation between object and background, starting from really simple methods like thresholding or even isosurfacing that we just talked about, to methods that grow a template or a seed, or methods that deform an initial representation of geometry, whether you keep the topology or allow the topology to change, to methods using interactive graph cuts or watersheds, all the way to the more recent learning-based data-driven methods. And a lot of these methods really show up in computer vision and in biomedical image analysis community, and not necessarily in geometry computing. So I'm not going to cover those, actually. I mean, this will take another course, if not a semester-long course, to talk about image segmentation. What I want to mention is that none of these methods is perfect, right? So it always depends on the quality of image data and the assumptions of these algorithms. So more often than not, you will get an imperfect segmentation like this one. So there will be parts that you really want to be in the segmentation, but it's missing. And there will be parts that you don't want in the segmentation, but they're there, right? So a common pipeline of segmentation would start with your choice of segmentation method, whether it's sort of morphological based, region growing or learning based, and then you end up with a cleaning process, right? You need to clean up the segmentation so that you can use it for further analysis. To clean up the segmentation, you usually need to know some prior about the shape that you're segmenting, because otherwise there is no way of knowing what is feature and what is noise, what should be in the segmentation, what should be outside the segmentation. So you should have some prior knowledge of what this object is about. Excuse me. There are many ways of defining priors, and these, the definition prior changes between, when you have a different biological structure to segment. But I'm going to talk about a particular class of prior that's quite common in biomedicine, and this is the topological priors. So for those who are not familiar with topology, it is a property of an object that is not affected by continuous geometric deformations. So here is an animation that I stole from Wikipedia, which shows a continuous transformation from a mug to a filled up mug to a donut. Now the geometry has changed substantially in this process. Right? I mean, there's nothing really alike between a donut and a coffee mug in terms of geometry. But there's something that's not changing in this continuous process. For example, this handle of the mug does not disappear. There is always this kind of cycle, right, in this shape. Whether it's a coffee mug or it's donut, you see this cycle there. And that cycle is a kind of topological property of the shape. So in the intuitive terms, topology can be described by a set of topological features. In 3D, there are three types of topological features. There are components, which are really connected components of the object. There are voids, which are connect components of the background that are sort of disconnected from the outside, because there is always this outside background there, but then you can have sort of background space that's disconnected from the background, but sort of embedded inside the object. So these are called voids. And then there is a topological handle, which we just saw on the coffee mug or the donut, right? A handle is a cycle, right, of object. And you can also think about it, it's a cycle of the background as well, which goes through the handle hole. In 2D, however, there are only components and voids, and so handle is a unique feature in 3D. So give you a couple of examples. If you look at this two-dimensional shape, it has one component, one void, right? So that characterizes the topology of this 2D shape. For this 3D mechanical part with 5 drill holes, right, it has one component. There is no void. I don't think there's any void, although I cannot really see from outside. And there are 5 handles. Each handle corresponds to one of those holes. Okay. The reason that topology is interesting and useful for biomedical sort of image segmentation is that most of the biological structures have a very well-known set of topological features, and usually it's a small number of topological features. A lot of the biological structures, from cells or bones or lung airways, nerve systems or blood vessels, they're simply connected, meaning that they have one connect component, there is no void, and there is no handle, right? And the majority of the biological structure that need to be segmented have a very simple topology like this. And occasionally you get structures with a little bit more complex topology, such as some of the bones, like a hip bone or the vertebrae, they have this 1 or 2 handles in them. These are called multiply connected objects. But you still kind of know ahead of the time how many cycles, how many handles, or how many voids it should have. So that makes topology a good prior for image, for cleaning up the segmentations, because you kind of know the target, right? And once you develop a method that would work on any topological prior, then you can really use it on a large class of biological structure segmentations. So the goal of this topological simplification is really taking an incorrect segmentation in the terms of an incorrect set of topological features and remove as many of them as possible, with one condition, is that you do not want to alter the shape too much. You want to change the shape only if it's necessary to change topology, but otherwise you want to preserve the shape, right? So here's a really sort of poor illustration I drew yesterday. So, think about this as being your input. You have a 2D shape with 2 components and a void, right? And a possibly good way, a good simplification, topological simplification would be on the right, where you connect up the 2 components and then you cleaved, right? You cut a thin channel to let the void connected to the background. So now you get a shape that's simply connected and looks very similar to the input. It's important, again, not to alter the shape too much, because if you don't have that requirement, you can just replace any shape with a ball, because a ball has the simplest topology possible. But of course, you lose all the shape information. So that's kind of where the problem setting is. You have an input shape, and you have a prior knowledge about the topological set of topological features that this object should have, and you try to modify the shape to achieve that topology while minimizing the change to the shape itself. And that naturally leads to the question is, how do I remove a topological feature? It turns out that there are two asymmetric ways of removing any topological feature. So I'll start with an example of removing components. Right? So if I have two separate components and I want to remove one of them, one of the method is to simply remove one of the component, just destroy it, right? And just take one of the component and get rid of the other one. I call this method cutting because it's removing materials from the input. The complementary way is to add a material that bridge the two components together, right? And this way reduces the number of components by one as well. Right? I call this method filling because it's adding materials to the shape. There's two different ways. Cutting or filling can be applied to remove the other topological features as well. For example, for a void, right, you can dig a tunnel through the object to connect the void with the outside. And that's, again, removing materials, so that's cutting. Or you can simply fill up the void with the object, and that will get rid of the void as well. To get rid of a handle, you can cut open the ring of the handle by removing materials, or you can fill up the middle hole of the handle, right, by filling in the materials. Right? So again, you have two choices, really, to remove any topological feature. The actual choice of which way is the best way should depend on geometry. So because either way would reduce the number of topological features that already accomplish the topological goal. The rest is about how to best preserve the original shape. Right? So this choice needs to be made based on the geometry of the input. So I'm going to talk about some basic methods in this category of to simplify the topology, and I'll again have a brief overview of the recent methods, more advanced methods for simplifying topology. The basic methods have to deal with binary pictures. So these are going to be operators on a segmented image or volume that have the effect of simplifying the topology. It may not always fix all the topological problems, but it is sort of a fundamental set of techniques that you can use. These techniques work on what I call binary pictures. So essentially, these are just the segmented images and volumes. Binary picture is a particular sort of a name for this type of geometry. So basically, it's an image with black and white pixels. And in this talk, I'm going to use a convention that the white pixels are the 1 pixels. They have value 1, and they're the object. And the black pixels are have values 0, and they're the background. Okay. Of course, you can use your own convention. It's at your own choice. Now, this binary picture should remind you of geometry that you see in games such as Minecraft, or physical objects like Legos. Right? So these are actually geometry people use, even outside biomedicine. So like I said, I'm going to talk about two types of operators that can change the topology of binary pictures. One class is called the connectivity-based operations. So these are used for removing small components or filling small voids. And the other class are morphological operations. And they are not directly operating on topology, but they can change the topology. And what they do is they can remove thin pieces or filling the narrow gaps. By using these two operators, you can actually convert a very noisy input segmentation to something that's much more clean. And we'll talk about how to use these operators as well. Now, these operators are what I call the building blocks of many segmentation cleaning algorithms, and they're implemented again in almost every biomedical image analysis software packages. So hopefully this will give you an idea of how these operators are actually implemented and some of the subtleties that you don't always realize when you try to implement them. So we started talking about connectivities. Now, connectivity is a well-defined concept on graphs, on mesh geometry, but it's actually quite challenging to define for binary pictures that's made up of pixels and voxels. And by the way, so we're now switching to the other conceptual model of pixels, where each pixel is a square and each voxel is a cube. Because then we can start to talk about connectivity, right? Because if you keep thinking about pixels as points on the grid, then it's really hard to looking at the connectivity because they're not actually touching. So for 2D pixelated images, there are two kinds of connectivity, types of connectivity we can choose from. The first type of connectivity is considering two pixels that share a common edge as being connected, right? So if there's two orange pixels shares a blue edge, then those are two connected pixels. In this connectivity, every pixel is connected to maximally 4 pixels around it, right? Top, down, left, and right, right? That's why it's called 4 connectivity. The other option is to treat every 2 pixels that share a common corner to be connected. And if you define connected this way, then every pixel can be maximally connected to 8 pixels around. That's why it's called 8 connectivity. You can extend this approach to 3D, and you will get 3 different connectivities in 3D. Either 2 voxels that share a common edge will be connected, and that will make a voxel maximally connected to a maximally set of 6 voxels. So that's called 6 connectivity. You can define 18 connectivity to treat 2 voxels sharing common edge as being connected, or 2 voxels sharing a common vertex, common point to be connected. And that will give you what's called the 26 connectivity. So you are actually free to choose any one of these connectivities as long as it's consistent throughout the entire object, entire image, right? You don't use different connectivities on different parts of the object. And it's really a sort of a personal preference which connectivity you use. However, you have to be very careful in choosing the connectivity of the background pixels when you fix your connectivity of the object. And this is one of the very important subtleties of analyzing images using connectivity. So I want to just show an illustration to kind of make that point. So suppose we're given this binary picture. If we use an 8 connectivity for the object, right, we'll find that there is one connected component because all these pixels are connected through their corners. So here I'm drawing a graph representation where every node of the graph is a pixel, and 2 pixels that are connected, I draw an edge between their corresponding nodes. And you can see that this graph is a closed curve, right? But if I use a different connectivity, let's say 4 connectivity, then I get 4 connect components because 2 pixels are not allowed to connect through their corners. So I get this 4 kind of islands in the image. Now the question is what connectivity I should use for the background. So one natural choice is to use the same connectivity between from the object and to the background, right? So if it's 8 connectivity on the object, then I can use 8 connectivity for the background as well. But here is a problem, right? Is that if I use 8 connectivity on the background has 1 connected component as well. And this creates a paradox because the object, as you see, is shaped like a closed curve, but the closed curve did not separate the background into 2 components. In fact, the background is still connected. That's quite counterintuitive, right? In fact, there is a famous theorem in a continuous case called the Jordan curve theorem, which states that every closed curve in 2D must partition the plane into inside and outside. So essentially, if we use 8 connectivity for both object and background, we break that theorem, right? The theorem fails in our setting. Similarly, if we use both 4 connectivity for both object and background, we get another kind of paradox, is that the object is disconnected, but somehow those islands disconnect the background as well. Right. So again, that's quite counterintuitive. So the solution to that is actually do the other way around, is to use a different connectivity between the object and the background. So if you choose 8 connectivity for the object, you should choose 4 connectivity for the background. And in this case, the foreground, it forms a closed curve that partitions the background into 2 different components. If you use 4 connectivity for the foreground for the object, then you should use 8 connectivity for the background. Right? In this particular case, the object are 4 islands, and those 4 islands do not disconnect the background. So the background still has 1 connected component. Now, visually for this example, this makes sense, but of course, to show that this approach really works, we have to prove that it works for all cases. In fact, there is a rich theory behind the choice of connectivity for binary pictures, and I will give you some pointers for papers and books to read after this. In 3D, it's similar, right? You have to alter your connectivity between object and background. And so if you choose 6 for the object, then you have to use 26 connectivity for the background and vice versa. And if you do that, you can also show that it conforms to the intuition that if the object is a closed surface, then it will partition the background into multiple connected components. With connectivity, you can start to clean up segmentation. For example, if you have a segmentation with noisy pieces that you don't want, and if those pieces are small enough, then you can remove those pieces by their size, right? So you can say that, well, let's pick the connected components whose size above certain threshold, or take the largest one, the largest 2, or largest decay number of connected components, right? You can also remove the holes inside these shapes, because these holes, these voids, are just connected components of the background, right? So by filling up all the background connected components, except for the largest one will be the one that's outside the shape, then you can fill up the holes as well, right? So these are operations that are commonly used for removing islands and removing holes. But it's not perfect, right? There are many issues with using connectivity alone. The first one is that if the components you try to remove are not really disconnected, it's barely connected, it's connected by a pixel or voxel, or if the voids are actually not real voids, they're connected to the background through some very narrow channels, then this approach won't work, right? So I'll give you an example. So suppose I have another segmentation, which is also noisy, and I can take the largest components, that's fine. But then if I try to fill up the voids by looking at connect components of the background, I found that I could not fill up some of those voids. This is because those voids are actually not voids. Those are actually connected to the outside through some very narrow channels, right? So in this case, the connectivity-based operations will not be able to filling holes as I could do for the previous segmentation. The second problem with using connectivity alone is that, going back to the cutting and filling approach that I talked about before, connectivity analysis only does one of them. For example, it removes a component by cutting away the component. It cannot bridge the 2 components together, right? So in this case, this component is completely removed, even though it's a pretty significant piece that you might want to connect with the main object. Symmetrically, for voids, you can only fill up the voids and cannot connect the voids with the outside, right? So it only does cutting for components and only does filling for the voids. And you cannot do the other choice. So that's another problem. And of course, it does not treat handles as well, because the handles is just a single connect component. It does not have additional components or voids, right? So connectivity analysis alone will not be able to remove noisy handles in 3D. So this is where we go to the next set of operations, which are called the mathematical morphology. So these are methods that can change the shape, not just topology, but the geometry as well, but it could also change the topology, right? So the definition of morphology is based on the two inputs. One is the object that you want to operate on, right? So that's, for example, is a blue square. And also there is a definition of what's called a structure element. So a structure element is, think about it as your chisel or as a brush, right? That's your kind of the tool that you want to operate onto the object. Usually it's a circle, right? That's centered at any point, and a given point. Or it can be a square, it can be some other shapes, right? But the structure element is defined around any given point X. And with these two inputs, you can define a way that shrinks the object inward called erosion. And this operator basically takes a union of all the points whose structure element can fit inside the shape, right? So if I take the big square, the erosion would be a smaller square, because if I center the circle at any point inside the cyan square, the smaller square in the middle, that circle fits inside the bigger square. The symmetric operation is called dilation, which poofs up the shape. It does this by taking the union of all the structure elements centered at the points that's inside your object, right? So it kind of grows the shape outward. Now, these two operations are actually due to each other, but under one condition is that your structure element has to be symmetric. So the structure element is symmetric if a point is in the structure element of the other point, if and only if the other point is in the structure element of the first point. So some examples are circles. It's always symmetric. If you have a structure element that's centered at a point, then they're always symmetric. A square is always symmetric as well. A triangle in general as a structure element is not symmetric. So if your structure elements are symmetric, then eroding the object is equivalent to dilating the background, and vice versa. And so dilating the object is the same thing, give you the same result as eroding the background. Okay. Now, erosion and dilation are rarely used alone in practice because erosion would shrink the object everywhere, right? And that will make it just objects smaller, right? And it's not helpful if you want to fix some local problems, like local topological issues. Same thing with dilation, it makes everything just bigger, right? So of course, you don't want to use that operation because that changes the dimension and size of the object. A more localized approach can be achieved by combining the two operations. But there are two different ways of combining the operations. One is you first do erosion and then you do dilation, right? So it's erosion first and then dilation. And this operation is called opening. The reason it's called opening is the following, is that because it shaves off the sharp corners and removes the thin spikes. One way of understanding opening, this is something that I tell my students all the time, is how do you check your result of opening is correct? Is because of the definition of erosion dilation, right? So erosion takes a union of points where you can center a structure element inside the object, and dilation take the union of those structural elements. So combined together, opening is essentially the union of all the structural elements that can fit inside the object, right? So if you take the input square and the union of all circles of that particular radius that can fit inside the square is this square with rounded corners, and that's your opening operation. Closing does the other way around. It starts with dilation and ends with erosion, okay? It actually produces a different result than starting with erosion and ending with dilation. Right? So that's another interesting aspect, that if you change the order, you get different shapes. Closing tend to shave off the concave corners from the outside and fill up the thin gaps. Right? So here's an example of using closing. You get those two concave corners shaved off. That means that the final opening result would not have those sharp corners, but instead have those rounded corners in there. And again, closing is always bigger than the shape, than the object that you start with, although it's not sort of expanding in shape everywhere, it's only expanding in the concave places. whereas opening is always a subset of the input, but it's not shrinking the object entirely. It's only shrinking in specific locations. So that's why these two operations are used more often than erosion and dilation. Again, if your elements is symmetric for circles and for squares as structural elements, erosion, an opening of the object, is the same as closing the background and vice versa, which gives another way of understanding closing. He said, like I said, opening is basically the union of all structure elements that can fit inside the object. And because of the symmetry, closing is basically the union of the structure elements outside the shape and the complement of the union, right? So that's, I think, an intuitive way of understanding the result of opening and result of closing. Discretely on the binary images, we can never define a continuous circle or a perfect square. What we can use is, come up with shapes that consist of discrete number of those pixels or voxels. So the typical structure elements to use in 2D are this 3x3 squares or this cross shape, and they have their counterparts in 3D as well. So the most common ones are the 3x3 squares in 2D or the 3x3x3 cubes in 3D. So here's an example result of opening and closing. So if I take a binary image, binary picture in the middle, if I do opening, right, I got rid of all the tiny pieces, but I still leave some holes inside, right? So basically, the result of the opening is a union of those 3x3 blocks that can fit inside the white region of the input image. And because of that, it got rid of all the thin pieces, such as this string of pixels, or even this part of the pixels, because it's very thin, and that disappear after opening. And that's what opening does. It opened up the shape. It got rid of thin pieces. Symmetrically, closing can be understood as try to fit 3x3 black squares in the complement space of the object, right? And that would get rid of thin tunnels like these ones, and they all disappear, but it will still keep the little islands out there because there's still a way to fit around those islands, the 3x3 black squares, right? So that's kind of difference between opening and closing. Opening can also be used for removing small islands, and closing can be used for removing small sort of voids in the middle. But they also changed overall shape of the object as well. You can do more opening and closing by using larger and larger structural elements. You get more drastic sort of effect in terms of smoothing and topological change. You can also do equivalent, instead of using larger structure elements, you can also perform erosion multiple times, followed by dilation multiple times, or the other way around for closing. So these two operators, connectivity and morphology, are often used together to fix a segmentation. So I'll use the example that I showed you early on to show you the benefit of using these two operators together. So this is the example I showed you before, where I first connect components, I can keep the bones there. But if I simply fill up the voids using connectivity alone, I wouldn't be able to fill up those big holes that are actually connected through very tiny narrow gaps, right, to the background, to the outside. So this means that we have to close those narrow gaps, right, to make those holes actual real holes in the middle. And this is where closing can come in. So instead of doing this second step, I replace the second step by closing. And then closing would give you a result where there are no narrow gaps of sort of narrow strands of the background pixels. And then I can use the connectivity analysis now to remove those holes inside by keeping the only sort of the largest connect component of the background, which is the outside component. And finally, as you notice, there are some pieces hanging off the bone, which probably not part of the bone, but an artifact of the imaging. We can use opening to open those up and to remove those pieces, because opening would essentially take the union of a 3x3 white block inside the shape, and that would not allow, those 3x3 block would not be able to fit into those thin pieces. So the last operation opening is really used not for topology, but for geometry as well. So as you can see, this process is going to be specific to the input segmentation and the qualitative segmentation and your goal of what to keep and what to throw out. And as a result, it's difficult to put together an automated pipeline using connectivity and morphological analysis. And something this is a process that the user needs to get really involved, which means it's probably not going to be used to batch process data. That's number one sort of issue with using connectivity and morphology. The number two issue is that, again, morphological operators are not targeted alone at topology. So sometimes it can create new topological issues at the cost of fixing existing ones. So if I take the input image on the left-hand side, which has two components and no void, and if I want to connect the two components together using, for example, closing, by connecting those two components, I also connect another part of the shape, which creates a void, right? Because closing is done for the entire image, right? So you have to, essentially fit this 3x3 or even 5x5 black square in a complementary space. And you don't have a choice of where you do it and versus where you don't, because you don't know where it needs to be done. So you do it everywhere. And that's a major issue is, we cannot control exactly the final topology. So the more advanced methods, which I'm going to just give a brief review of sort of the more recent and advanced methods for topological simplification. These methods are run automatically to satisfy a particular topological constraint, such as the number of handles, number of components, number of voids to have in the final result. Usually these methods try to simplify the object to a simply connected shape. So that means it has only one component and no void, no handles. But there are algorithms that can achieve a specified, prescribed number of topological features. All right, so one of the class of these methods is what I call the monotonic methods, and these methods only perform cutting or only perform filling. These are mostly earlier methods because it's easy to restrict your operation to only removing stuff or adding stuff to the object. The downside of these methods is that they tend to create large geometric changes. So I'm going to use this one as an example, running example, to kind of show the issues with these methods. So suppose this input is actually an isosurface or contour of a blood vessel from an angiogram. Those are blood vessels in the brain. And you can see that there are some isolated pieces, some components over here, and there are also handles, couple of handles throughout the blood vessel network. And we know this should be a simply connected shape. So that's what we want to do. If you perform filling only, right, if you're only allowed to add to the shape to remove the topological features, what you end up doing is you're going to have to fill in each handle hole, no matter how big the handle hole is. And you have to connect each component to another component through a bridge, no matter how small the components are, because you're not allowed to remove, right? Symmetrically, if you're only going to perform cutting and not connecting, you end up having to remove all the components, no matter how big they are. Some of the components are quite big, and they're better to be bridged with the main object rather than being removed as a whole. But you don't have that choice if you're only performing cutting. So the better approach would what I call the non-monotonic methods. They allow both cutting and filling, and they can choose where to cut and where to fill depending on the local geometry, right? So there are a couple of methods that fall into this category. And for example, they can choose to, perform cutting for a handle with a very large hole, but a thin sort of handle ring. They can perform filling by connecting a large component with a main object instead of removing the entire component. The issue with this method is that they often use local heuristics. So some of the choices may be suboptimal. So for example, this method would still miss some of the major components here because of some suboptimal choices that they made along the way. And recently there are some more global methods like this one that we presented in SIGGRAPH in 2020. It formulates the problem as a global optimization problem, and now it can perform better choices. It's not the optimal algorithm because the problem it formulated is actually an NP-hard problem, so there's no hope of getting the optimal solution. But the methods that's designed for solving the problem tends to perform, make better choices than the local heuristic methods proposed in the past. So this kind of captures sort of the stream of development for topological simplification in 3D, but I also want to mention some related topics that are also interesting. So instead of doing simplification completely automatically, you can also choose to involve user in some way. But the key is to reduce the human effort as much as possible. So one of the earlier work in this direction is allow user to draw sketches wherever there is a topological ambiguity in the reconstruction process, right? So the algorithm would identify those locations and prompt the user for guidance in those regions. Some other methods allow the user to draw a global sketch of like a skeleton, and then use the topology of the skeleton to guide the reconstruction process. And this would also allow the result to have certain number of handles or topological features that the user desires. An even better way of performing topological simplification separately from segmentation is to do two things at the same time, is to embed the topological prior in the segmentation or the reconstruction process. There are actually quite a few approaches, although not many of them are not applied to biomedical imaging. One of the approach that's kind of the type of way you can do this is to grow a seed shape to fill up the data. And as you grow, you can control the change in the topology. You can also take a template shape and try to deform it to your data. So in our lab, we have developed some topologically controlled reconstruction methods, and those are for data that consists of cross-sectional curves, right? So these are data also provided in the biomedical setting, where the doctor would often hand draw the boundary of regions of interest on selected 2D slices of a 3D volume. And of course, there are many slices, so we're hoping that the doctor would provide just a few slices, and we use an algorithm to interpolate those slices into a complete shape. And we developed an algorithm that can control the topology of the reconstruction, in addition to interpolating the geometry of these curves. And that method can be also extended to dealing with multiple materials as well. In this case, you would have to make sure that the topology of each individual material is as desired. So again, there is still quite a few open questions in the direction of topological simplification, especially dealing with multiple materials and dealing with very large data sets. So how to effectively combine users and algorithms to deal with large data sets with multiple materials and ensure that the correctness of the topological features, it is still an ongoing research. All right, so that wraps up the second part, and I want to see if anyone has any questions. All right, so I will move on to the last part, which is computing skeletons. So skeletons are commonly used shape descriptors in geometry processing. If you haven't heard of them, they are thin geometric structures that are centered in the shape. So in 2D shapes, for 2D shapes, the skeleton would be curves centered inside the shape. For 3D shapes, the skeletons could be curves, could be surfaces. That very much depend on the actual application. But no matter the sort of dimensionality of the skeleton, they all need to capture the shapes of the object as well as the connectivity and even topology, right? So if the object has a handle For example, the tail of the elephant here that needs to be captured by the skeleton. And the structure of the skeleton should also tell you how the object is decomposed in different parts. Skeletons are very useful for biological shape analysis. If there are many questions of shapes that skeletons can help to answer, for example, at fundamental level, it can give you some metrics and measures of the biological shape, such as the length or width or directions, right? So these are some images from the project that I've dealt with in the past. The middle one is an image of sperm cells of fruit flies. They are actually the stringy shapes, and biologists are really interested in measuring the length of those strings, right? So computing the skeletons of those cells would be a natural tool for measuring the length. And the picture on the left, on the right, is a picture of a microtubules on the outside of a plant cell. And the directions of how the microtubules line up is closely related to the direction in which the cell grows. So again, the biologists are interested in analyzing sort of distribution of the directions, and skeletons are again a natural choice for representing these microtubules and for analyzing their directions. Skeletons are used for decomposing shapes into parts. So here is an example of a protein imaged using cryo-electron microscopy. So you can look at the isosurface that's of the protein, and obviously it has multiple parts, right? And biologists are interested in how those parts correspond to protein structures, such as alpha helices or beta sheets or the connecting pieces, right? So understanding the part of the shape would help the reverse engineering process of computing the 3D structure of the protein. And this is, again, a place where skeletons can be very helpful. And last but not least, skeletons can be used to analyze the correspondence and alignments of shapes that are related to each other, such as the sequence of growing plant roots. So how do we compute skeletons? This goes back to another related concept called the medial axis, because many skeleton algorithms are based off this concept of medial axis. And medial axis is really powerful but simple, simply defined structure. So given a shape, given an object, whether it's in 2 dimensions, 3 dimensions, or higher dimensions, the medial axis consists of all the points that are that have 2 or more nearest neighbors on the boundary of the object. For example, this red dot would have 2 nearest neighbors on the boundary, and this green dot would have 3 nearest neighbors on the boundary. So the collection of these red and green dots would form the medial axis. There's another intuitive way of understanding medial axis is through a burning process. So imagine that your object is filled with grass, a uniformly distributed grass, and a fire starts to burn on the boundary of the field inward, like this. And the medial axis would emerge at the locations where the fire fronts meet and they quench each other, right? So it's natural because where the points where different fire fronts meet are exactly points that I have at least the 2 nearest points on the boundary. So medial axis has a whole bunch of interesting properties that make it a really useful, at least in theory. It's by definition it's centered because it has 2 nearest points, one on each side of the object. It is at least 1-dimensional thinner than the object itself. So the medial axis of a 2-dimensional object is 1-dimensional. If medial axis of a 3-dimensional object is at most 2-dimensional. So that means that medial axis in 3D is made up of 2-dimensional sheets. It preserves topology as well. And this is actually relatively new result, was proved in 2005 that in any dimensions, the medial axis has the same topology, number of components, voids, and handles, as a 3D as the object itself. And the medial axis capture the shape. In fact, you can reconstruct the object completely by taking the unions of the balls along the medial axis, where the ball radius is a distance from a medial axis point to the boundary of the object. However, it also has some drawbacks that makes it less useful in practice. So it's very useful sort of in theory, but not so much in practice. Number one is that it's very sensitive to small boundary perturbations. Like I said, medial axis has to be able to reconstruct the shape exactly. So it tries to capture every single sort of bump and knobs on the boundary. That makes it overly complex in most of the situations. And secondly, it may not be thin enough, right? Like I said, in 3D, the medial axis consists of two-dimensional sheets rather than one-dimensional curves, as some applications might demand. And this is where sort of skeletons come in. They are also thin and centered, but they can be as thinner than medial axis. So I'm going to go over a really quick, a simple algorithm for computing skeletons, again, on binary pictures. So the theme of this sort of the course is starting from binary pictures. And this is a commonly used method, something that's really simple to implement as well, at least in 2D. It's called thinning. And the idea of thinning is a discrete way of burning the grass fire analogy, right? Remember the fire burning analogy I mentioned earlier, but do that discretely at the unit of voxels or pixels on a binary image, right? So here's an example is that, you take this horse binary picture and you shrink it down and perform iterative erosion until you get down to a set of digital curves, a set of one voxel thick curves. And this is essentially an analogy of this fire burning process. And you replace burning by erosion, right, which is one of the morphological operations that I mentioned early on. The key is to keep track of pixels that are the places where different erosion fronts meet. And those pixels are usually forming these digital curves, right? One voxel, one pixel wide strands. And those are the pixels that we need to protect and not to remove from, right? So that's kind of how the game plays, is that you need to identify certain pixels and protect them from being eroded. So there are two types of pixels you can protect in 2D. One is called the curve end pixel. These are the pixels at the end of the curve. And it's easy to identify them because you just need to count the number of neighbors, right, around that pixel. If there's only one neighbor, that means this pixel is at the end of the curve. The pixels in the middle of a curve are much harder to detect because there's ambiguity. For example, in this situation, is this pixel C, is it on a digital curve or not on a digital curve? It could be yes, it could be no, right? In the yes situation is where this pixel is at the junction of multiple digital curves, but you really have to look at a large neighborhood to analyze whether this pixel is on a digital curve or not. A simpler way to do that is to just check if removing the pixel changes the topology of the object, because if it's in the middle of the curve, if you remove that pixel, set it to background, the curve will be broken up and you will end up changing the topology, right? So that's where the really interesting sort of replacement comes in, is to replacing a geometric test by a topological test. So I don't think I'll have time to kind of go through the details of the algorithm, but I just want to mention that, so let me go through this, is that the way to detect pixels to be removed is to identify pixels that are on the border of your object. This is one iteration of thinning. Identify which pixels whose removal would not change the topology, and those are called the simple pixels, and also identify pixels at the end of the curves. And you want to remove all the border pixels that are simple and that are not at the curve end. And that gives you a set of what I call the removable pixels to remove at each iteration. The key is all of these pixel types, border pixels, simple pixels, and curve end pixels, can be identified just within the 3x3 neighborhood of every pixel. That makes the algorithm very efficient to run. There is no need to go through the entire image to count, the change in the components of the object or components of the background. So that makes the algorithm very simple to implement. with this removable pixels, right, a natural way to perform thinning is to do the following. In each iteration, you detect all the removable pixels and remove all of them at the same time. It turns out that this natural approach doesn't work, right? And you'll get something like this. And the reason is because even a pixel, it's simple, which means removing individual pixels would not change the topology of the object. But if you remove a whole bunch of them together, you can still end up just changing the topology, right? In this example, if you have 2 rows of object pixels, each one of them is actually simple, because if you remove any one of them, the object stays, the topology stays, right? But if you remove all of them, the object basically disappears. So the alternative to that is called serial thinning, which means that in each iteration, you detect all the removal pixels, but then you check to see if it's still simple before you remove that pixel. And this will guarantee that the topology does not change, so you will get a skeleton back in this case, right? And you can do that for 3D as well. You can detect removable voxel as the border voxels that are simple. In 3D, you have to worry additionally about tunneling effect, because in 3D, handles become a third type of topological features. So you need to count not only the object and background components, but also the tunnels as well. You need to detect what voxels are at the end of the curve and end of the surface. In some cases, you need to use some templates. So the 3D implementation is a little bit more challenging than 2D. The problem with thinning, there are a couple, right? And that's why it was sort of the earlier method for computing skeletons. Number one is that because it is serial, it depends on the order that you visit the pixels and visit the voxels. And using different orders will give you different skeletons. The results can be very sensitive to the boundary perturbations, because there is nothing in the algorithm that helps you to identify whether this branch of the skeleton is capturing a major part of the shape or just a little small perturbation on the boundary. And finally, because it is using this thinning erosion method, it's simulating the sort of, the front growing of a Manhattan distance function, not a Euclidean one. So it's quite sensitive to how you orient your object on the grid. And there are ways to improve on thinning, and this is where sort of I will give a very brief overview of more recent methods to sort of remove the dependence on the visiting order. You can do what's called directional parallel thinning, and this is where in each iteration you break it up into multiple passes. And each pass removes all voxels that are bordering to one particular direction, right? To the top and bottom or left or right or front and back. And each pass can be made a parallel without changing the topology of the shape. You can use distance functions, Euclidean distance functions, potential functions, or gradient-based methods to improve the stability of the skeletons. So some of the better known skeletons are based on this method, such as Hamilton-Jacobian skeleton, which is based on propagating a speed function using the gradients of the distance field, and the mass transport skeletons by Jalba et al., which give you a nice and clean skeleton using the distance field from the boundary again. Some other methods, just want to mention briefly, is computing skeletons. You can start by computing medial axis, and then by processing the medial axis to get the skeleton that you want, right? Computing medial axis exactly turns out to be a very challenging task. And this is still an open problem, is how to compute exact medial axis of a polyhedral shape. The state-of-art algorithm can only process a very simple polyhedra with dozens of faces. So usually the methods that handle more complex shapes are based on sampling, placing sample points on the boundary, and they are usually based on the Voronoi diagram of those sample points or some derivative structures from the Voronoi diagram. More stable skeletons can be obtained by either smoothing the shape and then computing the medial axis, or just taking a subset of the medial axis that correspond to the major parts of the shape. And this is usually done by defining some sort of significance measure on the medial axis itself. If you're only interested in curved skeletons, there are actually a variety of methods designed specifically for curved skeletons, such as contracting the mesh to get the center curves, or taking a set of example poses of a shape to compute a segmentation of the object, which will give you a kind of a kinetic skeletal structure. For point samples that are incomplete or maybe noisy, there are methods that are based on deformable models or based on optimization. So there are actually more methods that are specific to curved skeletons than methods that apply generally that compute a general sort of medial axis type of skeletons. If you're interested, there are a couple books and surveys I can recommend. I wouldn't go through all of them, but I just want to mention the first one, the digital geometry book, also has some theory about the choice of connectivity between the foreground, between object and background, like as I have mentioned before. So this is kind of quickly going through the three classes of methods. I know I'm a little bit over time. I just want to briefly mention an example use case of these methods. And this is a case where, it's a current project they're working on where we take the input as a 3D image of a plant root, and we want to compute phenotypes of the root, including the hierarchical structure of the roots and the traits, properties of the branches of the roots. What's interesting about the project is actually it involves multiple steps to compute the phenotypes, and those types, those different steps of the pipeline all involve some form of geometric computing. So I'm going to quickly go through and to the pipeline, right? So this is kind of the input, which is a three-dimensional CT image of the plant root. The root has been excavated and cleaned and imaged using a customized CT machine. And the end result is a skeleton that's labeled by the hierarchy type and the different properties of the skeletons. The first step is to reconstruction, and this is where topological simplification comes in. The image resolution and quality just not high enough to capture some of the fine features. You have handles and thousands of those components. And using topological simplification, we can actually get a much cleaner reconstruction with significantly reduced number of topological features. In the second step, we apply skeletonization techniques, and this is where we use a medial axis approximation method, followed by a shrinking method on the medial axis to extract the subset as a curved skeleton, as well as a thickness measure associated with the skeleton. And finally, this skeletal structure, which is a graph, allow us to compute the hierarchy structure of the skeleton and the various geometric properties of the branches. And this is a final sort of the picture slide, some visualization of different hierarchies that we computed for all kinds of roots. So those are actually dug up from the ground in Illinois. There is a research field that we work with. And starting from these hierarchies, we can actually perform some biological analysis between, for example, wild type and mutants, and do so without too much of a user intervention because this entire pipeline is automated. All right, so I've kind of ran through these topics, and this is kind of recapping what I've talked about today. I gave a brief overview of biomedical imaging, talked about a couple of geometric algorithms for image analysis, and then I quickly showed a use case of some of these algorithms for root phenotyping. And with that, I will conclude, and I'll be happy to take up any questions.
Yeah, thank you for a really, really nice talk and overview of many different things. So I don't see any question on the different channel. I'm going to start with my question, and this is a question I'm not believing I'm actually asking, but a lot of the things you're dealing with have intrinsic ambiguity, right? You're talking about handle segmentation, and this is the part I don't believe I'm asking is you haven't talked about learning at all. And nowadays, learning is trying to be applied to a little bit everything, and it feels to me that when you have ambiguity and stuff like that, maybe this is something what could be used. What's your thought about that?
Yeah, it's a good point. So as I mentioned, I think I mentioned a little bit of learning in both contouring and simplification, right? So in contouring, there are recent papers that try to use learning to recover sharp features on isosurfaces, and this is definitely an interesting direction to go, because oftentimes ambiguity when there is ambiguity, it's difficult to know, if there is a sharp feature and what that feature looks like. In terms of topological simplification, right, this is where I think there's a lot of room for future research, is that right now, most of the simplification methods are using this, what I call classical approaches, right? They look at handles, components, and try to cut and fill them by setting up optimization problem or some local heuristics. It will be interesting to see if topology can be treated as a loss function, for example, in a learning pipeline. We have started to see some early works in that direction. The challenge there is, again, topology is a discrete measure, right? Number of components, number of handles, it's an integer. It's not differentiable, it's not even continuous. So how do you turn that into a form that's at least continuous, if not differentiable? And that would sort of, make us a step closer to sort of learning-based simplification. I think for skeleton computation, we also started to see some recent methods that use learning to compute either approximate medial axis or compute the curved skeletons. The challenge there again is with topological connectivity, is how to ensure that your final structure captures the connectivity of the original object, especially when the data is noisy and ambiguous. And if you can prove anything, right, about, if I have this many samples, it's dense, if I satisfy this density criteria, then our output would have certain properties. So I think there is already sort of learning-based method going in there. The challenge, again, I think for most of them is with ensuring the correct connectivity or topology. And that part is still a challenging aspect to putting the learning pipeline.
Yeah, I agree. Okay, there is a nice question on the Zoom chat, and this is nice because it connects nicely with the next talk. Yep. So let's go through that one. So the question is, in contouring in general, in everything you've been working on, talking about, do you think there could be an advantage of using higher order surfaces, for example, spline, and these could go even in the direction of ensuring CK continuity of your surface?
Yeah, I think it depends on what you want to contour, I think. So for large biomedical volumes, right? And I think there the biggest concern is performance rather than the quality of the surfaces, right? Now, but I think there are cases where the higher order surfaces would become beneficial, especially if you're trying to compute the contour of a man-made shape, which we know is smooth, right? And we would like to have the surfaces that conforms to those smoothness. I think that's where it really become beneficial to come up with a smoother representation. So I think it probably not so much in biomedicine, but actually this is a really important point for engineering when your objects are sort of man-made structures and have some inherent smoothness that you want to reproduce.
So you're saying that in natural object there is less smoothness than man-made object?
No, the natural objects, of course, are have certain smoothness, but once they're encoded in biometric images, right, you lose that smoothness because of all the issues with the images themselves. for example, like resolution issues, contrast issues, and noise. It will be interesting though, right? If you can, I guess maybe this connects to learning again, is to how to recognize that the smoother components, right, despite the little bit of noise in images, and capture those smooth components using higher order surfaces. So it's more of a, I think it's a combination of recognition problem, right, with a representation. It's not, you probably don't want to solve them independently from each other. So, and one of the interesting questions, that there were a lot of work on in binary pictures is how to recognize planes and lines from pixels or voxels. So those are called digital lines and digital planes. Turns out to be a really hard number theory problem. But then again, those approaches are trying to find perfect digital lines and digital planes. But now if you're putting ambiguity and noise and allow high order sort of representations and parametric surfaces, it will become, you'll change the nature of the problem, but it will be interesting to go in the direction too.
Cool. Yeah. Thank you. Yeah, I didn't thought at all about that. Thank you. Yeah, I think this is really a good way to connect to the next talk, on next and last talk by Daniele, who's gonna talk about higher order meshes and higher order meshing.
Hello, everyone. Can you hear me, Teseo? Is the audio working?
Yeah, and the video is a bit laggy, but the audio is great.
Okay. Hello, everyone. Thank you for inviting me to give a course in the SGP summer school. Every year, I always look forward to this event and all the talks in this school. So today, I would like to keep this an interactive talk, so I encourage the audience to participate. And my goal is to give an overview of, first of all, why are we interested in using higher order meshing? And then a brief overview of what is the state of the art and the main algorithms that are used for solving this problem. So feel free to interrupt me at any time, either with questions on the chat or on Discord. A few words about me. I'm co-leading together with Dennis Zoring a group at New York University, which is called the Geometric Computing Lab. And many of the images, at least, that you see in these talks are taken from papers that are realized by the group. And many of these works are also in collaboration with Teseo. So before I get into the more details on why do we want high order meshes, I would like to spend a few words on clarifying why do we need a mesh at all. During these last couple of days, we saw that meshes are one way of representing 3D geometry, but it's not the only one. We saw that there are implicit representations, there are representations that only use points. And depending on the application that you're trying to tackle, you might want to use different kind of representations. The reason for using a mesh is that for situations where you need to simulate how, for example, lights, like a physical phenomena, like how light distributes or how objects deform, meshes are just very well established. There are lots of methods that can use a mesh. And the advantage of them over auto representation is that they give you a very explicit way of knowing, for example, what is inside or outside of your shape, or they have an explicit way of telling you what is the boundary of a shape. So what this does is that it makes it easier to set up certain simulations. So to be a bit more precise, it's the standard de facto for rendering geometry is to use a mesh. Like no matter if you use rasterization, where you really have to have a mesh, or if you do ray tracing, it's very common to represent geometries with explicit meshes. Another thing that you can do with them is to use them. They are very commonly used for structural analysis, where you have some object, you have some boundary conditions, for example, forces that are applied to this object. And what you're trying to figure out is how will the object deform, and is there a chance of this object to be damaged? And in general, it's a useful tool for designing mechanical structures. Fluid simulation is another topic which is very common both in graphics for the purpose of realizing scenes that contain fluid, or usually interaction between fluids and solids, or in engineering where the goal is usually to understand, for example, what is the drag on this airplane, or anyhow inform the design. An example where specifically it's very useful to have meshes, so have explicit representation of boundary, is in any problem where you're interested in knowing when objects gets into contact. For example, in this simulation of a car crash, where this can be used, for example, to inform how to change the chassis of the car to better absorb the impact. While it's all possible to do this, even if you don't have a mesh and you don't use an explicit representation of a boundary, this becomes harder because, for example, contact is usually defined by measuring some sort of distance between the object as they move through time. Okay, so now that we have clear why do we want meshes, and the two things to keep in mind are either for rendering or for doing some sort of physical simulation. We can move to the main topic of today's talk, which is high order. And the first thing that we're going to cover is what does it actually mean, because it's something that you might have heard already before, but it actually can be used to mean two quite different things. And so the first thing that I would like to clarify is what do we mean by higher order mesh, so that from now on, then we can know precisely what we are talking about. And the first case, and this keyword is going to become more clear later on when we do a brief introduction on finite elements, is that a mesh is higher order when its geometric map is higher order. So let's first get like an intuition of what the geometric map is. And for this, let's take an application from a very famous paper from Adobe, which is called diffusion curves, that many of you are probably aware of. And the idea here of this paper is that to draw a vector, to draw to the images, instead of using the traditional approach of explicitly defining polygons and then saying how these polygons are filled with color, another way you can solve this is by instead drawing a set of curves that you're seeing here, and then specifying what colors do you want on the two sides of each one of these curves. Then after this is specified, what you can do is solve a PDE to compute how the colors diffuse. And this is what has been introduced in this paper. So in this specific case, the artists usually draw curves that are, well, not piecewise linear. They're actually curves. Usually they're cubic. And so one interesting thing here is that it would be nice for the purpose of representing these curves and still being able to do computation on this domain, to be able to represent these curves exactly. So instead of having to use a mesh that has edges that are straight, you might want to use a mesh that has edges that are curved, so that we can conform to the input that is provided by the user. And this is an example comparing a linear mesh and a curved mesh that have exactly the same number of vertices. So what you see here is that the curve mesh allows you to better approximate these curves that the user provided. And so it generates a result that looks better because there is less error in approximating these curves. But the interesting thing here is that if you use the finite element method for solving this PDE and computing these interpolated colors, the cost, it's mainly depending on how many degrees of freedom you have. So in this case here, using a mesh that is curved or one that is piecewise linear, it really doesn't make much of a difference. The difference is like 2–3% in running time. So what you see here is that in this specific case, having a higher order mesh allows you to get a result that looks better in more or less the same amount of time as a linear mesh. And so this is going to be one of the things to really keep in mind, is that I am not aware of any application that actually requires you to use a higher order mesh. You can always use a piecewise linear approximation of it and just use a denser one to get the accuracy that you want. The advantage of using these higher order meshes is that they allow you to get the same result with less computation. So this is something that it's important to always keep in mind. We are trying to be more judicious in how we invest our degrees of freedom so that we get more for the same amount of computation. Another example, this is another popular paper called Reproducibility that was presented at Eurographics a few years ago. And in this case, the goal is to create these inflated shapes. And this is also done similarly to the one before by solving a Poisson equation on top of a domain. And in this case here, you can clearly see that similarly to before, we have more or less the same number of degrees, actually, it's not exactly the same number of degrees of freedom on the left and on the right, but the result using a curved mesh has much higher quality. In particular, you can see these in the specular highlights that are much nicer and smoother in the middle than on the one on the right. And so also in this case, the computing the solution of this problem, which is the height of this height field, is actually the same or very close, 2–3% difference in running time between the two. Here is an example from simulation of fluids. This is solving the Stokes equation on this grid that has multiple holes. And what you can see here, this is the result that we get using a very coarse curved mesh. You can see in here that there are very few elements that are used to approximate every one of these circles. And as you expect here we are looking at the magnitude of the velocities, and the isoline of these are, as you expect, regular and symmetric. If you switch to a linear mesh, where the approximation of these circles is not as good as before, you now start to see strange things. For example, this isoline here, it's stopping. And this break of symmetry is really coming from the fact that the approximation is worse. So if we switch back to a curved one, we get a much more symmetric result, again, for the same cost. A final one is for elasticity, and here we're doing something slightly different. So instead of comparing two meshes, one that has curved edges and one that has linear one but have the same number of degrees of freedom, now we're going to try to do something else. We're going to start by taking a mesh that is curved and computing a solution, and then we're going to try to get another result that is as close as possible to the curved one, but using a mesh that is linear. And then we compare how much time do we need for both. And it turns out that there is a big difference. It's impossible to give you like a number that always holds, because it depends on the problem and on the PE and on the level of accuracy that you care about. But just to have a number in mind, depending on the problem, you might get 1 to 2 order of magnitude speed up for the same accuracy by switching to a curved mesh. This is particularly relevant, is what you care about, is what's happening around the boundary, where the approximation is much better if you use a curved mesh. Another problem, another way of looking at this is that you don't necessarily need to have a curved geometry. It's also, in the case where you want to compute a solution to your simulation problem and you don't care about having very high accuracy, what you might want to do is to try to use this extra flexibility that you have in your edges that now don't need to be straight but can bend to approximate a given geometry with a smaller number of elements. So this is what is usually called computing a reduced model. And here is an example. We start from a very dense piecewise linear mesh that you see on the left. And then we can convert these. If we have a way of converting these into a coarser mesh where the edges are curved, the fact that we can curve the edges allow us to be much coarser than using a piecewise linear mesh for the same error. And so also here, if your goal is to speed up a simulation, you can use these as a way to reduce the number of degrees of freedom without introducing too much error on the boundary. So all of these examples, what they have in common is that we are using this curved mesh to better approximate the boundary of our geometry. So this is one kind of higher order meshes. When you talk about higher order meshes, there is another kind which comes from the fact that you might want to run a simulation that is, for example, computing displacement of like this, figuring out how an object deforms when some forces are applied. But now the mesh might be linear to start from, but when you apply the displacement to look at what's happening in your simulation, the mesh becomes curved after the displacement is applied. And so this is an example of this. This is just a thin sheet of material, of an elastic material. And what's happening here is that we are just folding in to get some interesting folds appearing. And what we are comparing is a simulation with a very coarse linear set of bases used to represent the displacement. This is what is P1. Then we have a reference solution, which is computed with a very dense mesh using linear basis, which is one in the middle. And then we have one more on the right, which is another solution. This time is computed using quadratic basis. So the important thing to note here is that the geometry is always perfect in all three cases. This is just a box to start with, so you don't need to use higher order meshes, and we're actually not using higher order meshes here. What we are doing is that when we run the simulation only for the case on the right, we are using bases that are high order for computing the displacement, which is telling us how the object deforms from one frame to the next. So when we apply this displacement onto a mesh that is linear, we're getting a mesh which is curved. And so, but this kind of problem introduces a completely different set of issues, because we don't need to generate a mesh that is curved. The mesh is just linear to start with. It just becomes coarse, it becomes curved later on. Okay, so I hope this difference is clear. Let's take a look at what do we get here in terms of, again, performance. And so what we see is that the linear solution with a coarse mesh is very fast, but it's also very far from the result that we expect. The reference solution is something that we can always do, always using linear elements. We don't have to switch to curved one to get an accurate result, but it takes a long time. And so in this case, using these elements which have higher order for displacement allow us to get the same similar result, but for a much smaller time budget. Okay, so here meshes become curved after we apply the displacement, but the goal is the same. We are using these higher order bases because we want to compute a solution that is more accurate with a smaller time budget. So here the goal also is we want to use these higher order bases for improving runtime. Okay. The two things are not exclusive. So what we are looking at here is a mesh that was curved in the beginning. It has been generated as a curved mesh. And then when we simulate, we are applying a displacement, but it's also higher order. And that's also possible. And the output is, of course, a mesh that is higher order. And in this case, we might benefit from both of these higher order feature at the same time. In one hand, we can use less elements to have a better approximation of the input geometry. And at the same time, we can use higher order basis to get a better approximation of the physics. So from now on, I'm going to try to always make a big distinction between which one of these two cases we are considering. So takeaway, you can curve a mesh to better capture the geometry. A mesh might become curved after you apply a high order displacement, or both of them at the same time. Okay, so if you have any question, just feel free to write in the chat or on Discord. So what I would like to do next is spend like 10-15 minutes to give you a very basic introduction to the finite element method, which is one of the main reasons for using higher order meshes. And what I would like to do here is to give you a very basic introduction just in 1D, only for the purpose of making clear what do we mean when we talk about geometric map or basis order. And if you're interested in this, I recommend you to finish this tutorial that continues at the URL that you can see on this slide. In this talk, I'm really going to cover only the first few slides. So the problem that we're going to look at, it's very similar to the diffusion curves that we saw in one of the examples. But instead of trying to solve them on a 2D plane, we're going to just work on a 1D domain. So we have a 1D domain, and we have some boundary conditions, so some values that our function needs to have at the two extrema. Let's say that it has to be 0 here and 1 at the end of the interval. And what we're trying to do is to solve the Laplace equation. So we want that the second derivative of our function are 0 all over the domain. So you probably already know what is the answer to this. For these specific boundary conditions, what we're going to get is a line which is connecting the two. And you can compute this analytically. But what we're going to figure out here is how can we have a method that allow us to solve in a numerical way also equations that are more complex than this one, and also work in 2D or in 3D. So the setup is that we have our equation, we have a set of boundary conditions. These are the values that we are setting at the two extrema. What we want to do is develop this method for solving this. So one approach, which is what is usually used for finite elements, is to convert the problem for the strong form, which is this standard form of our PDE that says that this condition is to hold on every point of the domain, to a more relaxed definition, which is called the weak form, where instead of asking this to hold pointwise, we are asking this to hold in an averaged way. So when we take an integral over the domain omega, which in our case is just a 1D segment. And so what we're going to do here is we're going to ask that this equation hold, where we take our original strong form and we multiply it by a set of test functions. And these test functions can be anything as long as they are picked from a specific space of functions. So under a set of conditions that I'm not going to cover today, you can show that if you find a solution for this weak form, this is also going to be a solution for the original PDE. The advantage of this weak form is that now allow us to write down a problem that we can solve numerically. So the first thing that we do is to use integration by part to rewrite our weak form, getting rid of the second derivative and converting them into two gradients. When we do this, we get with this definite integral here, which disappears. And the reason why it disappears is because we can carefully pick our test function in such a way that this term vanishes. It's more of a technical detail that is not so important for this talk. What we end up with is this final weak form. So what we need to be able to do to solve this is to take an integral over our domain, and we need to be able to take gradients of u, which is the function that we're trying to find, and v, which are the test functions. So the second step is that we now need to have a way to represent our function. So we want to have a way to represent functions inside our 1D domain. And one way of doing it, which is to discretize them using a set of element bases. So the idea is that we're going to pick a few points on this domain, and for every one of these points, we're going to have a number attached to them that we call u. So for example, this can be u0, this can be u1, this can be u2, and so on. Then we're going to have a set of basis functions. Let me change color. So for every one of these points, we're going to have a set of basis functions. For example, for u1, we're going to have a basis function that we call v1, which is simply a add function. It's 1 on u1, and it becomes smaller as you go further away. Now we have this discrete representation of functions. We can define new functions u of x by taking a set of coefficients ui. And now by changing these coefficients ui, we can get different functions defined over the entire domain. So these bases are one of a part of this whole discussion, but we can change. So instead of using this basis, which is linear, we can use bases that are curved. We can put in there whatever polynomial of arbitrary degree that we like, and it doesn't even need to be necessarily a polynomial. Okay, so let's take this definition of our function u, we plug it into our weak form, and we actually do exactly the same for our test functions. So when we do this, our problem that was a problem that was not possible to solve numerically before, it actually becomes into a linear system of equation for this specific PDE. And so this can be rewritten in this form, where now this becomes a linear system solve that you can solve numerically. One of the interesting things here is that it turns out that if you change the degree of a basis, this set of equations will still be possible to solve as a linear system. There are other parts that becomes more complex, but it still stays a linear system for this specific case. Okay, so we now know what bases are. It's a tool that we use to represent discrete functions on top of, in this case, a 1D interval, but the same construction can be applied to triangles, to tetrahedra, to cubes, or other ways that we have to partition space. There is also, if you're interested in more details on these, the tutorial that I'm following actually comes with a complete implementation of a 1D solver for the Poisson equation, and the solver also shows you how to use higher order bases. So I strongly encourage you to take a look at this tutorial and run the Jupyter notebooks and to understand better what is going on. Okay, so the next part is that now we have this discrete version of our problem, but the integral that we need to take is still taken over the entire domain. So for every one of the degrees of freedom ui, we need to take an integral over the entire domain. So this is unnecessary because, as you can see from this picture in here, the bases that are attached to 1 degree of freedom only cover a certain part of the domain. They don't cover everything. So what we would like to do is to have a way to rewrite this expression to make this clear. And so write these integrals not over the entire domain, but only over one of our elements. And so what the difficulty that comes in here is that now we need to have some way of defining our basis on a canonical element. And then after we have the basis defined on this canonical element, we need to take it and map it to a specific element that we have in our mesh. So let's start by defining this canonical element, and let's start in 1D so that we have just one single segment. So we have one single segment that is in here, and now we need to have a way to interpolate the values that are attached to the beginning and to the end of our segment. And if we use linear function, these two lines are representing the basis for this single element. If we go back for a second and we look at this picture again, you can see that what this is just taking these two functions and copying them over every single element into this domain. Now, so now we have this canonical element, which we can decide once and for all that has a length of 1. It goes from 0 to 1. But now, when we take our actual domain, where we want to solve our Poisson problem, whenever we divide these into multiple parts, we don't have to necessarily make all these segments the same. Maybe there is something more interesting going on in some region, and we want to have denser, shorter segments so that we have more degrees of freedom in that area. So if that's the case, then now you see that we need to somehow map the basis that we have on our canonical elements to make it fit in here. So how do we do this? Well, the obvious thing is that we are just going to take this longer segment, we are going to translate it where it should be, and then we scale it down. Okay, so we're going to do a linear transformation to map this canonical segment onto one of the finite elements. So in this case here, every one of these segments is a finite element, and the element in the bottom is our canonical domain. So now this map, which is taking the canonical domain and is telling us how to take the bases that are defined on this canonical domain onto one of the elements, is called the geometric map. In the case of this example that we have, a geometric map G is pretty simple. It's just a translation and a scaling, but it can be more. And actually here, there is absolutely no restriction here in having this transformation to be linear. You can also have it higher order. And having the higher order geometric map, what allows you to do is allows you to go from triangle, the canonical triangle, but usually it's drawn in this way. And you can now map the canonical triangle that contains bases into some more interesting curved element. So that if your boundary is curved, you can actually use this map to better approximate the domain of your geometry. Okay, so here you're going to have like additional elements around. You can think of this as a triangle mesh, and we are just looking at one specific element. So you can see here that now every element will have its own geometric map. Whenever we work with triangle meshes, it's very common to not think about this because you just have a linear transformation that is telling you how to take a canonical domain and map it to an element on your mesh. But even there is a transformation happening. It's just linear. Okay. So let's take a summary of what we have here. So let's use a triangle mesh as an example. So we have a canonical domain, and then we have a geometric map, which is mapping it to another one, which can be curved. And then in addition to this, inside the canonical domain, we need to have a way to interpolate the physical quantities of interest that are usually defined on a set of nodes that can be on the boundary, but can also be inside. And so this map that is doing the interpolation and defining these bases inside a triangle can also be high order. Okay, so equipped with this, if you want to know more about finite elements, I encourage you to continue the tutorial, but now we have enough to actually talk about higher order meshing. So the next thing that we need to talk about is what kind of functions do we use to represent both the basis and the geometric map G. And usually the type of spaces that you can use for this function is the same. So there are a set of options that you can pick, and then you can use them either as bases or to define the geometric map. And the two things are completely disjoint, so you can have linear geometry and higher order basis, or you can have higher order basis and linear geometry, and you are free to pick and choose whatever you need for a specific problem. So there are many, many options. And if you're interested in these, there is this article, and all the elements that you see here are implemented in a software called Phoenix that gives you a very broad overview of elements that are commonly used for the finite element method. I don't want to go over all of these, but I just want to give you like a short explanation of what every one of these elements is. So at the end of the day, for every element, you have a set of degrees of freedom. In the case of a single triangle, let's use the single triangle because it's easier. And now, depending on the element that you pick, you're going to have a set of basis function. Here, every basis function is attached to one of the degrees of freedom. Now, the way you use this function is that now you can define the value of the interpolated quantities in any point P, which is defined by a pair of barycentric coordinates inside the canonical elements. And the value at P is computed by interpolating, by taking a combination of the values attached to the nodes. The way you do this is that the value at P is defined as the sum over, in this case, our three nodes of the value at the node, let's call it U0, and then this is multiplied by whatever basis you have evaluated at the barycentric coordinate that you're interested in. So this is P. There we go. So now you can use this set of rules to interpolate values. And as you go to more complex element, you get more complex rules. But at the end of the day, the formula is always the same. It's just that in the case of a linear triangle, all the bases are linear. If you go to a quadrilateral element, now the bases are not linear anymore. They are actually bilinear. And if you go to a quadratic quadrilateral element, you have something interesting that is starting to happen, which is not anymore that your value needs to live on the nodes of your element, but they can actually be also on the edges, or they can also be inside. Okay, and of course the basis gets more and more complex. We continue with these, and as you go to, for example, quadratic hexahedra, you see that the bases are very complicated. Okay, I don't want to go into the details of how you construct this, but the purpose here is that you see that, like, for a single element, if you have a lot of nodes, this is going to give you additional degrees of freedom, so you can represent in there more interesting set of functions. So you have always this option. You either increase the degree of a basis to get more points in there, or you take the element, you split it into smaller one, and you get more degrees of freedom. Okay, the focus of today is going to be on these methods that are actually increasing the degree of a polynomial to give you additional degrees of freedom. There is one more huge family of bases, which is the use of spline, usually B-spline or NURBS, as basis for both finite element or for representing your geometry. If you're interested in these, I recommend to read the original article from Hughes, Cottrell, and Bazilev on isogeometric analysis that describes in details how to use this kind of basis for analysis, and then how to use them also to directly represent the geometry. Okay, so now that we have an idea of what it means for a mesh to be higher order and what can we use them for, let's take a look at what are the properties and operations that we want to be able to do on these meshes, depending on what we're trying to do with. So the first group is going to be what properties and operation do we have if we want to use the higher order property to better represent the geometry. So if a geometric map is higher order. And in this case, there are going to be two things that we're going to cover. One is avoiding elements to overlap. And the other one is that we want to have ways of computing distances between these curved boundaries. Another very disjoint set of issues is if you're now using these higher order polynomials as basis for your finite element method. In this case, the thing that you need to be able to do are you need to be able to take integrals on this higher order polynomial on top of on the area or volume of the element that you're interested in. And then you need to have this property that the Jacobian has to be positive, which is something that it's quite tricky. So let's start from collision detection. So the question here is, if you have curved boundaries, and if these curved boundaries are moving, let's say that you have one here, and then you have another one of another color moving in the other direction, the question is, do they ever touch? Or you might have an object that it's already curved, and then as it deforms, at some point it starts to overlap. So the question is, can we detect when this happens, and then eventually we might be interested in figuring out how to react to this. So this is a problem that has been very heavily studied for linear element and is still under active research for linear elements. This is usually called collision detection or continuous collision detection or static collision detection. Interestingly, while it's still under heavy study for linear elements, this is something that you absolutely need if you want to you need to extend it to higher order if you want to use higher order meshes with a higher order geometric map. So unfortunately, there is very little solutions that allows you to do this. A recent one that we proposed last year is to reduce the problem of collision detection between higher order trajectories in this case to a set of linear problems. But this is only conservative, and it's also quite expensive. So in general, having a good way of detecting collision or detecting overlaps between higher order, between meshes that use a higher order geometric map is an open problem, which I think is a very exciting one, and one that will need to be solved if this kind of meshes will want to be used as an alternative to linear one. Of course, this doesn't apply to every single problem, but problems that involve collisions usually require you to have this primitive. Another one is computing distances. This is something that has been quite heavily studied for the case of splines, computing distances between spline surfaces. The case of using elements that are only C0 at the interface, like the one that we looked at before, should be easier, but not much easier. And there is a lot of work in this direction, but unfortunately, I'm not aware of any paper that actually, any algorithm that actually allows you to get a reliable, conservative solution to this problem, especially if you consider floating point arithmetic errors that are introduced. So that's yet another big problem. How do people solve this? Well, a typical solution is that you have your curved surface or line, and then what you do is that you decide that for the purpose of computing distances, you don't use the actual curve geometry, but what you do is that you sample the surface in a few points and you approximate it using a piecewise linear approximation. While this is a very practical solution, it's very inelegant because we just lost all our ability to better represent the boundary, but this is a very typical solution that is used right now in systems that use higher order meshes. So again, this has to do with using these for the purpose of better approximating the boundary using an higher order geometric map. Let's move on to using higher order bases to represent the physical quantity of interest. So in this case, the main feature that we're interested in is being able to compute integrals. You probably remember from the quick introduction to the finite element method that we looked at that we cared about taking integrals on top of our elements. So the good news here is that if your function space is polynomial, there is a lot of work and a lot of solutions that you can use for this problem. And so you can actually integrate exactly polynomials up to degree like 50 or so. And there are readily available algorithms that allows you to do this. One project that's on GitHub and I absolutely love is QuadPy, which is a collection of most of the papers that are dealing with this problem. And so the author of this package collected all of these and made them available in a very simple format to use. You can just pick the element, pick the degree, and then the code directly either compute the integral for you or gives you a table of integration points and weights. So if you never looked at this before, strongly encourage you to take a look. This is an amazing piece of software. Okay, so this was one thing. Then the other thing is that if we are interested in computing higher order displacement and we want to use this to deform our mesh, then one of the things that might happen is that our elements will change shape. This is what we are trying to do. But in particular, might have zero area or zero volume, or even worse, they might completely flip. And this is something that we want to avoid, because if we have a certain domain and we tessellate it with elements, for example, with two triangles, as long as the two triangles are not flipped, or like the map that goes from the canonical element to them is as positive determinant everywhere, then we are sure that these elements don't flip, so that we are sure that these elements are not gonna like leak outside of the domain, or you cover the same part of a mesh multiple times. So that's an essential property to have. And in the case of linear elements, so in the case of just taking a triangle and mapping it to another triangle on the plane, it has been extensively studied. If you never look at it, there is a seminal paper from Jonathan Shuchak that you can access here, where he studied in detail the issue of figuring out if a triangle flip, or equivalently, if you are given 2 points A and B, the question is another point C on the left or on the right with respect to the segment defined by A and B. So this sounds like a very trivial problem to solve. You can just take a cross product, but it turns out to not be easy at all. If you actually want to have an answer which is correct and you do your computation with floating point numbers, this is really, really not easy. So I encourage you to take a look at the paper for all the details on how to do this. But it is possible to solve. So for the case of this specific problem, you want the Jacobian of this geometric map to be positive everywhere. But since the map is linear, its Jacobian is going to be constant, and so this check only needs to be done on one point, and then this is going to hold for the entire domain. Unfortunately, this is not true when you have a geometric map which is not linear. So if you now go from a linear triangle to a curved one, now the determinant of a Jacobian will be different depending on which point you are evaluating it. And so figuring out if for any point inside your triangle the Jacobian is positive, it's a highly non-trivial problem. And it's an essential one, because without this property, you cannot be sure that, for example, your domain is going to be properly discretized after you apply the deformation. So there is a lot of work on these. One of the latest paper that I'm aware of is this one here from Joe and Remakol and Gazain. And they have a construction that allows you to do this check, but it's only guaranteed to work in infinite precision, and there might be an arbitrary number of recursive subdivisions that you need to do. So surprisingly, this quite simple problem statement does not currently have, at least as far as I am aware, a convincing solution. So that's another like neat problem that you might want to look at, and having a solution to these, especially if it's a solution that can be evaluated efficiently and using standard floating point arithmetic, would be something that will have a huge impact in using these sort of meshes for many of the problems that are of interest in engineering, in geometry processing, in graphics. Okay, and so in this case, this does apply both whenever you're looking at using curved geometric maps, but it also applies to the case of using higher order basis for representing displacement. Okay, so now you have I think a pretty clear idea of what is higher order mesh, what do we use it for, what are the properties that we need. So now, what are the challenges in generating these meshes, and how can we generate these meshes? So one first comment is that linear meshing is already something that is very difficult to do. The typical example that I like to bring up is that if you have two segments on a plane and you're trying to compute the intersection of the two segments, this is already a very difficult problem to do in floating point, because you're never going to get the point exactly there, but it's always going to be a little bit off. So some trivial properties like this segment is parallel to the other part of the same segment in general is not going to be true if you do computation in floating point, which is very annoying. But in addition to these, one of the challenges and one of the reasons why if we could not have a mesh, our life would be much easier, is that there are a lot of other issues that can come with this. For example, whenever you have a mesh, you might have problems with it. So for example, it might not very clearly identify what is inside or outside. That mesh looks quite nice, but if you actually zoom in, you see that there are a lot of ugly things happening in here. And so dealing with this sort of input, it's very difficult already if you want to try to generate linear meshes. If you want to do things higher order, you have to solve all these issues and some more. One thing that I find it surprising is that I thought that at least for 2D problems where people specify curves by hand, for example, drawing them in Illustrator, this will not be an issue. But it turns out that it is. So even for drawings that are created by hand, software usually don't check for basic things like if things intersect or slightly touch and so on. So these are some model randomly picked from a collection of SVGs that I found online. Even in this case, we don't really get clean collection of curves. These are just some random example taken from that data set. And one that I particularly like is this one, which is the SIGGRAPH logo. It's something that probably many of you looked at many times. And you might not have noticed that if you actually look carefully, it's really broken. And if you download the official logo from the website and you look at it carefully, you see that you see like these different colors that are not exactly touching. There are some small overlap. There is a gap appearing in here. And I mean, sure, these things are like kind of small, so you don't notice them immediately, but they are there. So what we would like to have is some methods that are able to deal with this. And we want to, at the end of the day, to generate these meshes to solve some problems in there. And so here you are always faced with this issue, like you either figure out a way to generate a mesh and then it's easier to simulate, or you try to avoid the mesh entirely. Our goal today is to talk about how to generate meshes, just because this is the most popular tool that it's used right now. So these are just some results of the sort of things that we would like to get. So we would like to get meshes where most of the edges are straight, but then the ones that are close to the boundary or close to some of these feature line are curved. Okay, so what happens when we go to 3D? So up to now, we only look at 2D results. Are things easier in 3D? And the answer is unfortunately not. Whenever you work with 3D models, there has been like a decision that was made many years ago in the CAD, both industry and research, that is to try to represent shapes using NURBS surfaces. These are curves that are defined by a specific family of rational polynomials. So the issues with this representation, which is something that many of you, especially if you look at this for the first time, you might not be aware of, is that, I mean, if you look at these closely, it looks fine, right? Everything in here, it's very nicely touching, all the surfaces are perfectly touching. But it's not, it's a bit deceiving, because that's not the case in the actual format that is used to represent all of this. And the challenge for this is coming from this decision that has been made a long time ago, which is you have surfaces, and every surface is represented by a polynomial. Let's say that this is a NURB of degree 3. And now you can have another one. Let's change color just to keep it more clear. We have now another surface here, which is intersecting the one that we have here. And so the two surfaces intersect into a curve. I'm going to use the color green for the curve. And so one of the basic problems that you have to solve if you want to work with higher order surfaces is, I give you two surfaces and they intersect, find me a representation of a curve intersecting that at the intersection. And the unfortunate reality of using NURBS to approximate surfaces is that their intersection is a NURB, but it's a NURB of potentially much higher order. So it can be like maybe like order 50 or order 60. So while it's possible to represent this curve as a NURB, this will become quickly, it will go out of hand, because the more operations you do, the higher is the degree of a NURB, and it becomes very expensive to compute this, and also numerically unstable. So the decision that is ubiquitous in modeling higher order surfaces in CAD software is to not use the proper degree, but to use always the same. So for example, 3. So what they do is they compute this intersection and then they try to approximate it with a NURBS of lower degree. And this is a nightmare, because now essentially every intersection between two surfaces is not going to be completely right, but it's going to be right up to certain geometric tolerance. And then when you use a software like Parasolid, when all of this is processed, the software is able to handle this uncertainty in every connection and is stitching them together before they show it or do any other operation. So this leads to a very difficult problem, because the actual geometry is not really known. The geometry of a higher order surface processed by a CAD software is whatever the Parasolid kernel or the geometric kernel that is being used produces, which is a definition that relies on an algorithm which is not public. And so it's very hard to do anything in there. So this is the unfortunate situation of dealing with this sort of higher order models, is that even loading them or knowing what they are, it's difficult. So for the talk today, we are mostly going to focus on 2D, where at least it's more clear to know what it means to have a higher order input. Okay, so I would like to go over three approaches that are more modern. But before, I would like to talk about the most standard way that has been used in the last 20 years or so to generate higher order meshes. So the idea is usually to generate a linear mesh, and then you take this linear mesh and you somehow curve it to match the boundary that is curved. So the problem with this is that if you do it blindly, you might get a lot of problems. You might get element that intersects, you might get Jacobians that is not positive, and so on. So we're gonna skip over the large literature that is doing this, and we're gonna move on to more modern methods where there are extra checks on these, which are added to make sure that things don't, that the meshes stay valid and they stay usable. So I'm going to cover three methods. One that is called Bézier guarding, which is focusing on reproducing exactly a set of 2D curves. And it has strong guarantees on the bijectivity or on the injectivity of a map inside every element. Then I'm going to talk about a second method, also for 2D, but this one is actually purportedly not representing the input exactly, but it's allowing it to vary a bit for the purpose of automatically healing small imperfections that might be in the input. And then finally, I'm going to talk about an approach for doing higher order meshing in 3D. But here, the input is not going to be a curved surface, as in the other two cases, but the input is going to be a dense linear mesh that we want to approximate with a set of higher order elements. So let's start from Bézier guarding. So in this case, I would like to first of all thank Manish and Marcel for providing slides for this part of the talk. And in their work, they take a set of 2D polynomial curves and they fill it with curved elements. So we want to generate an higher order mesh where the geometric map is higher order. And they want to do this exactly conforming to the input curves. They want to allow arbitrary polynomial triangle elements of arbitrary order, have guarantees on injectivity of every element, and supporting arbitrary order. So the approach works in this way. It starts by taking every segment, every curved input, and protecting it, guarding it with a polygon, which is constructed around it. So you see that the side of a polygon that is not touching the curve are straight. And in the case you have more curves, you can just add more of these polygons. And so you see that a crucial property of these polygons is that they never overlap. They touch on the side, but they never overlap. So after this is done, the method actually provides already a way to generate guaranteed to be valid elements for every one of the curved triangles that you see in here. And then the rest can simply be filled with standard linear elements. And in 2D, meshing with a fixed boundary, it's a solved problem. Okay, so what are the contributions of this paper? First of all, they observe that it's always possible to envelop a curve with a valid polynomial map. So in this case, they show that if you change the curve, you can construct these guarding polygon. And as you change the guarding polygon, the curve changes. But this works also on the other way around. So if you have any curve, and if you change the curve, you can always construct a polygon that is protecting it. In some cases, whenever the polygon becomes too large, you might have to split it. But it's guaranteed that no matter what, you can always find a set of these polygons which is protecting the curve. And every one of them, for property number 1, will have a valid polynomial map inside. Then the last piece, which is crucial, is that if you have different protecting polygons and they start to overlap, then you can always refine it. You can always bisect it to get smaller ones. And so the combination of all these three properties gives us a very elegant algorithm for solving this problem with guarantees. So the algorithm is you take a set of curves and you try to protect them. So if you can't, because they overlap, you split it further and you continue doing it until they don't overlap anymore. After this is done, you fill in the rest with linear elements. So the algorithm is very elegant. it's after you have this basic tool, it's simple to implement, and it has strong guarantees on what you get. So these are some results. This is an example on a puzzle piece. And they also tested it on a large collection of SVGs in the open clipart dataset. These are just some collection of some of the more difficult models. There is a lot of work done by Marcel's group on this algorithm, and I encourage you to take a look. So the goal of all this work is to mesh planar domain with strong guarantees on injectivity and conforming to the input and working for arbitrary polynomial orders. So the work I just briefly mentioned has been published in 2020, and there are author follow-ups, for example, to deal with having better quality, actually guaranteed quality, and also using rational computation to guarantee the generation of these, avoiding issues that are related to floating point rounding. This is a paper that actually is going to be presented at SGP later in the next week. Okay, so this was the first method. And the assumption there is that you have a set of curves that you want to preserve exactly. The second method is called tree-wild, is trying to solve a different problem and a way less well-posed problem. So it's trying to take a set of curves and assuming that the curves are probably not going to be what the user meant. This means that there might be like curves that are too close or something that is overlapping in strange ways, and preserving them exactly will lead to probably not the result that you want, because you might have degenerate elements or a lot of elements. And so the question here is, can we have some way to filter this out to generate a mesh that is suitable for finite element simulation? So the idea of this paper is to start by taking the collection of curves and cleaning it up. And then after this is done and we have a clean set of curves, it generates a curved mesh. So this last stage, this method was proposed before all the work that Marcel did. So it will actually be interesting, and the second part of the method could be replaced by what Marcel has been proposing. The advantage of this one is that it allows a bit of slack in approximating even certain of the features that you care about. So it tends to allow you to have coarser models. But of course, it loses the guarantees of being able to represent the input exactly. So in this case, the input is a collection of Bezier curves. And what we're trying to do is to generate a curved triangle mesh that conforms to some important features and approximate the other ones. So the features are first cleaned up by splitting in region of high curvature and also ensuring that there are never two curves that are too close. So there is a certain geometric tolerance that you can specify, and curves that are closer than that are not allowed. So this prevents a lot of the degenerate cases. The corresponding thing that you might think of if you're thinking of a linear mesh is that you might have two triangles that are numerically close. And in that case, trying to fill the gap between two triangles that are numerically close will only lead to disaster. So the only way to handle this is to throw away one of the two. And here it's similar, but it's applied to curves instead of linear elements. So we call this mu separation. So it's a parameter that you can use to control how far these curves are. So after this is done, there is an optimization that generates the mesh. And we base this on an approach that we developed years ago for 3D, but is used more or less vanilla in this paper, but of course, like adapted to 2D, where a lot of things are easier. So it's based on the idea of inserting segment into a background mesh using rational numbers to avoid numerical problems, and then doing an optimization that is taking these coordinates and converting them to a floating point. The approach is incremental. It applies local operation to try to minimize an overall measure of quality of distortion. And after it stops whenever you either reach the desired quality and you manage to round all the vertices to float, or you run out of computation time. So there are some variants in the algorithm to deal with features. For example, we pre-split to make sure that features are not approximated too badly, because otherwise we cannot curve. We have special rules on how to move points around curves, and we also have a way to reproject points onto the curve to minimize the error. At the end, when we have this initial curved mesh, then we do further optimization to try to coarsen it as much as we can while staying within this geometric tolerance. So the key part here is that we need to be able to check for inverted elements, which is something that we do in an approximate way using this paper here. And this is one of the main open problems to solve if you want to do geometric optimization to make sure that elements don't flip. So with these, we now have a method that allows you to specify what is the desired number edge length that you would like to have, and you can get meshes for the same curve at very different resolution while preserving the input curves approximately. So you have some tolerance to decide what you want to drop. One of the advantages of not having to preserve exactly the boundary is that if there are issues with the boundary, for example, what you see here on the left, where there was something happening here, and these are to be preserved, it had to be refined a lot. This is something that we can avoid on our side because these small things can be cleaned up. And so the final mesh has a more uniform size. We can actually control the size. So in this specific case here, both meshes can be used for solving a finite element problem, but the one on the right, it's definitely what you would like to use because it has less degrees of freedom, or I mean, at least like less degrees of freedom in a unwanted region. The problem with a mesh on the left is that you cannot control how many elements you have in this area. Okay, and this has been tested on a large collection. It's the same data set of a previous paper, is this open clipper data set. And so in summary, this method gives you a way to work with input which is imperfect, giving you good meshes that can be used for finite element simulation. Extending this method to 3D should be possible. There is no step in here, but it's not extensible to 3D, but the technical details in doing these are really hard. And so as of today, we still do not know exactly how this could be extended to 3D, but it is a very interesting problem. The main challenge here is also figuring out how to get actual 3D curved data because of these issues of approximation of NURBS intersections that I briefly mentioned before. Okay, so final method. This is quite different from the other two that I presented. This was presented at SIGGRAPH last year. This method is not taking an input that is curved and trying to approximate it, trying to mesh it with a curved mesh, but this method is taking an input which is linear. So it's taking a very dense linear mesh and it's trying to create a reduced model. So it's trying to approximate it with a curved mesh. So the reason to use a curved mesh to approximate it is because if you want to stay within a given tolerance, if you are allowed to bend your elements, then you have a higher chance of being able to use less. Okay, so note here that like going super coarse is not always what you want to do, because depending on the physics that you're trying to solve, you might actually have to refine anyway. But the goal of this is to get the coarsest possible mesh so that at least you have a baseline that you can start to work on if you want to have something quick. And then it's easy to refine after you have these coarse one. So here, the goal is you start from something dense, linear. You want to approximate with a mesh that is coarse and curved, and you want this to work automatically on a large collection of difficult geometries. So the goal is to get meshes that are coarse, where every element is valid, meaning that the determinant of the Jacobian of the geometric map is positive. Absolutely no intersections, because otherwise you cannot use this for simulating any simulation that has contacts. And what we also have is a way to control how much error you have, so that instead of having to specify the resolution of a mesh, which is not particularly interesting, what you can say is, what is the maximal geometrical error that I'm willing to tolerate? And the algorithm is going to try to be as coarse as possible, but while keeping that bound. And it also supports the possibility of preserving existing features, which is something that was discussed in the previous talk. And while it's not necessarily something that you want to preserve for many biomedical applications, for mechanical models, this is crucial. So a few comments on these. So now you know what the geometric map is. And so what we are trying to do here is making sure that they stay valid. But one of the big concern in this paper is that we don't have a way to do this check exactly. So this check in the paper is done in a way that is not guaranteed to be correct. Having a way to do this correctly, I think it would be worth a dedicated paper, and it would be a fantastic problem to tackle. No intersection. So that's an important property, is like no matter how close objects are, we don't want them to intersect. And this is something that right now we do by doing explicit checkings that are slow and expensive. And it would be interesting if there was a better way to do this. The distance bound, it's something that I'm really excited about, because I think it's very unintuitive that whenever you create a mesh, you need to specify how many elements do you want. It's so hard for a human to tell. I think it makes much more sense to just say, I want to have a maximal geometric error of 1 millimeter, do your best. And this is what this argument allows. And finally, if you do have features, you can specify them, and then these features are going to be preserved. But this is a double-edged sword, because if you prescribe features that cannot be preserved, you're going to get bad meshes out. So the method allows you to do things of this sort. So you start from a very dense mesh, and if you now try to remesh it for a given error using only linear elements, in this case, we were able to reduce it to 15,000. But if you use curved elements, you can go down to 2,000. So if your goal is to have as few as possible degrees of freedom, using curved elements pays off a lot. I'm going to give a very, very brief overview of how this works in the remaining minutes that I have. So it's based on a construction which is called shell construction. And the idea is that you can approximate a dense linear mesh with a coarser one, which is a collection of prisms, which is built all around the surface. After you're done with this, inside this prism, it's possible to define a curved mesh only inside the prisms. And similarly to the observation that Marcel used in his paper, here now you see that the boundary inside, the interior boundary here, is actually linear. So we can actually fill it up with linear elements, and then we can optimize the whole thing to get a curved mesh. So the key part here is going from the input to the shell, and from the shell to the curved mesh. So what is the shell? So the shell has been introduced in this paper in 2020, and it's a construction that allows you to take the a certain region of your surface and wrap it around this shell, which is made of tetrahedra. And inside this tetrahedra, there is a special vector field defined. And the special vector field allows you to compute correspondences between different surfaces that are in here. So if you take a point on one surface and now you advect it through this vector field, what you get is that you get a point on the other surface. And if you use the specific vector field defined by the shell, you have a guarantee that this map from one surface to another is a bijection. And so this is a key property that we use to now take a coarse shell and inside it define a curved version of the input, which is trying to be as close as possible to the input. This algorithm, I know I described it at a very, very high level, but I encourage you to take a look at the paper if you want to know more details, allows to process very complex models and gives you reliably coarse approximation which are curved. It's versatile in the sense that you can use it for CAD data after you convert it to a triangle mesh, and you get coarse CAD models that are useful for simulation, or also in this case, you can use them for visualization. You can take like very complex, for example, implicit microstructure, do first a dense marching cube to get a linear mesh, and then you can use this algorithm to convert it to a coarse curved representation. Or you can take a 3D model with a lot of triangles and you convert it to a coarser one with very few that you can, for example, in this case, use for visualization. Okay, so this concludes this quick overview of recent methods, and I would like to give an overview of open problems that I think are important in this field to make these meshes usable, and hopefully this is also going to stimulate some of the discussion in the Q&A. So let's quickly go over these. So the first problem is, I already mentioned it multiple times, how do we check if curved elements actually have positive determinant of a Jacobian? So I encourage you to take a look at this paper. It's a completely open problem, even for simple elements like triangles or tetrahedra that are curved, like Lagrangians, triangle or tetrahedra. There is no method that has guarantees to give you these envatrans in a reasonable time. The method that exists do fail, but they are reasonably reliable that you can actually use them in applications. But I really, really would like to have a way to solve these exactly, and I think it's an exciting problem to look at. A big can of worms is figuring out a way to take Cad representation, which are this like collection of patches, or even worse, like a sequence of operations like filleting or Boolean operations done on primitives that are curved, and convert them to meshes that we can use for simulation or for visualization. So this is very challenging, as essentially the output depends on the geometric kernel that you use, and the geometric kernels are not open source, so it's not even clear what this means exactly. But the idea way to go will be to try to take a subset of one of the reasonable languages and try to convert it into a mesh. This is a very, very hard problem. There are starting to be many data sets of CAD model. For example, there was one introduced today in the Autodesk talk at the beginning of the day. Another one is ABC, which is just a collection of random 1 million CAD models. So on one hand, this is an interesting problem because it has a large practical impact and a lot of data to play with. On the other hand, this is a very, very challenging problem for which a solution has been elusive for at least 30 years, maybe more. And it's a very difficult problem to solve. In some sense, even doing linear meshing of CAD models is already very hard, and there is no reliable solution as far as I know. Another thing which is interesting is that if your goal is to do finite element simulation, it's fine to use elements like this one here that are C0 continuous around elements. So here you can very clearly see that the normals in between the different elements are not continuous. You can see clearly discontinuities in the lighting. So while for the purpose of doing finite element simulation, this does not really matter. The methods converge at whatever rate you expect, even with this zero continuity, at least for some of the more common volumetric PDEs. For the purpose of rendering, you would really like to not have these sort of issues. So one question is like, can you use similar methods to create meshes that are CK continuous using different set of bases? And I think this is possible, and probably the methods are going to be similar. The question is if this is something that is useful for visualization, if it's going to pay off in the end to accelerate visualization. The reason to use higher order meshes for finite element is very clear because they do pay off, at least in certain cases, but for visualization, I just have no idea. And I think it would be an interesting question to actually explore if this is something that would be useful or not. Another open issue in isogeometric analysis is how do you generate meshes whose basis and geometry are splines? And in this case, what the community is trying to do is to get meshes that don't have these C0 discontinuities, so that you can use it for visualization, but they also can be used directly for analysis. So this is a very difficult problem because it requires you to have meshes that are made of X's. And generation of meshes made of X's is already hard. Doing it for higher order element is one more level of difficulty. If you're interested in these, we are looking at this problem in this paper published in CIMAME, where we start from an existing linear mesh and we figure out a way to curve it so that this can then be used for an isogeometric analysis pipeline. But the problem of doing this automatically without having to create by hand the mesh of hexahedra is something that is completely open. And another thing is that I don't exactly know what are the applications in mechanics that require these sort of elements, as in some of the experiments that we did in the group, they seem to perform quite similarly to elements that are only C0 continuous around edges. So identifying exactly what application requires it, it's an interesting problem. And finally, everything that we discussed today was always assuming that we want to generate one mesh and solve something on one mesh, but this is not the case in many real scenarios. For example, here there is this simulation of this mesh. This is a paper from SIGGRAPH in 2010. And what you see here is that there is a huge variation in geometry. And with this large variation in geometry, to keep the quality of the elements reasonable, you actually have to do remeshing on the fly. So as the mesh changes and as the quality changes, you're going to do operations to change the mesh so that you can keep higher quality. And this is what is required in many simulation algorithms. So all of this is already very difficult if you have a linear mesh. And in general, an approach that works reliably for doing remeshing it's still elusive, also for the linear case. But if we're serious about trying to push curved meshes to gain extra performances over linear elements, then this is something that at some point will have to be tackled. And I'm not aware of any work that is directly trying to address this problem for curved meshes in a reliable way. And one final problem, which is one where I think there is a high chance of, but it's very, very difficult to tackle with traditional method. And I think there is a high chance that data-driven methods will be effective at tackling this problem, is the one of feature cleaning or defeaturing of curve models. So I encourage you to read this paper from Sandia to know more about the application and how this method works. But this is the first paper that I'm aware of that is trying to use data-driven methods for this purpose. And so the issue is that whenever you have a CAD model, it can be very complicated. Imagine like you have an airplane, and somewhere there is going to be the full details of the airplane, from like what is the shape of a wing to where do we put bolts, to what is the size of a bolt, what is the geometry of a fillet, and so on. All of this has to be there. But when you try to simulate, for example, like the fluid flow around the wing of an airplane, you really don't want to have all the geometry in there that is telling you where every single bolt is. So the question is, how do you get rid of it? And this is really hard, because this is something that is very heavily dependent on a specific application. And not only these, but some of the inconsistency might even be like small modeling issues that the person that drew the technical drawing did. And so the way it usually works right now is that people go there by hand and clean it up. But it would be very exciting and save a lot of effort and allow automation if you had a way to actually do this cleaning automatically, so that you can optimize for a given resolution and then from there generate a curved mesh that is capturing the features that you are interested in. And then one final comment is that everything I discussed from the beginning is that the reason we want to go for higher order meshes is because we want to be faster. We want to compute results that are at a certain level of accuracy faster than taking a linear mesh and just refining it until we get the accuracy that we want. But we can always do that. We can always take the linear mesh and just refine it. So since the benefit is performance, one thing that is very important here is eventually to define benchmarks that allows you to honestly compare an entire pipeline, going from generating a linear mesh and solving the problem, or generating a curved mesh and solving the problem on the curved mesh, and making sure that indeed the extra cost that you pay in creating your higher order mesh actually pays off and you save it later on in the solve time. So something that is very encouraging is that usually the solve time is super linear with respect to the number of degrees of freedom that you have. So it's very likely that at some point, for a certain level of accuracy, the curved mesh is going to pay off, because in the construction of the mesh is usually more or less linear with respect to the input. But it's not clear, to me at least, where the cutoff is. And so it will be important to set up experiments on real applications that will actually allowing us to evaluate if the algorithms that are proposed to do curve meshing actually pay off, and if what we get is an actual speed up. And if that's not the case, then you probably want to stick with linear elements. It all really depends on the application. If you know that you need to solve the same simulation on the same mesh many, many times, then the benefit of going higher order is more clear. But it's still something that I think it's very important to evaluate before we get into a rabbit hole of something that maybe it's not a very promising direction. So I'm not aware of any experimental evaluation in this direction, and I think it would be very exciting to have one. There are a lot of evidence that this pays off, and curve meshes, despite the fact that they are so hard to be generated, they are still commonly used in industry. So it's very likely that they do pay off, but I think it would be nice to put some numbers on it to have a very clear idea of how much you are gaining for going to a higher order mesh. So this concludes my talk. I would like to thank the sponsoring agencies that are making this possible, in particular NSF, Adobe, Autodesk, AMD, and Topology. And I'll be happy to answer any question, both now or at any time during the week on Discord.
Hi, thank you, Daniele, for your really, really nice talk, introduction about a little bit everything, finite element, meshing, higher order meshing, numerics. I'm looking at the chat here. I don't see anything yet. Yeah, so remind everybody there is Zoom and Discord. So I'm going to start with my question. If you, the moment you go higher order, you end up, multiplying floating together. So you mentioned about the problem about the determinant. Do you think there are problems in just evaluating these things, integral, basis, etc.?
So yeah, it's every time you go for polynomials of higher order, you need to be careful. For the purpose of geometric map, I really don't think you'll ever go high enough to actually have problems. So it's more likely that it's going to be maybe like degree 2 or 3, or maybe you go for rational if you want to exactly represent circles or spheres. So I don't think there is going to be a problem, and I don't think there is any need for doing anything special. The other kind of meshes, the one that you get by computing displacements that are higher order, and then you apply them, then yes, there could be problems. I know that, for example, MFEM is advocating for using very higher order elements. They go to like degree 20, 30, and because these have like huge benefit in terms of computation, to keep the computation local when you solve a problem, because you get like massive dense blocks, which are better for working on clusters. But I don't know enough. I don't know what are the I expect that there are going to be numerical problems in there, but I don't know how they solve.
Yeah, thank you. There is a question. Oh, 2 questions. Okay, first, are you aware of any work using higher order meshes for polygonal faces?
That's a very good question. So higher order meshes for polygonal faces. So I think it depends on how you define your elements, but if your elements are defined, for example, using barycentric coordinates, these are already likely higher order. So I think it's, if you look at the literature on polygonal elements, there are many ways of building them. A reference on this is a book from Sukumar and Kai Orman. And so, yeah, it's definitely possible to do it on polygonal elements too. And actually, I think, I'm not an expert, but I think the large majority of the polygonal elements actually are already curved. They have to be, because it's very difficult to keep a polygon flat, especially if you are in 3D, because all the vertices needs to stay on the same plane, which is a very difficult problem that is actually tackled by many SGP papers that are figuring out how to compute meshes where every polygonal face is flat.
Thank you. There is another question, but I have a follow-up sneaking question here. So you were thinking about generic polygon, and it's hard to make them flat. I'm curious. I know you were working on hex meshing some time ago. There too, I mean, those are polygon, and they're usually not flat. Do you have any comment about, let's say curve or fake curve boundary for hex meshes?
That's a very good question, and I don't have an answer. I try to find one, but I don't really know. So like by construction, like if you have an hexahedral mesh, every face is going to be bilinear. And so this is something where it's like, for example, computing contacts or measuring distances. It's really much more difficult than doing it on a triangle mesh. And I don't know how this is usually dealt with. And I couldn't find any reference that actually explains how this is done. My guess is that for the purpose of computing collisions or distances, the face is just divided into two triangles, and then the distances are computed with the triangles, but I don't know. My first guess was that probably they do a procedure to make sure that all the faces on the boundary are planar, but this doesn't seem to be the case.
Yeah, also weird. Okay, so there is a question about CK continuity in contact mechanics. About, is it crucial to have higher order CK continuity for contact and contact?
So I don't have an answer, a precise answer, because I guess it depends on applications. So in graphics and in geometry processing, it's very common to solve very difficult collision problems with linear elements. So there definitely you don't have CK continuity. And as long as you have some padding, like the two objects stay a little bit separated, it's not, I don't think it's an issue, at least for applications in graphics. I do expect that, like, if a surface is supposed to be smooth, if you use a smooth representation, this should likely pay off. It's probably less likely that things are going to get stuck into these C0 discontinuities, but I'm not aware, I don't know how this could be done or how is it actually done, because even just computing collisions between moving curved surfaces, it's a very, very hard problem, and I'm not aware of a solution for it. And so if you use something that is CK continuous, but then at the end of the day, you compute your distances on a piecewise linear mesh, then it's not obvious that this is going to give you a benefit in the first place. But if you have any like direct pointer to these, and especially a case where it's very clearly shown that this pays off, I would be very curious to take a look and comment more on it on Discord.
Yeah, thank you, Daniele. And I think this is really a good point to stop already over time. Yeah, the Discord channel are going to stay open, I think, forever, or at least for a month from now. So if you have any question to any of the panelists, to any of the lecturer speakers, could follow up on Discord. And this concludes the summer school. Tomorrow they're going to be the official SGP starting, and I just want to remind anyone, this is something I wasn't aware, that all the summer school presentation of SGP are hosted, not only this year, which is special in Zoom, but all the previous year. They were all recorded, and they can be accessed and watch on school.geometryprocessing.org. So if you want to rewatch, to check a tutorial from past years, something you liked when you were in person, all the recording are there, and you're free to watch. Thank you again to all the speakers. Thank you again to all of you for being here, and see you tomorrow at SGP.